Cool. So there's strings/live, strings2020.com/live now takes you to this one.
Okay, our live stream feed is up. Nathan, if you don't mind, I'm going to share my screen quickly and just make a couple of announcements because we've changed the schedule and stuff. And then you can share again.
Okay, so I'll stop sharing.
Thanks. I just want to wait for a few more people to sign in. We're about 150 now. Okay, welcome everybody to the last day of Strings 2020. Just some of the usual announcements. Please do read and abide by our code of conduct. Keep your questions till the end of the talk. If you want to ask a question, please do use the raise hand feature and wait to be called by the session chair. In between that, we'd like to ask you to remain on mute. If you're going to use the chat feature, you can use it to ask a physics question to everybody, or ask an organizational question privately to one of the organizers. Then I would like to remind you that our Slack channels for the talks are still open. They've been open throughout the week, and you're very welcome to join one of the Slack channels and continue discussions about any one of the topics that we've covered over the week. And then I would like to inform you that we're going to be taking a conference photo, to the extent that such things exist, before the panel discussion. So what will happen is I will ask if you could please turn on your video if you're comfortable with that, and then I will take screenshots and we will compose the screenshots, and hopefully we will have a large enough number of people that will constitute our conference photo. We've changed the schedule slightly for today. Today is our special black hole information paradox day. So we will start off with Juan Maldacena with the review talk, and then we'll proceed on to the black hole information special session. The schedule has been amended slightly. The talks will now take on a 30-minute talk followed by 10-minute question each for the talks in that session, which will then take us to the conference photo at the end of that session and lead on to a special panel discussion on the black hole information paradox. The panelists will be Juan Maldacena, Ahmed Almeri, Netta Engelhardt, Samir Mathur, Jeff Pennington, Subrat Raju, Douglas Stanford, Andy Strominger, Don Maroff, and it'll be moderated by Malcolm Perry. And once that is finished, and we've allocated this an additional slot of an hour, so the total panel discussion will be 2 hours long. So there won't be any breakout sessions today, largely because we're just talking about black holes and black hole information. So we'd like to keep the conversation in one space. So again, the panel discussion will be 2 hours long, and that'll lead us to David Gross's vision discussion talk, and he will thank the he will give a list of thank yous, and then I will close the session at the end of the day. So with that, I will introduce the session chair for the first session this morning, and that's Nathan Berkowitz from ICTP Safer.
Okay, thanks very much for asking me to chair this session. So I have the double privilege of also announcing strings next year. So just to say a few words about strings next year, hopefully everything will go fine. It's going to be in Brazil from June 21st to June 26th, almost 1 year from today. And it will be organized by the ICTP South American Institute for Fundamental Research, ICTP Safer in Sao Paulo. There's a big string group there. We have 6 local organizers who are all well known in the string theory community. And also, fortunately, Juan Maldacena has also been involved with this institute since before it started. There are other string people who are closely involved. Peter Goddard and Fernando Quevedo have been involved on our steering committee also from the start. And more recently, Michael Green and Atish Dabulkar are on our steering committee. So there's a large string theory community involved with this institute, and it's going very well. And in fact, just after the strings in 2021, we're going to celebrate our 10th anniversary. So for people who can stay a few days longer, there'll be lots of presentations by people from South America that are involved with our institute, associate members, and also obviously some guests. Now, before strings, we're also going to have 2 satellite meetings. There's going to be a satellite meeting in Rio de Janeiro, the string math meeting at IMPA, which is the main mathematics institute in South America. And there'll also be a satellite meeting in Natal. So there's a Institute of Physics that David Gross is closely involved with that will organize a pre-strings workshop 1 week before. Unfortunately, they'll be at the same time, but maybe people can go to half and half. They're both in beautiful places on the beach, and I think it will be a great atmosphere for string theory in Brazil. So we hope you can all come next year. Hopefully everything will go well, and there'll be lots of great advances in string theory. It'll be exciting. Okay, so with that, let me stop the screen share, and I have the pleasure of introducing Juan Maldacena, who will give a review of recent progress on the black hole information paradox.
Hello, everybody. Can you hear me?
Yes.
Yeah.
Okay. So I'd like to start by thanking the organizers for organizing this wonderful conference, especially the accommodations. They really made me feel at home, made all of us feel at home. So my talk will be a review talk on the recent progress on the black hole information paradox. And it'll be largely based on a review that we recently wrote, and which in turn is based on a couple of recent papers that appeared during last year, and which is also based on many previous and follow-up papers. And my task today will be to try to summarize these developments and to explain all the ideas around these papers. I'll try to be basic, and there also have been very interesting recent papers by Saad, Schenker, and Stanford, also on the information paradox, but I will say very little about them. It's also a very interesting development, but I decided to concentrate on only the first part of the development. So the outline will be, I'll remind you of some things about black hole entropy. We'll discuss the formula for fine-grained gravitational entropy, and we'll compute the entropy of radiation coming out of black holes. And we'll see that we'll get a result using a result which is consistent with information conservation as opposed to information loss. And I will not be historical, but hopefully will be pedagogical. Now, we all know that black holes have a temperature, and then also black holes obey the first law of thermodynamics. Well, we can use the first law of thermodynamics to define an entropy, and when we do that, we get the entropy, which is the area of the horizon. And then the second law of thermodynamics is implied by the area, the classical area increase theorem of Hawking. Okay. Now, many of these calculations will be done using semi-classical gravity. So semi-classical gravity as an effective field theory. So in this approximation, we treat the background geometry as being classical, and we think of quantum fields propagating on that classical background. This includes also the perturbative gravitons that propagate on that classical background. And in this way, we can compute the back reaction due to Hawking radiation, treated using the semi-classical equations, where we calculate the expectation value of the stress tensor, and we put that in the right-hand side of Einstein's equations. When we consider this theory, there is an effective coupling, which is basically the strength of gravitational interactions at the scale of the Schwarzschild radius, which is of the order of the inverse of the black hole entropy. And this implies that things like the expected energy spacing of the various energy eigenvalues of the black hole are non-perturbatively small. And so naively, we would think that any statement that involves the microstates would seem to require non-perturbative accuracy. But we'll see that there are some things we can calculate even with the semi-classical theory, and that's one of the main messages. Some things that know something about the microstates, but nevertheless can be calculated. Now let's go back to the entropy again. So the formula that Bekenstein actually had the area term plus the entropy outside. So he was thinking about the entropy outside the black hole, and this term was the obvious one, and then he added the area term. Now, it was realized later that this term should also include the entropy of quantum fields that are sitting here outside. And that's necessary, for example, to get the second law when there is Hawking radiation, because the first term decreases, and then this one will, the second term will increase in such a way that total entropy will increase. And now this entropy of the quantum fields arises because we have only a portion of the full slice. The full slice goes all the way to or equal to 0, but we're only computing the entropy outside the horizon. And so that entropy is UV divergent here at the horizon, and that's supposed to be canceled by a renormalization of the Newton constant. And this has been checked for some scalars, vectors, and so on. This hasn't been completely demonstrated for gravity, but we believe it's true. Okay, and then with this formula, then the black hole obeys the second law of thermodynamics. So this includes both the area and these further corrections. Now, these results have inspired the very influential hypothesis that somehow pervades the language we use to describe some calculations we are using, including the thinking of the previous formulas and entropy. And we will call this the central dogma in the study of quantum aspects of black holes. And so this is the central dogma when we think about black holes as quantum systems. And the idea is that a black hole as seen from the outside can be described as a quantum system with s degrees of freedom, roughly s qubits or s Majorana fermions, where s is the area divided by 4 g-Newton. And not only that, but also it evolves according to unitary evolution as seen from the outside. So there's some Hamiltonian, and it evolves according with that unitary evolution as seen from the outside. So this is saying, so here pictorially, the black hole and its space-time around it can be replaced by some set of qubits. So normally we think of some kind of cutoff far away, some kind of infrared cutoff far away from the black hole, and we replace the black hole and the space-time around it by some set of qubits. And it's not completely clear how far this cutoff needs to be. If you want something very precise, you can think of this cutoff as being the ADS boundary, and maybe you couple that ADS, this CFT, to some other system, or this. So that, but it would not be very necessary for what we're going to discuss to make further assumptions about where the cutoff is. So if you wanted something very precise, imagine that as the ADS boundary. Now, sometimes people ask, what is the difference between a black hole and a piece of coal? So central dogma says that if you view the black hole from outside, there is no essential difference. Actually, there are some detailed properties even seen from the outside that are a bit different, that have to do with quantum chaos and so on. So we need a very strongly interacting piece of code, but it is the same in the sense that it is just an ordinary quantum system. Now, the word central dogma is similar to what is used in biology, where the similar dogma is some hypothesis about, so the word dogma comes from the Greek and it means hypothesis. And it's a hypothesis about how, in biology, it's a hypothesis of how information goes between DNA and proteins, etc. And here it's also a statement about quantum information and how the black hole is seen from the outside. Now, notice that these A or 4 g-Newton qubits that we are talking about are not manifest in the gravity description. And that's why it is an assumption. Otherwise, it would be a theorem if we knew how to derive them manifestly in the gravity description. Okay, and I should emphasize that this assumption is that these degrees of freedom are sufficient to describe arbitrary measurements with arbitrary precision outside the black hole, as long as those measurements are done outside the black hole. And it's only a statement about the black hole as seen from the outside, and no statement has been made about the inside yet. So we'll make a statement about the inside later, but we will not need those statements yet. Now, of course, from string theory, we have a lot of evidence for this central dogma. And the first big piece of evidence came from the entropy counting of supersymmetric black holes in supersymmetric string theories, whose entropy could be counted precisely using strings and d-branes, and were seen to reproduce the area formula. And not only that, but also corrections to this formula, and for some special cases, one can even get the integer number to come out from a gravity computation. Another Another development is the BFSS matrix model and BFSS conjecture, which, if you assume it, it's telling us what the 11-dimensional S matrix is. And this S matrix describes also, in principle, processes of black hole formation and evaporation. Of course, you will need to actually do the computation using the matrix model, but if you had enough computational resources, perhaps you could do that. And similar development, ADS-EFT tells us that a black hole in anti-de Sitter space can be described by a thermal state in a conformal field theory, which is a unitary system. Okay, so all of that is very good. However, Hawking in 1976 said that this idea can't possibly be true. And his reasoning was based on an understanding of where Hawking radiation comes from and from looking at the full space-time geometry of the black hole. So full space-time geometry contains an outside region. So this is the geometry of an evaporating black hole. It also contains an interior region. And when we consider that there is a full quantum state that contains entangled pairs of particles, some outside the horizon and some inside. So the ones outside are the Hawking modes that go to infinity. And the ones inside, we're going to call them the interior partners of those Hawking modes. And those go into the singularity. So if we consider a slice here in the far future, well, here, this particular slice I'm pointing here, we have a pure quantum state for the quantum field theory in this background on this slice. But if we restrict an observer who's outside only sees a part of that quantum state and therefore sees some entropy. And so roughly speaking, the skeptic's view is the following. So this picture on the left, which is the actual space-time picture for the black hole, can be viewed as, roughly speaking, as, so there is a parent universe here, there's some matter that falls in and creates some other disconnected universe. So here, after the black hole completely evaporates, we are assuming nothing very dramatic happens and that the two spacetimes disconnect. And so we have this other disconnected universe, sometimes called baby universe, but it really could be a very big universe. So it could be, this region here could be very big for a big black hole. So we will call it perhaps a teenage universe, not so much a baby universe. And it also, it's a universe that creates some problems with for the parent. So here we have some radiation, we have some apparent information loss. And so the skeptics would say, well, I mean, this is not very mysterious. In physics, sometimes we create an entangled state, and if we separate two parts of that entangled state by a long distance, and you have access to only one of them, then that only one part of it will look thermal or will look mixed. And if you had both, then it would be pure. But so that's the skeptic's view, and it's in contrast with the central dogma that we're talking about. Now that view can be formalized a little more by computing the entropy of Hawking radiation as it comes out of the black hole. So not just as a function of time. And so initially the black hole forms, there is no Hawking radiation, and then we start emitting Hawking radiation and its entropy grows steadily until it reaches some maximum after the black hole completely evaporates and it stays constant. As the black hole evaporates, the thermodynamic entropy of the black hole, on the other hand, decreases and goes to zero when the black hole completely evaporated. This is just roughly the area of the black hole that is decreasing. Of course, the shape of the curves is not exactly this one, and the precise shape depends on the details of the matter fields we have and the type of black hole we have. But the general feature, this general feature we see here is fairly generic. Now, here in the initial stages of black hole evaporation, this rise in entropy is not really a problem with the central dogma, because this entropy could be arising because we are entangled with the rest of the black hole degrees of freedom, and there are lots of black hole degrees of freedom, so it could be forming a pure state together with the black hole degrees of freedom. But after this time, if we are, for example, in this region, the entropy of Hawking radiation is bigger than the entropy of the remaining black hole, than the thermodynamic entropy of the remaining black hole. And so there is no way that we can make that we can make a pure state out of these two systems. This system is too small. Here, the black hole system in this region is too small. Notice that the problem arises here when the black hole is fairly big. So the black hole here, this black hole could be very big, has nothing to do with the endpoint of black hole evaporation. Okay, so that's a problem for that central dogma hypothesis. The behavior we expect if that hypothesis was true is what's been called the page curve, which is a curve where we could follow this behavior in this region, but then afterwards we cannot have an entropy which is bigger than the thermodynamic entropy. Since the radiation is purified by the black hole degrees of freedom, its entropy cannot be bigger than the total entropy of the black hole degrees of freedom. So we'll have to follow a curve like this. And so the question we can ask is, how do we get this curve from a gravity computation? So that's the curve expected for unitarity. Now, besides this paradox, there were other apparent paradoxes with the black hole entropy formula. And I will just quickly review them because they often come up in the discussions. So one is a confusing solution, which is the full Schwarzschild solution, the two-sided maximally extended solution, which looks like two black holes that are sharing an interior. So this on this particular surface, this surface is called the Einstein-Rosen bridge. It's a three-dimensional space that has roughly the geometry here. So it's asymptotes to two separate R3s connected by some wormhole. Now there is a closely related geometry, which is called bags of gold. So that geometry has an initial slice, which is similar to that of the Einstein-Rosen bridge, except that here we replace the second R3 by, let's say, an S3. And so we have here the solution in this region is close to the eternal Schwarzschild solution. And we'll develop to that as we evolve this in time. But it's connecting a flat space universe with a closed universe. And in this closed universe, we can have matter, and matter with a lot of entropy. So we can have a very big sphere with lots of matter. And in particular, we can have more entropy in the matter here than the area of the horizon. So this geometry was brought up as a counterexample to the statement that the area entropy counts the entropy inside. So the entropy on some spatial slice inside the black hole. Okay. And now we'll see how to resolve these confusions, and it's important to realize that all these confusions involve the black hole interior, and they have something to do with the interpretation of the black hole interior. First confusion was the two-sided black hole, and there we can have also another variant of the solution where the two black holes are in the same space-time and connected through the interior. And in that case, we can apply this central dogma separately for each of the two black holes. So there's a quantum system for each of the two black holes. And the connection is supposed to arise from entanglement. And in particular, the particular geometry of Schwarzschild is supposed to arise from this particular thermofield double state. So if you had access to all the microstates, then you would form this particular quantum state for these two systems, and then that should give that geometry. Now, the rest of the paradoxes involve a deeper understanding of the fine-grained entropy. And so first, I'd like to remind you of the two notions of entropy that should not be confused. One is what we are calling fine-grained entropy. It's also called von Neumann entropy or quantum entropy, or sometimes entanglement entropy. So this entropy is simply if you have a density matrix rho of your system, then you compute trace rho log rho, and that's the definition. An important property is that it remains constant under unitary time evolution. And another notion is the notion of coarse-grained entropy or thermodynamic entropy. And this arises due to the fact that we don't make a complete observation. So if you have some density matrix rho and you only measure a subset of the observables, for example, you only measure the energy, then there could be other rho hats which give the same value of the energy, but that have higher entropy than rho. And so if we look at the rho hat that has the maximal entropy, then that's the coarse-grained entropy. And this entropy obeys the second law, so it can increase under unitary time evolution. For the moment, we'll be talking about the entropy of the black hole as seen from the outside. And this is the entropy of the quantum system that appeared in the central dogma. So that's, we imagine that that quantum system has some rho. We don't know from gravity exactly what that rho is, but it has some rho, and we're computing the entropy of that rho. Okay, so it's somehow the entropy of the piece of coal. Now, on the other hand, the horizon area, so the formula by Bekenstein and Hawking, computes thermodynamic entropy. So the question is whether we can compute the fine-grained entropy. And in some developments that starting in 2006 with a formula proposed by Ruan Takayanagi that was improved by various other authors, we have come now to a formula, which is this formula here, that tells us what the fine-grained entropy formula is. So it basically has the same form as the usual black hole entropy formula. The only difference is that we are computing the area of some other surface, not the horizon, but some other surface, and also, of course, the entropy outside that surface. And the idea is that we'll select this surface X in such a way that we extremize this generalized entropy. So here is a drawing and a Penrose diagram. So we have some surface X, and we have some we have a region from the cutoff surface to the to this point X. And so we compute the entropy of the quantum fields on this green slice. We add the area of X, and then we choose an X by moving it in the space and time directions so as to extremize that quantity. And if there are many extrema, then we pick the minimum of all such extrema. Okay. There are also other ways of defining it, some maximum procedure, which I'm not going to discuss. A crucial point is that we're allowed to take the surface to the interior of the black hole. And therefore, the value of the entropy that we get in this way will depend on the geometry of the interior. And you should be surprised by the claim that there is a formula for the fine-grained entropy. I mean, we are familiar with the fact that the black hole behaves as a thermal system as seen from the outside. There is some hydrodynamics and so on. But certainly, such formulas for the fine-grained entropy is not something that we have in ordinary hydrodynamic systems. And it is related to the black hole that has an interior, which is also something we don't normally have in hydrodynamics. Now, let me show you how this formula works by working out a couple of examples. So first, imagine this collapse geometry where the star collapses into a black hole that maybe then evaporates. So in this case, we can take the surface X and shrink it completely. So we have what we call a vanishing surface, or surface with zero area. So it goes here to r equal to 0 at the center of the star inside the black hole interior. And in this case, we just the formula, the entropy reduces to the entropy of the quantum fields here in the interior, and that picks out just the entropy of the star. And if the star was in a pure state, then this entropy would be 0. Now notice that if we calculated here at this point the area of the horizon, that would be non-zero. So thermodynamic entropy, in this case, it's bigger than the fine-grained entropy, and that's good. And here in this process of collapse, the fine-grained entropy is preserved. Now, the new development in these two papers, the new idea was the realization that there was another extremal surface that arises sometime after the black hole forms. So about the scrambling time after the black hole forms, you can have a new quantum extremal surface, so a new extremal surface, as we defined. And in this case, the area is not the minimum, but the gradients of the area with respect to the position of the surface are balanced against the gradients of the quantum entropy, and those develop some gradients due to the Hawking radiation and the fact that the Hawking radiation leaves the system. That ensures that you can find actually a solution. I won't go into the details of exactly where the solution is. There are some interesting properties about the position of this surface, but the only thing that we will need for our later discussion is that this position is fairly close to the black hole horizon. And as time evolves, as we compute this at different times, this surface also goes up along the horizon, and the value of the actual value of the entropy is close to the area of the horizon. So the quantum fields are have a large gradient, but they are smaller than the area term. So we discussed two possible extremal surfaces. So one is the vanishing surface, or the surface with zero area, which we can define at any time. And here, when we compute it at, for example, late times, we get the entropy of all the interior Hawking modes, which, if we started from a pure state, is equal to the entropy of all the exterior Hawking modes, and that gives us a rise in entropy. Okay, so that's from this vanishing surface. And then from this other quantum extremal surface, we get something close to the thermodynamic entropy of the black hole. So we will follow this curve that goes down. And now we are instructed to choose the minimal one. So if we choose the minimal one, we get this this curve, which is roughly like it's roughly like the page curve. So we get something like the page curve for the entropy of the black hole. But what we really wanted was the page curve for the radiation. Now, the radiation lives in a region where quantum gravity effects could be very small. So it could have left the ADS space, and it could be collected in a faraway quantum computer. And but the idea is that since we obtained the state using gravity, we should apply the gravitational fine-grained entropy formula even for computing that state, which lives completely in a region without gravity. And so that leads to the so-called island formula, where if you're computing the entropy here in some region that contains purely radiation, and let's say you can neglect gravity in this region, let's say the interior of this cutoff surface could be ADS, and the exterior could be some other quantum system. Then when we compute the entropy in this region, we should also apply a formula, well, essentially the same as the formula for black hole, the fine-grained gravitational entropy formula, which involves, again, a surface and an interior here. And we can, again, minimize, or extremize and minimize over the choices of x. And we should view this as basically a special case of the gravitational fine-grained entropy formula. So it's a special case, really, of the previous formulas. Now, there is one aspect of this formula that has caused a lot of discussions and heated arguments. And this is the fact that the quantum fields in this region appear both in the left side of the formula and in the right side of the formula. And they mean really two different things in the left and right. So here we are computing the entropy of the exact radiation state. So there is some supposedly exact radiation state that we compute using the full non-perturbative theory of gravity, et cetera, et cetera. And in the right-hand side, we have quantities which are all computed within the semi-classical gravity description. And here we are considering the state of the radiation fields as it appears, the quantum state, as it appears in the semi-classical gravity description. So this radiation region and the quantum state is really different on the two sides of this formula. Now, if the initial matter state is pure, the quantum extremal surfaces are the same as the ones we discussed before, and therefore we get the same curve as we got for the black hole, and we have the page curve for radiation. Okay, so this is a derivation of the page curve of the black hole from gravity reasoning. Now, the skeptic would complain, and they would say, "Oh, this is just an accounting trick." They would say, "I have always said, if you include the black hole interior, then the state is pure. So you are cheating because you're including the black hole interior. And of course, the black hole information problem arises only because you don't have access to the interior." Now, I would say that more than an accounting trick, this is like an accounting oracle. So it can, first there is the point that this formula that we've discussed can be derived from the gravitational path integral. And we'll discuss the derivation in a second. But it's an oracle in the sense that it gives us the true fine-grained entropy of the exact state, but only using the semi-classical state. So that's where the miracle lies. So I'll briefly now talk a bit about deriving the RT formula. It is conceptually similar to the derivation of the black hole entropy formula using the Euclidean black hole. And it has some of the same advantages and disadvantages. So first, I remind you of the Euclidean black hole. We have a thermal circle at infinity, and we then have a geometry that fills in this circle at infinity with some geometry that obeys Einstein's equations. And we interpret the result of this computation as giving the trace of e to the minus beta h, where h is the Hamiltonian that was appearing in the central dogma, and the trace is over the Hilbert space that was appearing there too. Presumably also that's some Hilbert space that arises from the full quantization of the gravity theory, but we don't have direct access to the left-hand side. So the left-hand side is some system that's supposed to exist. The right-hand side is the thing we know how to calculate, so we can have the gravitational action and evaluate the action. So that's just the usual Einstein action. And then we can calculate the partition function of the quantum fields on this geometry, which gives, with usual renormalization and so on, gives a finite answer. And then once we know here the right-hand side, we can apply the usual thermodynamic entropy formula to calculate the entropy. And we get this variation of the Einstein term essentially gives the area, and similar variation of this case gives the the entropy of the state that appears in the semi-classical description. So the entropy of the quantum fields outside the black hole horizon. Okay. Now, we can view this formula in slightly different way. Well, basically it's the same, but so if we can imagine cutting open this circle, and then that would give us some kind of trace of rho, rho tilde, so it's an unnormalized version of rho. And then if we go around the circle n times and then we join them together, then that would be computing the trace of rho tilde to the n. And of course, this is exactly the same as the previous discussion, except that we're making the inverse temperature n times bigger than the previous one. And if we can analytically continue in n, then we can take the derivative with respect to the temperature and get the formula. And so this the advantage of thinking about it this way is that we can also apply it to cases where we don't have a U1 symmetry. And so we could imagine we create a density matrix by doing Euclidean evolution, but inserting some operators or doing little wiggles here. So this little wiggle really means that we are changing the boundary condition for the fields at some point in Euclidean time. And we can do that. We can insert operators along the Euclidean time direction. And in this way, we can create gravity waves, or we can create all kinds of waves of other fields. Or we can change the boundary conditions for other fields. And this way, we can create fairly general states, fairly general and complicated states. And so if we can describe a state in this way, so a state, let's say, created by the Euclidean path integral, then we can consider n copies of the state. And that's, again, given by a more complicated, and the trace of that rho tilde is given by, again, a Euclidean path integral. Notice that here I'm talking about the Euclidean path integral, but here we could do Euclidean evolution up to this time, and then Lorentzian evolution, and then put all those things together again. So this is fairly general. And in cases where this geometry has the full geometry in the interior has respects the CN symmetry of the boundary conditions, we can sort of analytically continue the evaluation of these geometries up to n close to 1. And in that case, the formula, or the action for these geometries reduces to an area plus the semi-classical entropy of the quantum fields for similar reasons as in the Gibbons-Hawking computation. And this minimization or extremization over the area is just simply the process of minimizing the action of these geometries. And so in this way, we derive this formula, and the derivation is conceptually similar to the Gibbons-Hawking computation. Now, and it is conceptually similar, and it has some of the same defects as, well, has the advantages and defects. One advantage is that it gives us the actual answer. And the disadvantage is that it does not tell us what the quantum state rho is. One might have thought that in order to compute the entropy, you need the actual value of rho, but this formula of the density matrix, but this formula gives us the trace of rho log rho without giving us what the actual rho is. Okay. Now, if the state is prepared by Euclidean path integral and has dynamical gravity, let's say only in some regions, then we should allow various topologies in that region. So as usual, when we do black hole thermodynamics, we can allow various topologies. And when the interiors are connected by different topologies, we can call this replica wormholes, and they lead to the island formula. So here is one simple example. So here we have flattened the cigar that we had in the previous formula. So we are representing it as a disk. And then we have some region outside this cutoff surface that, let's say, it's a flat space or some space with no gravity. And we are interested in computing the entropy of some region outside. So this would be analogous to the radiation region. And then in order to compute this entropy, we need to introduce many copies of the system. So we're considering here the particular case where we consider 2 copies. So we have 2 copies, and then we connect the exterior regions. So this connection between the 2 copies comes from the fact that we are taking the trace of rho squared of the entropy of radiation. And then the interiors can be connected in various ways. So one is we can just have 2 separate black holes. And this type of solution, after we continue, take all possible n's and continue in n, would give us a Hawkins result. On the other hand, if we connect these black holes through the interior, then this is what's called a replica wormhole. So a kind of wormhole that connects 2 replicas of the original system. And we continue in n and so on. That will give us the page answer when it dominates at late times. And so this fact that the interior geometry topology can be different, I mean, it's familiar in many other cases of black hole thermodynamics. For example, black holes in ADS or flat space can sometimes have this Hawking phase transitions. So the idea is that as you vary the parameters, sometimes this geometry dominates and sometimes this geometry dominates. So in fact, the transition between the Hawking curve and the page curve here, this decreasing curve, is actually a Hawking page transition for all these replica geometries that in the limit when n goes to 1, they give rise to this transition between the 2 cases. And actually, there's been some work actually finding out what the curve is very close to this region. We cannot have a sharp phase transition because we have a finite entropy. And indeed, this curve gets rounded up by effects that go like 1/√G Newton. And this was explained in these papers. Now, notice that the Rayleigh entropies are given by these other non-trivial geometries, but the von Neumann entropy is given by computation in the original semi-classical geometry. So that's the computation that we were doing to use the Ruta-Kayanagi or Engel-Hallwall formula. So far we've only talked about the entropy, but the question is, what is this telling us about the interior? So how do we describe the interior? Now, as I've emphasized, the central dogma involves some degrees of freedom that describe the black hole from the outside. But a very natural question is, what part of the interior do these degrees of freedom describe? Do they describe all of the interior, none of the interior, part of the interior, and if so, which part? Okay, so that's a very important question. And before answering this question, we'll introduce a new concept. Okay, and this is the concept of entanglement wedge. I mean, following the logic of this presentation, it should be called the entropy wedge because it's associated to the computation of the entropy. But originally, this was viewed as entanglement entropy, and so it was called entanglement wedge. So this is the causal domain of dependence of the region that appears in the computation of the entropy. So namely, these are some examples. So for example, here we had a black hole, and let's say we were considering the vanishing surface. So we had a spatial slice that went all the way to r equal to 0. And then all the points in the green region are points that can be obtained by evolution from initial data on that slice. Okay, so that's the green region here is the entanglement wedge of the black hole at this time. When we had the new quantum extremal surfaces discovered in the papers of last spring, then we had a spatial slice that went only up to here, and then the causal domain of dependence is this other region, which only covers a small portion of the black hole interior. And on the other hand, when we calculated the entropy of radiation, we also were including an interval on this side. And so the entanglement wedge of radiation includes this portion of the black hole interior. Okay. And then if the black hole evaporates completely, then the entanglement wedge of radiation includes all of the black hole interior. And here, if the black hole evaporated completely, then the region inside this cutoff surface would just be flat space, and that would be the entanglement wedge. So these are various examples of entanglement wedge. So now we go to the answer to the question we posed before about how much of the interior we describe. And this is called the entanglement wedge reconstruction hypothesis. And it says that the quantum system describes everything that is included in its entanglement wedge. So by describes, it means that we can recover the state of a probe qubit inside the entanglement wedge. And this recovery is sort of state dependent or subspace dependent. So it depends on the state of the rest of the qubits, of course, not the state of the probe, but the state of the rest. And it is similar, it involves concepts of quantum error correction and so on. And I won't discuss in detail how this happens. But the idea is then that when we have, let's say, an old black hole, so a black hole past the page time, then the black hole degrees of freedom describe this portion of the interior, but the radiation, the radiation describes this other portion of the interior. Okay, so that's the idea. So this, so the answer then of the previous question was the third possibility, that the black hole degrees of freedom describe only part of the interior, and the part of the interior they describe is determined by the entanglement wedge of this black hole degrees of freedom. Now, what this implies is that by performing a very complicated operation on the radiation, we can extract information from the interior. Okay. Now, how does this happen? So there are a couple of ideas for how this happens. So one idea is that the complicated operation creates a wormhole connection that connects the quantum computer that is doing the complicated operation with the interior of the black hole, and then pulls the information from there. And a concrete example of a setup where this happens is the Gauss-Jeffreys wall traversable wormhole. But then there are some more general discussions based on concepts of quantum information theory, such as the PETS map and so on, that give a similar picture for more general states. Another idea is to use the modular Hamiltonian for, which is the trace of rho, which is non-local, can be act non-local in the bulk. And this has also been explored as a possibility. Okay, so now this brings us to the AMS paradox. And the AMS paradox was a paradox that was arising when, by making a certain set of assumptions. And the assumptions that they made involved the central dogma that we discussed before, plus one further implicit assumption about the interior. So they assume that the interior operators act on the Hilbert space of the black hole. In other words, they were assuming that the interior could be described in terms of the black hole degrees of freedom, that the whole interior belonged to the black hole degrees of freedom, that black hole, that set of degrees of freedom that appeared in the central dogma. And the current, well, what we now think is that this hypothesis is not true. Okay, so that's the thing that is not true, and that is how we will solve the AMP paradox. So I remind you that the AMP paradox relied on saying that we have some late some Hawking radiation emitted at late times that was supposed to be entangled with the with the early time Hawking radiation, and we call B prime the distillation of the mode that is entangled with B. So the actual, so we distill the particular qubit that is entangled with B. Then we have some paradox because B is supposed to be entangled with B prime, but also B is supposed to be entangled with the interior Hawking partner of called A, of the interior Hawking partner of B, and so that leads to some configuration which violates the strong subadditivity. But the idea here is that this mode B prime that is entangled with B is some mode here in the island region. So this is what B prime is. And it can be here because this island is somehow created out of some complicated entanglement pattern in B. Okay, and then A is just the future. It's essentially the same as B prime, just the future evolution here into the white region. Now, it's important for this not to confuse the following two things, which are sometimes confused in the discussion because our language is a bit imprecise. So one is there are two concepts which are called black hole degrees of freedom, and we need not to, it's important not to confuse them. So one is the degrees of freedom that are necessary to describe the black hole from the outside. This is sometimes called also the black hole degrees of freedom. Now, in the piece of cold analogy, that would include all the degrees of freedom in the piece of cold, both the degrees of freedom in the surface of the cold, as well as the degrees of freedom in the interior of the cold. So some atom in the middle of the cold is also included here. And second is the quantum degrees of freedom in the black hole interior. So let's say some qubit that is here in the interior of the black hole, that sometimes is also called the black hole degrees of freedom because it's somehow inside the black hole spacetime, but they are not the same as what we were talking about here in the top of the transparency, okay? And in fact, for example, and in particular, they are not the same as the degrees of freedom inside the piece of cold. It's actually wrong to think about them. Well, at least we think it's wrong to think them as analogous to the degrees of freedom inside the piece of cold. For example, in this setup, we have some qubit that is here inside the island. And the idea is that this qubit is really a degree of freedom, some complicated degree of freedom, which in principle we can access from the outside, okay? And so it has nothing to do with the degrees of freedom in the middle of a piece of code. So if we go back to this idea of this teenage universe that we have here, not big baby universe. So the parent here has access only to a portion of this teenager, okay? And the other portion of the teenager is only accessed from the outside, from outside influences, okay? Now, there is something non-trivial that needs to be explained, which is that why simple operations here on the radiation do not disturb this qubit. And there are ideas, I won't go into the detail of this, but there are ideas of quantum error correction, quantum complexity, and so on, that are supposed to explain how, why that happens. So if you do a simple operation, you really are perturbing the full quantum state, but in a way that you can still quantum error correct so that this qubit can be actually extracted, nevertheless. And there is an interesting developing story for understanding better and better how this happens. Okay, so there is another comment, which is that the entanglement wedge is a property of the state at some time, t, okay? And on the other hand, things like horizons depend on the actual Hamiltonian that we have for the system and depend on what will happen in the future, okay? So for example, in this setup that we had here, let's say at time t, we decouple the quantum system that describes the black hole. We put some boundary condition here, and we decouple this from the radiation. So at this point, the black hole is not evaporating anymore, or well, it could continue evaporating into this flat space region, but there will be a gas of particles in flat space contained here, reflected from this wall, and so on. And in here, again, we just don't let the radiation interact with the black hole any longer. So, so in these cases, then the position of this horizon might be changed by exactly which Hamiltonian we choose here. But the idea is that no matter, so if we decouple the system and we do arbitrarily complicated operations here, we can never access what is in the island. So in some sense, this quantum extremal surface is really the boundary of the region that we can access doing extremely complicated operations on purely the black hole degrees of freedom. Now, let's return to this issue of the bags of gold. If we have that set up with the bags of gold, and we have a lot of entropy inside, then precisely when there is a lot of, when the entropy inside is bigger than the area here, you will find that the actual minimal quantum extremal surface will be essentially given by an area around here, around the neck. And if that happens, then the entanglement wedge of the outside, or the black hole degree, this outside black hole degrees of freedom, will only go up to this surface. And so this whole blue interior region belongs to someone else. I mean, it belongs to whoever is entangled with the matter inside this closed state universe. Okay. Okay. Now, the reason that the bag of gold sometimes appears in this discussion is because if we consider a slice at late times, so the geometry of this slice and also the entropy on this slice is very similar to the bag of gold. So here we have a relatively small neck here where we are crossing the black hole horizon. And then we can choose a slice where the area here and the size of this interior region is very big, and which would contain a lot of entropy if this is a very old black hole. In the same way that here this interior region belongs to the radiation, in the bag of gold, the entropy within the bag would belong to some other system that depends on how we created that closed universe. So in conclusions, we reviewed the gravitational fine-grained entropy formula. We applied it to the computation of the entropy of the radiation and obtained results consistent with unitarity. And at late times, most of the interior is part of the radiation, not part of the black hole degrees of freedom. Now, what was Hawking's mistake? Well, Hawking's mistake was simply not to use the fine-grained entropy formula. Of course, it hadn't been discovered at the time, but that's our current view. Now, a lot of what we discussed was derived by thinking about aspects of ADS-CFT, which itself involves string theory, but you only need, and this was very important for checking and testing these formulas and developing these formulas, but you only need gravity as an effective field theory to apply these formulas. And so this is a part of an amazingly deep connection between gravity and quantum mechanics. Now, is the information puzzle solved? Well, one aspect is solved, the aspect of computing the entropy, yes, but there are other aspects of the puzzle which are not solved. So for example, part of the puzzle involves understanding how different initial states go to different final states. And we are not saying exactly what the final state is, so that aspect has not been solved. So calculating the gravitational S matrix, that has not been solved from the point of view of gravity. Of course, if you assume other conjectures like BFSS and so on, then you can solve that too in principle, but it has not been solved directly by doing some gravity computation. Because these replica wormholes compute the entropy, but do not tell us what the state actually is. And this is the same as the formula for the black hole entropy. It's an accounting, let's say, oracle that gives us the explicit, but the explicit gravitational representation of the states is still mysterious. Now, there is another aspect of the gravitation of the information problem, which involves long-time behavior of correlators. And these have corrections that are due to the discreteness of the energy eigenvalues and the finiteness of the entropy. This is some other aspect of the black hole information problem. And there's been great progress on this aspect in beautiful papers by Schenker and Stanford. And there was a particular feature, I don't have time to discuss this, I'm only just mentioning it. And there's some particular feature called the ramp, which can be understood as coming from this geometry. If we average over all these wiggles, so if we average over couplings or average over the time, so we somehow do a suitable average between these two systems, we get, we can explain this ramp, or they manage how to explain the ramp in terms of this geometry. And in another paper, they discuss how JT gravity can be interpreted as arising when we average over Hamiltonians. And this gives a new view on the random matrix and string theory connection. And it gives a new interpretation for the matrix that appears in that connection as a random Hamiltonian of a random quantum system. So in those discussions, the idea of random couplings that give rise to geometric connections was important. And this connection between random couplings and wormholes was suggested in the past. And these ideas are being revisited. And there is the question of exactly what role they play in ADS-CFT and in string theory more generally. And this is part of what is being explored actively. So for the future, the question is, what further lessons is this teaching us about the interior and the singularity, and what implications will have for cosmology? So thank you.
Thanks very much, Juan. So we can start with questions so people can raise their hands. So Dan Harlow, you can just unmute yourself and ask the question.
Yeah, hi, thanks for the nice talk, Juan. I guess before we completely dismiss the EMPS paradox, I wanted to mention that, I guess, from my point of view, the only EMPS paradox that survived longer than a year or two after the original papers was the one about typical pure states in the paper of Meroff and Polchinski. And my understanding currently is that these recent developments do not resolve that paradox, because if you have a black hole in a typical but pure state, it's not entangled with anything else. And I'm curious if you have any thoughts about that, or do you think, I mean, as far as I know, we don't know whether the horizon of a typical pure state black hole is smooth or not.
Yeah, I agree that we don't understand what a typical pure state is. And I think that's important. It's related to the question of getting a better gravity picture for black hole microstates.
Yeah.
Upamanyu, you have a question for Juan?
Yeah. So hi, thank you for the very nice talk. A few weeks back, there was a paper by Andreas Kirch and one of his collaborators on entanglement islands in higher dimensions, where gravitons exist as a propagating degree of freedom. The graviton in their picture, which is in a Randall-Sundram brane with transparent ADS boundary conditions, is necessarily massive. However, they found that in the limit that the graviton mass is taken to zero, the island does not contribute to the page curve. I was wondering if you could make a few comments about it.
Yeah, so in these papers, it was noted that when we take let's say an ADS space and then we couple it to some external system, we can think of that as having a massive graviton. This goes back to ideas of Karsh and Randall. So in these situations, the stress tensor that is dual to the graviton in the original ADS is not exactly conserved because it can leak to the other system. And so, yeah, so the graviton mass is related to the coupling to the external system. And indeed, when you try to make it massless, you decouple the external system, and then you will not have the island, because having the island, in order to have the island, it's important to have the other system. So yeah, indeed, these things are connected in this example. Now, the fact that we can describe this lack of conservation of the stress tensor or energy as a graviton mass is special to situations with lots of symmetries, like conformal symmetry and so on. In general, the idea is that, well, the energy is not conserved. There is some exchange in energy between two systems, and but whether we can describe that as a mass or exactly how we describe it, that's another issue. I mean, it's just perhaps the simplest description is that we're just not conserving energy. We're coupling to an external system, and that's important for getting the island and the new quantum extremal surface.
So in that case, in the let's say in the real world where the graviton is supposed to be massless, to what extent does the island give the page curve?
Yeah. So in the real world, you would need to separate the black hole from the rest of the system. You would need to say, right, that you separate, let's say, the black hole and its environments from some other system where you will collect the Hawking radiation. And it's only to the extent that you can separate these two that you can even talk about the island. If you always consider the whole system, then there is no island. Then there is just the entanglement wedge includes everything, and the state is always pure. So to the extent that you separate these two things, then because there is a coupling between the two, there is no the graviton in the interior will be massive. But this is when you prepare the system. Of course, you can decouple the two systems, and if you decouple them and you let them evolve, now the graviton will be massless in the, let's say, in the interior in an ADS situation, but there will still be an island. There will be an island because in the past, when you were preparing the state, you were coupling the system. So it's not, so the island is a property of the state, and you could have also a state with, let's say, massless gravitons, which contains an island, if you prepare it by coupling it to some other system.
Thank you very much.
Andy, you want to ask you a question?
Yeah, so in ADS, we have the Ryu Takanagi and its quantum version, which I guess we were originally just conjectured, but ultimately could be derived, and then the quantum extremal surface story. So it could all be subsumed or was consequences of some larger vision of holography in ADS. So in asymptotically flat spaces, would we hope that this quantum extremal surface for computing the rate of black hole entropy are somehow derived from some kind of holography in flat space? And if so, what could that be? Or maybe you just don't want to do that.
No, yeah, you in principle, there is probably some way of deriving it using some kind of holography in flat space, and perhaps dividing the null infinity into regions and deriving some version of this. I guess you've written a paper about this recently.
Well, but that could be wrong. But more generally,
well, I think this formula. So an important feature of this formula is that it relies on the existence of a quantum system that is well defined, whose entropy we're computing.
Yeah.
Right. So if we try to apply to de Sitter, for example, it's a bit unclear how to define that quantum system. What is the quantum system whose entropy we're computing?
Yeah.
But maybe there is a more general formula. Sandeep?
You have a question?
Can I ask a question? Is that okay?
Yeah, sure.
Okay. Yeah, Juan, you touched upon but didn't say more, and I want to ask you to comment a little more on what I feel is a very mysterious aspect of this whole proposal, namely that you can manipulate the radiation outside, admittedly perhaps with very complicated operations, and then affect the island, which is very far away in the interior. And I wanted to just ask you, if that is going to be true, why aren't we worried about massive violations of locality? Just to put it another way, you could have thought of preparing that state of radiation, the final state of radiation, in principle, through a very complicated experiment which never involved a black hole evaporating, etc., and do some similar complicated manipulations on it. Then again, presumably now you don't have the black hole interior, but you're affecting some region far away. How is this story supposed to work, even conceptually?
Yeah, let me show you a picture again. Let me see. So let's imagine you do what you just said, right? Preparing some state of radiation that is the same as the state we have in this case, right? The idea is that if you did that, then we'll also have this region of the space-time geometry. We wouldn't have the green region necessarily, but we would also have this region.
I see. Even though there may not be any black hole, or would you say?
Yeah, there would not be a black hole. There would be maybe a black hole interior here, and this green region could be completely different. We don't know what it is, but the idea is that there would still be this region inside.
And so would it?
This is a hypothesis. I mean, I'm just giving you what we think is true, but there's not much evidence for this.
Yeah, no, I understand. But then would it mean that if you created sufficiently complicated states and did sufficiently complicated manipulations on them, you could be affecting regions of space-time very far away, because wormholes would open up and connect you to those regions?
Yeah. There are wormholes that somehow that connect. So the entropy between here and here, like little wormholes that connect these two regions. So in some sense they're close, but in some sense they are far away. So.
And this should just be a general property of a quantum theory of gravity, not even necessarily tied to the interior of a black hole.
Yes. That should be a general property. Yes.
I see.
Of course, one thing we were very proud of in the earlier work on wormholes that they exactly don't do that. They exactly don't introduce any non-localities once you went to the super selection sector. So there must be something very different about the way that wormholes are included in this context than in those ones.
Yeah.
I don't think they're giving non-localities. I think the non-locality that they give is the type of EPR non-locality, right? Not there is nothing. There is no non-local direct interaction.
Suppose I make a black hole out of red stuff instead of blue stuff that goes into there, into
you change this,
and I send it from down on Scry minus, and I go to where you've written island, and I make a red shock wave.
Yeah.
And then instead I make a green shock wave.
Right. So
I have a flavor symmetry, let's say.
Yes. You can make two different states here. And then the idea is that the state of the quantum fields here would be subtly different. It would be slightly different in the exact theory. In the semi-classical theory, the state of the quantum fields here would be very close. But in the exact theory, they would be different.
Could I suggest a slightly less provocative answer to Sandeep's question? So take the very complicated state of the radiation that you made synthetically in the lab by manipulating a lot of photons rather than by collecting Hawking radiation. Once you have that very complicated state, you could also make very complicated measurements on it. And in general, you get very complicated answers. However, the claim would be that if you make the suitably chosen and carefully chosen very complicated measurements, you'd actually get simple emergent answers that could be described simply in terms of what you might call an emergent spacetime, or what you might call it an accounting trick. But anyway, it would be a simple description of outcomes of certain very complicated measurements on the complicated state.
But
that's
sorry.
That's a way to answer Sandeep's question that I think is slightly less provocative.
I see, and sorry, and I should get offline and give others a chance, but to both Juan and Edward, you in such a case, when there's a simple description, wouldn't it amount to a mass locality? Can't you burn up the Britannica deep inside by doing something to the radiation? Sorry.
Well, if you created the state synthetically, there wouldn't be any answer to the question of where this effective description was. So in the experiment you suggest, there's definitely not any non-locality. There's just a convenient description of the outcomes of certain carefully tuned but complicated measurements.
Okay. I see. Thank you.
Alexander, you have a question?
Hi, Juan. I wanted to ask, Imagine that I take a quantum field theory, which is in a swampland. So I can, if I couple it to gravity, then it makes a perfect semi-classical theory, but we cannot make sense of it as a full quantum theory. Then if I understand correctly, I can do the computation you described and I will get the same curve.
Yes, yes.
So what is the interpretation of this?
Well, it's just saying that for the purposes of this observable, this theory is behaving the same way as a unitary theory. Now, maybe there is some further inconsistency when you analyze it more precisely, but you don't see it at the level of this calculation.
So in this formula on the left-hand side, as you emphasized, you have this exact.
Yes. But this is so that. But that exact state is a conjecture, if you wish. It's part of this state that was appearing in the central dogma. So the central dogma would not be correct in, let's say, a non-complete theory. But the right-hand side is still behaving as if it was correct.
Right. So in this case, I might erroneously conclude that I have some unitary quantum theory. So yeah, I will get the page curve, but
yes. Yeah, that's true. Yes.
Emil, you have a question? Emil? I see his hand, but I don't hear him. Emil, you're muted.
Are you asking me? I didn't raise my hand.
No, Emil.
No,
Sorry, I was
Okay,
muted. My apologies.
Go ahead.
Yeah, so let me ask the previous question in a slightly different way. So, I mean, heavy use in all of this is being made of solutions of low energy effective field theory. And so how do we know, or what's the evidence? How do we justify whether or not the island and the interior and all the structure that's being employed isn't part of the swampland, that there is sort of a swampland of Penrose diagrams that you can draw? And how do we know that this isn't just some artifact of low energy field theory that isn't part of some fundamental construction?
Well, I think we don't know. So the part of the point is that here well, as I was saying before, as long as you have the low energy gravity theory, you can do these computations and they will give you answers which are consistent with unitarity. So let me make an analogy which perhaps is more familiar. So if you, let's say you're considering a gravity theory in ADS, right? And if you consider just purely, instead of gravity, just purely field theory, and you do not allow the possibility of forming a black hole, you compute the entropy of fields in ADS, you have a contradiction with the boundary CFT, right? But if you allow the black hole formation, then you don't have a contradiction with the boundary CFT, right? Now, so that means that when you form the black hole, you get something consistent with having a boundary dual. But it could be that the bulk theory in ADS is in the swampland and it doesn't have a gravity dual, and it, I don't know, maybe have some instability and so on. And you will not see that by looking at the black hole solution. I mean, the black hole solution exists even if the theory is in the swampland. And
yeah,
I think, so as I was saying, this whole discussion has the same basically advantages and disadvantages as the usual black hole entropy formulas. And this is one of them.
Takato, do you want to ask the question?
Yes. Let me ask one naive question, two questions in total. First, in the fine-grained gravitational entropy formula, how is the observer dependence incorporated?
Observer dependence. Well, I think it's not, there is no observer dependence. I mean, there is just the formula is the actual formula that any observer.
I mean, since the state itself is observer dependent idea, right?
No, so the entropy depends on the state, right? So trace of rho log rho. And yeah, so it's an objective thing that measured by any observer that has access to the quantum system will get that entropy.
But
no observer depends. Of course, the value for the entropy depends on the state, right? So the value depends on what rho is.
So you're not assuming the entropy is measured by asymptotic observer?
Yes, I am assuming that. I'm assuming that the entropy is measured by someone who has access to all the quantum degrees of freedom of the system. So it can be defined only when there is a quantum system that is well defined, and we can do arbitrarily precise measurements.
I see. Well, let me ask you another question. You're assuming the black hole is a pure state, and why is it not in mixed state?
Well, I assumed it for the simplicity of the discussion. So for example, when we form the black hole, we could form it with matter, which has some entropy. And as long as the entropy is not too large, then everything that I said would hold. And if the entropy is very large, then some things that I said need to be changed.
So, well, let's see. What in case of if you have some region other than black hole, you can which is invisible and to some observer, then black hole can be regarded as a mixed state, right?
Well, if it is absolutely invisible, so if it is behind the RT surface, if there is an RT surface or a quantum extremal surface, and there is some region behind that, then the black hole will be in a mixed state. So the black hole is in a mixed state if there is a non-trivial, let's say, quantum extremal surface, or well, if there is some, well, I guess you just compute the quantum entropy. If the quantum entropy is non-zero, then it will be in a mixed state.
Yeah.
So the black hole that we were discussing was in a mixed state. Most of the evolution, when it started emitting Hawking radiation, it went onto a mixed state. Sometimes the mixed state was appearing because we had some matter entropy, and sometimes also, in addition, we had a big quantum extremal surface, or non-trivial quantum extremal surface. So those two things contribute to the entropy.
I see. Thank you.
Andy, you have a final question?
Oh, me?
Yeah, you have your hand up still. Are you finished?
Yeah. I want to comment on Sasha and Emil. So we started with a theory which was probably in the swampland, just, n-free bosons with a flavor symmetry in 2 dimensions coupled to linear dilaton gravity. And in that theory, you can make black holes and you can use the QES prescription. And it shows the page curve and the information coming back out. On the other hand, you can actually explicitly compute on Scribe Plus what the entanglement entropy is as a function of time from the local measurements up there, and they're not the same. So my view is that the hope would be that in a consistent theory, which is not in the swampland, these things will agree.
Well, I think if you restrict to computations of entropy, these formulas and RT formulas give results consistent with unitarity. I think the problems you discuss have to do with exactly the explicit presentation of the state and what the actual state is.
We get an exact formula for the state at large n, and the entropy, the entanglement entropy is of a section of Scribe Plus, which is what a physical detector would measure,
right.
is unambiguously defined and not equal to the QES prescription.
That is true. So the entropy of that state semi-classically is not equal to the entropy given by the quantum extremal surface description. But as I was saying in the beginning, the computation of the state, it's approximate, and it's 2 orders in 1/n. So n was the entropy in your case, and so you need non-perturbative corrections in n to actually get the actual state exactly, right? Because you need access to the macro states. So
at large n, because it's a flavor symmetry,
Yes.
subleading corrections can't change that.
Can change what? I mean, I
They
think
can't change the leading form. They can only change the entropy at subleading order of n.
well,
What?
no, I don't think so. So in fact, well, if you compute the entropy with using the gravitational path integral, you see that there are corrections. Now, I view that as
to use the gravitational path integral. We have an exact solution of the theory at large n.
yes, but that solution neglects topology change. And when we include the idea is that when we include the effects of topology change, then we can fix this problem, this entropy problem. And I take this as an indication that there could be small corrections in the state, so very individually small corrections to the state that would correct the state so that it has the new correct entropy, the one given by the RT formula.
Okay, we just have 7 minutes until the next talk. So it's an animated discussion, and I think the talk was great. So let's all thank Juan again for his excellent talk. And we'll take 6 minutes and be back. And of course, everybody is all invited next year to our next strings meeting in Brazil.
Thank you, Nathan. Hi, Anastasia.
Jeff, can you hear me?
Yes.
Anastasia.
Hi, Surat. How are you?
I'm fine, thank you.
Surat.
Great conference, Jeff. Great.
Thanks.
Should I start sharing my screen, Anastasia?
Yes, please.
Oh, I think I have to wait till Juan stops sharing.
Oh, sorry.
Oh, sorry. You're.
No, Jeff, could you please make Surat co-host?
I'm doing it now.
And
yeah, just one more request. I have an iPad just for questions. I won't use it, but could you make that a co-host as well? It's called Suvrat iPad or Suvrat Raju
Sure.
iPad. Can you hear me clearly, Anastasia?
Yes.
Okay, so both you and your iPad are co-hosts.
Okay, great. So this will stop the other person's screen sharing.
Yeah, that's just Nathan advertising. Okay. Great. Thank you, Nathan.
Okay, great. And you can do that?
Yes.
Great. Okay, great. So we are set. Whenever you say Anastasia.
Surat, you know, it's 30 minutes plus 10 minutes for questions, right?
Right. So you'll give me like a 5-minute warning or?
Well, I prefer that, you know, you keep time, but yes, if you keep on going, I will tell you.
Okay, sure. No, I'll probably be in time. I mean, if I give me a 2-minute warning if you feel I'm
okay, yeah. If I see you, yeah.
Yeah, I have. Yeah, if you see I'm not en route to finishing, you can say no. Give me 2 minutes.
I'll do it. All right, but we have 4 more minutes now, so. Okay, Subrat, should we start?
Sure, yeah.
Okay. Hello, everybody. Welcome back. And now we're happy to have Subrat Raju from ICTS, who is going to tell us about holographic null infinity and the information paradox in flat space. Subrat.
Okay, thank you very much, Anastasia. Thank you very much also to the organizers for organizing this wonderful conference. I'm sad that I wasn't able to visit South Africa for the conference, but I hope I get a chance to visit soon. Before I start my talk, let me just acknowledge my collaborators. So I'm going to speak about work that's done in collaboration with Pushkal, Chandramouli, Bidisha and Siddharth at ICTS, Olga and Kyriakos at ICTP, and Alok at the Chennai Mathematical Institute. I'm largely going to talk about this paper we wrote a few months ago with Alok, Siddharth, and Pushkal, but I'll also describe some work in progress that should be out soon with Chandramouli, Olga, and Kyriakos. So before I start my talk, let me just try and explain what the main idea that I'd like to convey is. So we've understood AdS-CFT now for many years. And when we say that quantum gravity in anti-de Sitter space stores information holographically, we are referring to a very special property. And that very special property is as follows. If you consider some Cauchy slice that runs through AdS, like this slice on the right-hand side, this slice might have some excitations or some features that live very close to the middle of AdS. But the statement that the theory is holographic is a statement that you can immediately read off the form of this bulk excitation from this little red region near the boundary without waiting for the signal to emerge at late times. You could wait for the signal to emerge at late times if you so wished, but holography tells you that you can also read off the signal just at the same time. So the main announcement that I would like to make in this talk is that we have been able to establish a similar result for gravitational theories in 4-dimensional asymptotically flat spacetimes. And the result is as follows. If you consider a theory with massless particles, one might have thought naively that the information about the massless particle is spread out all over future null infinity, and that is indeed the case in a local quantum field theory. What I'll try and describe is that in a theory of gravity, this information can be obtained just from the past boundary of future null infinity, which is the region marked in red on top. There is an analogous statement for past null infinity, in which case the information can be obtained from its future boundary. But to avoid duplication, I'll only make statements for future null infinity in this talk, and there's always an analogous statement for past null infinity. So that's the main result that I would like to convey. Now, there is some difference with the situation in anti-de Sitter space in that null infinity, even in a gravitational theory, I'd like to explain, stores information more intricately than the boundary of anti-de Sitter space. So one of the points I would like to describe is that unlike anti-de Sitter space, we tend to lose information as you move along the boundary. And what that means is that if you look at the information that's available on this magenta cut or this purple cut, it's a subset of the information that's available on the red cut. And the general rule is that the information on later cuts is a subset of the information on earlier cuts. Okay, now one of the points I'd like to emphasize is that even though I'll talk about operator algebras and some technical aspects in my talk, this is really not an abstract result. The result I'm describing leads to a very concrete physical protocol for observers near the boundary, for observers who live in this region near the past boundary of future null infinity, to identify the bulk state. So at the end of the previous talk, there was some discussion about what if you had a shock wave that was blue or green and how you would be able to identify that from far away. And I'll try and describe how one could do that in a theory of gravity. I'd also like to explain that this has direct implications for black hole information. In particular, there's been an idea which was also discussed in the previous talk, which was that it may happen often in a theory of gravity that degrees of freedom that look like superficially they're localized on different parts of a nice slice may need to be identified with each other. So this is an idea that was articulated clearly at the time of the debates on the firewall paradox in papers by Kyriakos and me, by Rick and Herman, by Yasunori, and subsequently also by Juan and Lenny, and going on to the more recent discussions on the island proposal. And what I'd like to explain is that this notion I'm describing of how information is stored in null infinity makes it precise and also suggests a physical origin to this idea. And the way it does that is that if you think of a black hole spacetime and think of this nice slice, you might have thought that the information that lives in these green dots is the information that emerges on later parts of null infinity, which is this green segment. But if it is true, as I claimed, that the information on the green segment is also available on this red segment, that's a precise version of the statement that the information in the green dots or degrees of freedom in the green dots need to be identified with some complicated set of degrees of freedom in the red dots. The perspective I'll describe will be a direct Lorentzian perspective, so it's complementary to the perspective that we heard about previously, in that I will not make reference to a Euclidean path integral or even the Ryu-Takanagi formula. But there is also some difference in detail with the story I'll describe and the story that we discussed previously. One of the points, the physical points I would like to emphasize is that the results I'm describing suggest that in a sense, if you make complicated enough measurements, then the information about the black hole is always available outside the black hole, even before the page time. And this has a quantitative implication. It suggests that the naive page curve that we draw is not necessarily the correct curve for the von Neumann entropy of the state on Scri+, as I will describe. Okay, let me say just a few words about the philosophy of this talk. The way I'm going to go about constructing my arguments is that I will observe and make some analysis of some interesting properties of the semi-classical theory of gravity. And then I would like to make some precise assumptions about the full ultraviolet theory. And the assumptions will be that the ultraviolet theory shares, in a sense that I will make precise, some specific low energy properties of the semi-classical theory. And then if we accept these assumptions, this will allow us to extrapolate the results that we have for holographic information and gravity to the full UV theory. Of course, I want to clarify that and just the obvious point that there is no claim in this talk that semi-classical gravity is a complete theory by itself. But the claim is that the semi-classical theory does hold important lessons about how quantum information is stored holographically in quantum gravity. And those are lessons that we can already learn about without looking at the full ultraviolet theory. So let me now go on to some of the more and try and describe these results a little more precisely and the arguments that go into them. So I'd like to consider four-dimensional asymptotically flat spacetimes. And this is the standard form of such a spacetime in Bondi gauge. So there's a leading metric, which is just Minkowski space, and then there are subleading corrections to the metric. There could be dynamical fields, other massless dynamical fields, and then we'll use the standard boundary conditions, standard fall-off conditions for these massless fields. I am going to be specifically interested in the algebra of observables on parts of null infinity. So in particular, I would like to look at the algebra of observables between a cut u and u plus epsilon, where u is this null coordinate that parameterizes null infinity. And this algebra includes, of course, observables, which are components of the metric, such as what's called the Bondi news and the Bondi mass. But more importantly, it will also include all possible products and linear combinations of these observables, which is what we usually do. We have some elementary observables, and then we allow the observer to also observe combinations of these observables. There is a special algebra that will play an important role in my talk. And that algebra is what I'll call A minus infinity. That's the algebra that I've marked here near this little red region. And it's the algebra near u goes to minus infinity of the theory. Okay, let me just review a few well-known features about the Hilbert space. We've known and we've analyzed a lot in recent years that the vacuum of these theories in four-dimensional spacetimes is infinitely degenerate. In fact, the vacuum, the various vacua are labeled by their eigenvalues under what are called the super translation charges. And then if you tell me the eigenvalues under all the super translation charges, that fixes the vacuum. But then on top of each vacuum, we can of course build a Fock space, which is the standard out space that we discuss. And the way you build this Fock space is just by acting with the various dynamical fields in the theory on this vacuum, and that lets you build up a Fock space. And then the full Hilbert space of massless particles is what you get by taking the direct sum of all of these Fock spaces that are built in these different vacua. And all the statements that I make in this talk will be confined to the space of massless particles, which excludes massive excitations, although I think it should be possible to include them, but I'm not going to include them in this talk. Okay, so now I would like to describe the first result, and the first result is as follows. I'd like to claim that if you look at any two distinct states in this direct sum of infinite Fock spaces, which is the Hilbert space of massless particles, then any two distinct states in this Hilbert space can be distinguished just by observables in A minus infinity. And that's a precise version of the statement that the information is always available near the past boundary of future null infinity. Okay, so I'm not going to go through the proof in great detail, but I'll just try and sketch the various steps that lead to this kind of a result. The first step is a technical observation. It is the fact that if we assume that in the full theory, the Hamiltonian is positive, then that gives us a familiar property of the theory. And that familiar property is that if you look at one of these subspaces that's built on top of a particular soft vacuum, then you can get any state in this subspace by acting with an operator from A minus infinity on the vacuum on which this subspace is built. So this is like the familiar map that we have between states and operators in quantum field theory, and it will hold in this case as well, and you can prove it more formally if you're allowed to use the positivity of the full Hamiltonian. I'd just like to make a note of caution here because sometimes this sounds like a confusing statement if you're not familiar with it, but this is an intermediate technical step, and in fact, it does not even require dynamical gravity, and this step, I think this is a true and important statement, but it is not the main point of the argument that I would like to make. The main point of the argument, the main physical point, I think that's relevant for this result, is the fact that both the Hamiltonian and the super translation charges are elements of this algebra A minus infinity because they can both be measured from the past boundary of future null infinity. Now, there is a physical implication of the statement. And the physical implication of the statement is as follows. Consider what happens if you were to measure a super translation charge in a given state psi. Then the usual rules of quantum mechanics tell you that one doesn't get a definite answer, but one could get an answer between S and S plus delta S with a probability that's proportional to the expectation value of some projector in this state psi. So these projectors which project onto specific eigenvalues of these super translation charges, and also the projector onto the manifold of vacua, which I'll denote by P omega, which is what tells you the probability that if you were to measure the energy, you would get 0. These projectors are physically observables and they are part of the algebra A minus infinity. In fact, if you were to make a measurement, this is what you would really observe. Okay. Now, there is a surprising consequence of this. And the surprising consequence of this is as follows. What this tells you is that if you had a set of identically prepared systems and you were to use the standard measure and discard procedure that one uses in quantum mechanics, where you make a measurement and you discard a system if the measurement is not what you want, you can use this to select a specific soft vacuum from near the past boundary of future null infinity. And mathematically, that's the statement that this operator, which is bra S ket S, is also an element of this algebra A minus infinity. Now, I'd like to emphasize that this is the key physical point. The fact that one can select a specific vacuum using observables on the boundary of the space-time is a very unique feature of gravity. It is not true in any other theory. Even though there are non-gravitational gauge theories which have boundary charges, you can never use those boundary charges to select a specific state, which is something that one can do in gravity. Now, once you accept this, which I think is a result that can be established very clearly, then using other operators that live in A minus infinity, which have a given supertranslation charges, you can also construct these transition elements that take you, that look like ket S bra S prime that cause transitions between these different vacua. And these are also elements of A minus infinity. And they're just obtained by taking these projectors and multiplying them with some operators that have supertranslation charges. Okay, now this is actually sufficient already to sketch how the argument for the result goes. And the argument for the result now goes as follows. Consider any operator that maps the space of massless particles back to itself. Of course, by the usual rules of quantum mechanics, you can expand this operator in a complete basis. In this complete basis, you have a sum over these different soft sectors, and then you have a sum over states in those given soft sectors. But now, by the first technical result I mentioned, you can generate all these excited states in a given soft sector by acting with an element of A minus infinity on the given soft vacuum. And then by the important property of gravity that I mentioned, which is that this operator in the middle is an element of A minus infinity, you see that on the third and last line, you just have a linear combination of a product of three operators that live in A minus infinity. And this is manifestly also in A minus infinity because the algebra is closed under linear combinations and products. And so this tells you that any operator from the space of massless particles back to itself can be approximated arbitrarily well by an operator near the pass boundary of future null infinity. Okay, now this was an argument in the semi-classical theory, but in fact you can convert this to an argument or a property of the full theory of quantum gravity if you make some very reasonable assumptions. And the reasonable assumptions that one needs to make are that the vacua in the full theory are still labeled by operators near the pass boundary of future null infinity, and operators that map the space of vacua back to itself are also contained in this algebra A minus infinity. Now, because these are only low energy properties, there are only properties of the vacuum of the theory or the space of vacua of the theory, it's reasonable to assume that the full ultraviolet theory will share these properties with the semi-classical theory. And if you assume this, then the previous argument that I made goes through, and you can argue that even in a full complete string theory, if you could construct one in four-dimensional asymptotically flat spacetimes, all information about massless particles would be available near I plus minus. Okay, if one makes stronger assumptions about the UV theory, it's possible to prove a slightly stronger result, which leads to the picture that I mentioned about how null infinity stores information slightly more intricately than ADS. And that is, as I said, the statement that all the information that's accessible through this algebra at A of U1, which is through an observer who makes observations near this cut at U1, can also be accessed by an observer at an earlier cut who makes observations at this cut U2. The way one goes about showing this argument is by noticing that in the semi-classical theory, it's possible to derive some commutators between the Bondi mass and other dynamical fields in the theory. I won't go into the details of these commutators, but in fact, these asymptotic commutators, and when they were first derived, can be derived in the full nonlinear theory of general relativity. And the reason that works, even though the theory of general relativity has such a complicated symplectic form, is because these specific commutators depend only on the weak field limit. So now if you assume that these commutators carry over to the full UV theory, this is not really a low energy assumption. It's an assumption about how certain commutators behave in a weak field limit. But if you were to make this assumption, then you would find that the Bondi mass acts like a Hamiltonian, but it acts like a Hamiltonian for operators at larger values of U and not like a Hamiltonian for operators at previous values of U. And therefore, you can use the Bondi mass to evolve information from the algebra at U2 to the algebra at U1 and get all observables there, but you cannot do the converse. And therefore, unlike ADS, you tend to lose information as you move up on future null infinity. Now, this is just a recap of the results I described and the assumptions that I needed to make. As I said, if you make two very reasonable assumptions about the vacua of the theory and the low energy properties of the theory, which are that the vacua are identifiable by charges near the pass boundary of null infinity, and that operators near this pass boundary can map one vacuum to any other vacuum, that leads you to the conclusion that all information about massless particles is available near the pass boundary of future null infinity. If you make a stronger assumption about commutators from the semi-classical theory, which depend on the weak field limit carrying over to the full theory, that leads to the conclusion that information on any cut of scribe plus is also available on any earlier cut. This result 2 is stronger than result 1, but it also relies on stronger assumptions. Okay, so perhaps some of you are thinking at this point that this is some abstract argument about operator algebras, but what does it mean physically? So I think that this argument I described actually has a very concrete physical manifestation. It's related to the question that Andy asked at the end of the previous talk, and it's as follows. Consider that we have some astrophysicists, these are my little astrophysicists, who live near this pass boundary of future null infinity. And then somebody sets off a bomb which creates a shock wave somewhere in the middle of the space-time. And then the shock wave propagates and is going to come and hit null infinity at a later time. The shock wave has a profile. I could also consider different fields and flavors, but for now it's just a gravitational shock wave that has a profile that's given by this function f. And the challenge for the astrophysicists is that working only near this cut at I plus minus, they need to figure out the profile of the shock wave. So they are not allowed to go up or wait for the shock wave to arrive at null infinity, but they need to figure out the shock wave just by making observations here. So it turns out that this is something that can be done concretely. And one way to do this is to measure the correlations of the Bondi mass with other dynamical fields near the pass boundary of future null infinity. I want to emphasize that this is not just measuring the energy, not just measuring the Hamiltonian, but measuring the quantum correlations of the Hamiltonian with other dynamical fields. Because this is a two-point function, it's just a two-point function of simple operators, one can compute it reliably in perturbation theory, and one finds some answer, one finds this answer. Now, the important point about this answer is that if you know this answer, for u being in this region minus infinity to minus 1 over epsilon, which is in this little red region, you can completely reconstruct this profile function f. This is something that you can demonstrate more formally using analyticity arguments. But if you just look at this expression, you see that if you knew this function, this right-hand side for large u, you could do a series expansion in powers of x by u. And this series expansion would give you all the moments of this function f, which would be sufficient to reconstruct this function f. So this gives you, and one can generalize this protocol, this tells you in a very concrete physical sense how observers near the pass boundary of null infinity can use these gravitational effects to obtain information about the bulk state. It's very important that such a trick cannot work without gravity. It doesn't work in local quantum field theories, and it also does not work in non-gravitational gauge theories. In a non-gravitational gauge theory, of course, you have the possibility of measuring the charge, which might be like the Hamiltonian, but non-gravitational gauge theories also contain exactly local gauge invariant operators, which just exactly commute with all elements of all operators that these astrophysicists can measure. So for instance, if you had a non-gravitational gauge theory and you didn't allow these astrophysicists to use gravitational effects, you could completely defeat them just by taking the vacuum and considering another state, which is a vacuum acted with e to the I f squared on 0, and there would be no way they could distinguish these two states without using gravity. It's also important that these effects I described, as I said, are not true in classical gravity, but they rely on measuring quantum correlations, and quantum correlations which rely also on gravitational effects. Okay, let me spend the last 5 minutes that I have in making contact with some of the previous talks, and I'm sure some of the subsequent talks. So one interesting result one can get by looking at these kinds of results about information is about the page curve. Now, there is a common way to define the page curve, which is the way it's usually defined, or to define the von Neumann entropy of segments of null infinity, and that is done as follows. Consider some segment of null infinity that goes all the way from its pass boundary to some finite cutoff at u, which is marked by this thick red segment. Then there is some algebra of observables on this thick red segment. And then one looks for that element of the algebra, which you call rho, which when traced with other elements of the algebra, gives you the correct expectation value of those other elements of the algebra in that state. This is the way one usually defines the density matrix associated with a region in quantum field theories. But now there is something special that happens about gravitational theories when this region is part of null infinity. And that is that by the result I just described, all elements of this bigger algebra, you can always find a representative that approximates them arbitrarily well already in A minus infinity. Therefore, you can always choose this density matrix rho of u, which is describing the state on this segment of null infinity, to just be some fixed sigma, which is an element of this algebra at minus infinity. And this tells you that if you define the von Neumann entropy, or if you were to define something more careful like the relative entropy, this is just independent of u and doesn't change as you go up. So in particular, it would suggest that the page curve for a system of this kind, which is the black hole that evaporates, and when you look at the von Neumann entropy of this segment, is just a constant. The reason this constant is not zero in this case is because I've ignored the effect of massive particles. But the fact that the naive page curve fails, it should not be a surprise, because the page curve is based on known to be incorrect assumptions about the factorization of the Hilbert space. If one goes back and looks at the derivation that Page had for the entropy of subsystems, that explicitly relies on the factorization of the Hilbert space. And in flat space, even the algebra on Scri plus does not factorize because there is a remnant of the constraints of gravity that remains as you go on Scri plus. Now, I'd like to emphasize, and this is an important point, that it may be the case that perhaps an appropriate restriction of the algebra by throwing out some observables will mathematically yield the page curve. But the physically important point that I would like to emphasize is that the information is always available outside the black hole if you allow the person outside to make all possible measurements, even before the page time. You might also think that you've never seen this curve before, but actually you have. And it's a very familiar curve. And it's the curve that appears if one considers the entropy of small black holes forming and evaporating in ADS-CFT. So this is a cartoon of a small black hole that started from dust and collapsed to a black hole and then evaporated to Hawking radiation. And if one looks at the fine-grained entropy of the bulk region near the boundary, which is this red region or this magenta region or this green region, this fine-grained entropy is always zero, which is reflecting the fact that one can measure all operators by going close enough to the boundary and making arbitrarily complicated measurements. So I'd like to propose that the evaporation of black holes in flat space looks similar to the evaporation of small black holes in ADS. I want to emphasize that this is actually not inconsistent with the recent work on the derivation of the page curve. And that's because the recent work, which is very nice, but always considers gravity coupled to a non-gravitational bath. So schematically, the picture looks like you have a gravitational system and then you couple it to a bath. And by construction in this setup, the Hilbert space factorizes. And when the Hilbert space factorizes, it is guaranteed that both SBH and the entropy of the bath will follow a page curve. But the physical point I'd like to emphasize is that it's important to make a distinction between the question of black holes and when you've coupled them to a region where there is just gravity just switches off beyond some point, and when you consider black holes, which are coupled to a region where gravity is weak beyond some point. And the reason for this distinction is that we have learned, and I think the island story also re-emphasizes, that weak effects in gravity can often conspire to give radically different answers from local theories. And so I think we need to distinguish these two setups. And I think it is the case that in systems where gravity is non-dynamical beyond some region, the information emerges after the page time. But for more realistic black holes where gravity is dynamical throughout, I think the information is always outside.
Sorry,
Okay.
Subrat, you have 1 minute.
I'm done. Yeah, I'm done. So let me just recap the results. So I argued the main result I wanted to present was that all information on future null infinity is actually present near its past boundary. And I think this is a precise version of the claim that degrees of freedom on parts of a nice slice must be identified. I think this has a physical lesson, and it tells us that an outside observer with sufficiently complicated measurements can always determine the state of even a young black hole. This is not inconsistent with recent derivations of the page curve, but it does suggest that these derivations are inapplicable when gravity is everywhere dynamical. Okay, so I'm done. Thank you very much.
Great. Let's thank Surat for a very nice talk. And now we have 10 minutes for questions. Please raise your hand. Ed Whitten, please.
Sorry, I was muted. When you discussed the page curve, you considered the state to the past of a cut of null infinity. Suppose instead you consider the state to the future of that cut.
Yes. Then I think you might actually get the page curve. It depends on how much entanglement there is between the soft and the hard degrees of freedom. This is something, but I think you might get the page curve. But the physical interpretation of that, its question is, what if instead of this state that I've drawn here, you were to consider the complement of this region? So you were to consider how much information is available from the future to this region. And then I think you would get a more interesting curve and you might get the page curve. But the physical interpretation of that is slightly different. The physical interpretation of that is when you start out here, you have all information. And as you go up, it's like you're going inside, inwards, inwards, inwards. And of course, as you go inwards, you tend to lose the information that's outside. And therefore, you get some curve. So, but I should emphasize that even this is a result that I think relies on how much entanglement there is between soft and hard degrees of freedom. And as I said, the main physical point I wanted to emphasize is that it is true that an observer here who makes measurements here can always determine the state of a young black hole. And I agree with you that there are other definitions you could make that might mathematically give you the page curve.
Okay, next, Raphael.
Hi, yeah, thanks for the talk. I just wanted to comment that Aaron Wall and my students Sven Chandrasekaran and Ilan Halpern showed a couple of years ago that the bonding mass is actually not in the algebra of observables of a finite interval of Scri plus. That follows both generally from entropy bounds or statements such as the quantum null energy condition. And it can also be seen operationally from the fact that quantum fluctuations become uncontrolled when you limit the amount of retarded time for the measurement, but you take the radius at which it happens to infinity, which is the limit that you would need to end up with a finite interval. Physically, it's simply the statement that you could have superpositions, for example, of different Schwarzschild geometries, which would result in a non-zero entropy if you could actually measure the bonding mass at zero energy, since you wouldn't have any gravitational radiation arriving at that interval. Or put a different way, you could communicate between distant observers at zero cost and energy by asserting that they can measure the bonding mass in finite time at Scri plus.
So thank you. I just want to emphasize that, I mean, we can discuss this. I know we've discussed this in the past. But in fact, this point is not relevant to the central result that I want to describe. And the reason for that is that, if you look at the Hamiltonian or the super translation charges, which played a central role in my description, those actually live from u equal to minus infinity to u equal to minus 1 over epsilon. So you have an infinite amount in some sense of retarded time to measure them, even though that's very close to the pass boundary of future null infinity. So as we described in our paper, in Appendix B of our paper, you could just, there's a very physical procedure by means of which you could measure the Hamiltonian, which doesn't even run into the problems that you have discussed. I think it should also be possible to measure the bonding mass, which is a question of measuring something up here. But for the central physical result I wanted to mention, which is the Hamiltonian, you actually already have an infinite amount of retarded time because you have all this infinite amount of time near the pass boundary. And so I think this obstruction doesn't arise.
Okay. Next, Andy Strominger.
Yeah, you talked a lot about the super translation charge and diagonalizing the super translation charge, but there's a whole infinite tower of more charges from the Virasoro symmetry, from the sub-subleading self-graviton symmetry, and so on, which one might expect to play an important role in this kind of analysis. Have you thought about them at all, or what?
Yeah. I think the important question is whether the vacua are labeled by those charges or not. So I think our current understanding is that the vacua are labeled by super translation charges. Now, I should say that actually...
I wouldn't agree with that. The vacuum can certainly have angular momentum, for example.
Yeah, let me just make a statement that I think you would agree with. What is really important for my result is that the vacua are labeled by charges that are defined near scri plus minus. So provided the vacua are labeled by observables near the past boundary of future null infinity, the argument I made would go through. It doesn't actually rely on the fact that the vacua are labeled only by the super translation charges. So I think you would agree if I'm not correct, if I'm not wrong, that all these other charges are can always be defined near the past boundary of future null infinity. And if that is the case, then I think this argument would go through. It would require some more bells and whistles, but I think it would still go through.
But maybe also, that's what I understood, but maybe also the specific structure of them would be useful in understanding how the readout worked.
Yeah, I agree with that, yeah.
All right, next, Henry Maxfield.
Yeah, thanks for the talk. So I was wondering, you seem to be suggesting that this page curve result relies on the radiation being in somewhere where gravity is completely decoupled and turned off. So you can play games even in ADS, for example. You can put a boundary geometry, which is maybe a small sphere where you create a pure state black hole, and then some large sphere, and you just join them with some narrow neck that just allows the Hawking radiation to slowly leak out.
Yes.
It's just something to give you a clean separation between the black hole system and the radiation system. So that seems to be the more important thing. I was wondering if you could comment on that in relation to your...
No, I agree with that. In fact, when we discussed this first, many years ago, our proposal was that one should actually use the so-called plasma ball that Shiraz Minwala and Ofer Aharoni and Toby Wiseman discussed, which is what's called a localized, it's a localized black hole in a planar ADS-CFT correspondence. And that black hole is localized in some transverse directions in the boundary theory. And then there's a clean separation between that region of the boundary theory and its complement. And because the Hilbert space of the boundary theory factorizes, one should be able to derive a page curve for that as well. However, in the situation of a black hole in flat space, if you're surrounding it in all ways, then I think that's not what happens. And it's also not what happens if you just take a small black hole, which is not, you don't have localization in transverse directions, but a small black hole is just living near the center of ADS. So I agree with you completely that there are situations just in a single CFT where you could get this. And I think the plasma ball is the cleanest system where you could see this.
Yeah, I think we only have time for one more question. Okay, Daniel Harlow. Daniel Harlow. Okay, is he here? Okay, then Andreas Karch.
Thank you. Maybe I have a direct follow-up to what just was said last, since
sorry.
This feature that once you couple to some external Bass, we recently demonstrated that will always tell you that the graviton gets a mass. So my understanding is that maybe this feature that you're finding, that you silence when you have gravity that goes all the way out to infinity, and you say you get the regular page curve only when you one way or another couple to an external mass. Can this be related to the fact that you do get a graviton mass the moment you couple to an external Bass, and you wouldn't get the graviton mass if you really have gravity living all the way to infinity? Is this, you think this is related? I guess that's what I'm asking.
Yeah, thank you. This was discussed earlier, but I'm really sorry. I don't have something very sharp to say about this question of whether the graviton develops a mass if you couple it to an external system. So I don't want to say something.
I think that's a fact. That's just a fact. If you couple to an external system, the stress tensor is no longer conserved and the graviton gets a mass. I think that's undisputable. That this has something to do.
No, I agree with that. I'm not disputing it. I'm just saying that I don't have something intelligent to say about the implications of that observation for the story.
Okay, thank you. So unfortunately, in view of time, we really have to move to the next speaker. So let's thank Surat again for the beautiful talk. And now we're going to move to the next speaker. So we're very happy to have Andy Strominger from Harvard, who is going to tell us about celestial holography. Andy?
Okay. let's see. Okay, share screen.
Share screen, yeah.
And does that look good?
Perfect.
Looks perfect. Okay. And what time how much time do I have now? There was so much discussion.
All right. No. I'm keeping it very on time. So you have 30 minutes and then 10 minutes for questions.
30 minutes and then 10 minutes for questions. Okay. So I'm going to talk about an approach to holography in flat space called celestial holography. Okay, what's happened here? Sorry. What? Oh. Okay, there we go. So the black hole area entropy law, that the entropy of a black hole is the area horizon over 4 times Newton's constant, is the primeval holographic relationship. It says that the number of degrees of freedom of the black hole scales not like the volume of the black hole, but the boundary of the volume of the black hole. So understanding this formula for black holes with near horizon anti-de Sitter regions, in which we've had a spectacular success over the decades, went hand in hand with understanding ADS-CFT holography in anti-de Sitter space. And so one might guess that understanding black holes in flat space, where the information paradox takes its most striking form. You start out with a pure state, you make a black hole, and all the energy went to the maximally mixed state, will go hand in hand with understanding holography for quantum gravity in asymptotically flat spaces. For example, this island rule entropy, one might hope in the flat space context to derive it from some holographic formulation of quantum gravity in flat space in the same way that one derived the island rule entropy formula in ADS space. Now, if you want to find a holographic dual, one of the first things that you better do is figure out what all the symmetries of the problem are, because the holographic dual and its partners better have the same symmetry. Now, thanks to the subleading soft graviton theorem and the sub-subleading soft graviton theorem and all the new subleading theorems we've learned about in the last few years, we now have a better picture of this. And I think the picture of the nice way to think about this was drawn almost 20 years ago by De Boer and Solodukin. And what they did was they said, hey, let's just write flat space as a non-compact compactification. So the compact direction is usually noted tau, it goes this way, over a sequence of anti-de Sitter, Euclidean anti-de Sitter up here in the future and the past, and a de Sitter region in the space-like region. Let's write it as a non-compact compactification, decompose the wave equation that way. And then we've got wonderful three-dimensional anti-de Sitter space whose holography we understand in insane detail. And we can use that to uplift to a holographic description of Minkowski space. And the hologram should live at the boundary. And the boundary we call the celestial sphere. Now, the problem is there's two boundaries. There's one in the future and one in the past. But one of the things that we've learned in the last few years through the soft theorem is that the conformal structure on these boundaries, this is supposed to be a lock and chain, are locked together so we can view it as one sphere. There's one conformal structure, and there's a canonical way to identify, it's actually antipodal, to identify points on the future sphere with the past sphere. And of course, these symmetries, there's a lot of symmetries here, and much more than just the supertranslation symmetries. And they greatly constrain the black hole formation S matrix and will induce correlations between the Hawking radiation and the quantum state of the black hole. And this was partially analyzed in Hawking and Perry with Sasha, other Flanagan and Nichols, Busso and Prati, various people. And also I think there's a lot of resonance here with the talk that Suvrat just gave. So the basic idea is that you start with an S matrix and written in a momentum space basis, and you just simply rewrite it in a conformal basis. In other words, instead of using momentum eigenstates, you use Boost eigenstates. So the conformal group, the global conformal group, is nothing but the Lorentz group. So writing things in Boost eigenstates is just like what we would do in two-dimensional conformal field theory. And due to the subleading soft theorem, which after a long line of manipulations, which I've given many talks on, you learn this thing has also not just a global, but a local conformal symmetry. And so the basic idea is that there should be some kind of holographic duality in which the S matrix in Minkowski space is written as some kind of correlation function on what we call a celestial conformal field theory. And we call it celestial conformal field theory because it has some peculiar properties that are not characteristic of an ordinary conformal field theory. Now, the conformal symmetries are not the only symmetries that act on here. There are the super translations, for example, and they have the peculiar property of relating an operator of dimension delta to an operator of dimension delta 1. So the correlation functions on this theory, it seems like they obey way too many constraints, that there shouldn't be any set of correlation functions which obey all these constraints. But we know that there is, because we can construct them through reverse engineering. So I want to explore here. So, flat space holography, it's kind of like ADS holography, at least in this construction. It's as close to ADS holography as it could be because it uplifts the ADS slices, but there's going to be a lot of differences. And the celestial conformal field theories, they have the same conformal symmetry, but they're different from ordinary conformal field theories. And so we'd like to try to understand what their properties are. And so far, almost all the discussion, of which there's been kind of a slow boil over the last 5-10 years. The conformal fields theory story, maybe it's been going for 3 or 4 years. It's been mostly bottom up. Let's take a field theory that we understand, rewrite it as a conformal field theory. The left-hand side in this duality defines the right-hand side. And it's a little bit like Brown-Hainaut. I mean, ADS really started with Wan's paper, but Brown-Hainaut, it was a top-down from string theory approach, but Brown-Hainaut had a bottom-up approach where they just said, assume an assistant quantum theory of gravity on ADS3. We can see there should be some conformal symmetries. That paper wasn't read very much. Beautiful paper, it should have been, but it wasn't read very much. It could have been used to develop some notion of holography on ADS, which didn't depend so much on the details of string theory. So that's the approach we've been finding. Now, a top-down approach from string theory, that is an intrinsic construction of a conformal field theory, is not ruled out. And in fact, we're saying that the S matrix is computed by a conformal field theory on the two-sphere. Well, that's, of course, what you learn on page 1 in any textbook on string theory. You compute conformal field theory correlation functions on a two-sphere, and you get the string space-time S matrix. So could those somehow be the same two-dimensional conformal field theories? Well, Stieberger and Taylor showed that they are, in fact, in a certain limit where the boost weights get large. And I was also in this regard very taken by Rajesh's talk, in which he talked about the relationship between the conformal field theory on the boundary of ADS and the conformal field theory on the string world sheet, and showed that they were same because of this Luhnen-Matur localization, the localization moduli to the Luhnen-Matur subspace. And there was also Givyan, Kudasov, and Seiberg, who talked about the relationship between current SL2C current algebra on the world sheet uplifting to the Versar algebra of ADS3 in space-time. One might also less ambitiously try to do this for the CHY string in 4 dimensions. And I want to say for those of you out there looking for a hard problem, if somebody gives an intrinsic construction of a conformal field theory that defines a bulk quantum gravity theory in Minkowski space, that is a very major breakthrough. It's a hard problem, but it doesn't seem ruled out that it's possible. Along the way, we encounter many string-like structures, and it kind of suggests that much of what we know about string theory, in this talk, we are only going to use things which are known to be true of all theories in nature, which contain gravity and gauge theory. And nevertheless, we are going to be found that the structure that underlies it all, if you assume of ultraviolet completeness and so on, looks an awful lot like string theory. And this has been a recurring theme. Now, what is the same and what is different about these theories? Well, they both have conformal field theories and ordinary unitary rational, celestial conformal field theories and ordinary unitary rational conformal field theories. There's 2 Versaros, there can be current algebras. The collinear singularities, which have been studied a lot in gauge theory and gravity, are the same thing as OPE singularities in on the world sheet, and we're going to have more to say about that. The representations are different. Ordinary conformal field theory, you usually have discrete highest weight representations. More exotic things are discussed, but that's the usual thing. Here we have a continuous family of complex highest weight representations lying on the unitary principal series. Various things. And the biggest thing is that there are these infinite dimensional symmetries, the super translations, the subleading soft theorem, subleading soft symmetry in gauge theory, the subleading soft theorem in gravity, which we're trying to understand how much power they have in constraining the scattering. Okay. So a lot of cool stuff has happened. There's a beautiful enriched structure, a coherent overarching picture is not there. So I can't give you one. I'd love to. We're sort of groping around, looking for ultimately an overarching picture, I suppose, would come from a top-down construction. Instead, I'm going to just share some tantalizing tidbits of what we've learned. Okay, so what do I mean when I say this conformal basis? Well, usually you would write an amplitude as a function of the moment, and I'm suppressing spin variables and so on, and actually I'm mostly going to talk about massless particles. All of this remains true, and it's beautiful the way it remains true for massive particles and spinning particles, but it's simplest to discuss the massless case. And what you do is you trade the momenta for an energy omega n, the 4 momenta for its energy omega n, and for the point z to which the momentum points, there's an explicit formula for it, to which the momentum points on the celestial sphere. So if you have a null particle, it will with these momenta will end up at this coordinate on the celestial sphere. For a massless particle, it goes to the future hyperboloid, and then we have an interesting integral. Instead of this simple omega integral, we have an integral over the bulk to boundary propagator in H3. But for that reason, we're only going to talk about massless particles. They also have a conformal weight, H and H bar, which depends on their spin and lies on this principal continuous series. And Pistersky and Shao showed that these were a complete basis of orthonormal. So you can go back and forth between this basis and orthonormal. They're a complete basis of renormalizable wave packets. up to these subtleties at 0. Now, lambda is actually, L naught generates a boost, lambda is the boost weight, so lambda is the Rindler energy. So these are closely related, and I'm working with that with Adam Ball and Noah Miller. These are closely related to Rindler modes. Okay, so you take this ordinary momentum space amplitude, you do its Mellin transform, and you're left with a function of z, and these give you operators. These can be thought of, this looks like a correlation function on the sphere, and these operators can be thought of as being labeled by weight hk and hk bar. And that correlation function, that defines the correlation function, which we write in this form as an object on the celestial sphere. So we want to study properties of those correlation functions. So they've been computed in a lot of cases. I won't review that here. One interesting thing I want to say is that in endpoint already at tree level, if you have a bad theory like Einstein gravity, the celestial amplitudes don't exist because the integral of even the tree level interactions overall energies diverges. You need a theory like string theory with some exponentially soft high energy behavior. So that seems like a very nice thing. The moment you say celestial amplitudes, the fact that it has some good UV behavior is baked in, because the theories without, classical theories without good UV behavior don't have a corresponding set of celestial amplitudes. They exist for all theories which are either renormalizable or finite, but not others. In other words, we're not free to discuss a lot of the swampland. Now, I'll be brief here because Andrea gave a beautiful talk on this. So the operators are labeled by their conformal weight, and it's interesting to ask. We know in ordinary conformal theory, amazing things happen when one of the conformal weights goes to 0. You get a concurrent current which generates interesting ward identities. That happens here. It's related to the conformal soft theorem. And in fact, we proved it using UV regulator, as did Andrea and this group, using UV regulators, showing that you get what looks like the standard current algebra ward identity. It should be a QK here, sorry. Standard current algebra ward identity. And this is surprising in the conformal picture because the conformal things involve modes of all energies. So the intuitive argument that you have this soft theorem because the mode is so in energetic space, because the mode is so spread out that it doesn't see the details of the interaction, isn't true there. Still, it's forced on you by some kind of argument having to do with the behavior under boost weights. The celestial stress tensor is also an example of that. Now, super translations are more interesting. For gravity, gravitons have this. Now notice that H minus H bar is always 2. So this is the conformal weight of a graviton on the continuous principal series. And something special happens when lambda goes to 0. And in fact, this operator is holomorphic in correlation functions, but it has the peculiar factor, the word identity tells us that, has the peculiar feature that when it acts on another operator, then it shifts its conformal weight by 1. Now, in fact, one thing I meant to say is that part of the problem in an ordinary conformal field theory is figuring out what the operator content is, depending on how the theory is presented to you. Here we're given that. For every stable particle, which there might be very few, it could be there's only the graviton. In some theories, we know we have at least the graviton and the electron and the photon. There might be very few. completely stable particles. For every such particle, there is a continuous complex spectrum of conformal primaries labeled by H and H bar. So therefore, it makes sense to say that we map from an operator of one weight to another point in that same spectrum. That wouldn't make sense in the discrete series, for example. Now, how does this constrain scattering amplitudes? So this is a beautiful story which we just published at the end of last year. How does this affect, operator product expansions, which are the same thing as collinear singularities? So a lot of work has gone into computing these, but it turns out that they can be computed very simply using the symmetries. So just from dimensional analysis, we know that if we take two gluons of weight H1 and H2 of positive helicity, the coefficient of the third positive helicity gluon has a 1 over Z1 minus Z2 times some arbitrary function of the weights. And what we're going to show is that all the symmetries we know completely fix that function. So translation invariance, just commuting both sides with translation, shows that these weights obey a recursion relation where you shift both of the two arguments by a half. Now there's something else called the subleading soft symmetry, which was proved by Francis Lowe and other people in the late 50s. And that subleading soft symmetry also has a global piece, or also a piece which concentrates near the two operators, and it gives you this recursion relation, which relates these weights. Now it's known that together with some boundary condition in infinity, that these two recursion relations are exactly what is needed with exactly these factors to completely fix the form of the 3-point OEE function, OPE function, and that is fixed to be just the beta function. And that agrees with more tedious direct calculation of the Mellon transform of the collinear singularities produced in momentum space. And in fact, all the leading graviton-gluon OPE collinear singularities, and that most interestingly includes the subleading soft symmetry, which turns a graviton into a gluon and vice versa, are so determined by the symmetry. How far we can go with this to get all the subleading OPEs and so on is yet to be seen, but it clearly is imposing a big constraint on the theory. So finally, I want to mention a paper that is to appear with Nima and Monica Pate, who's a junior fellow, and Honora Clario, who sadly is leaving us for Perimeter, and which hopefully will appear soon. And there we sort of combine the ideas from the Amplitudes program and from what we're doing. They're clearly very close and asking many similar questions. We try to look at the analytic structure, and also we learned some very interesting thing about infrared divergences for these celestial amplitudes. So first of all, we want to assume what most people believe to be true, maybe it's even proven somewhere, that in quantum gravity at very high S, that all amplitudes die exponentially. Now, this is due to the fact that there are exponentially, because at high amplitude, you can make a black hole with entropy S, and therefore there are exponentially many states that contribute to the final cross-section. So every exclusive amplitude should be exponentially small. Near S equals 0, we can expand this amplitude in terms of some functions of Z. Here, we're just at tree level. We'll do quantum theory on the next page. And these are coefficients in the low energy Wilsonian effective Lagrangian. And they obey very interesting positivity constraints, which have been shown in this work on the EFT hedron. by Arkhani, Hamid, Huang, and Huang. Now, the celestial amplitude, which is the Mellon amplitude of that, S is the square of omega, so I can integrate over S if I take care of the factors of 2. You can integrate over poles or log cuts. The only place you can get a divergence, assuming the exponential softness, is at the origin. And so that tells you that this, this object, the only divergence, this object is meromorphic in the delta plane, except for poles at tree level, simple poles at even negative integers. So the problem of studying the analytic structure of scattering amplitudes is in a new and apparently very simple form. We just have poles regularly spaced, regularly double integer spaced on the negative axis, and moreover, there are constraints among those poles. What happens to go when we go to the quantum theory? And here again, I want to stress, we're not assuming n equals 4. This is true of any amplitude in any consistent, fully consistent quantum theory of gravity. So the ultraviolet behavior still should be exponentially suppressed, and divergences in A tilde all occur only at the IR. They're still meromorphic, though now we can get higher order poles from logs. Now, infrared divergences with logs appear now in exclusive amplitudes. And of course, this is a big bugaboo in ordinary quantum field theory because you have to introduce a regulator and in order just to define the amplitudes. So now let's just do but the form of these logs is controlled by the soft theorem. And let me do QED, though the story for gravity is even prettier, but longer to write down. There we find that all the infrared divergences are absorbed into a prefactor, where the prefactor involves the cusp anomalous dimension and the log of the ultraviolet cutoff multiplied by, well, the Wilsonian cutoff divided by the ultraviolet cutoff. Now, if you transform this to the celestial sphere, now it's not at all obvious that the Mellon transform of a single object, a product of two objects in momentum space, is the product of two Mellon transforms. But it is, except that you must renormalize the dimension of the, so it transform is the product of two transform, and one piece is an infrared safe hard piece, and the hard piece involves only a shift in the boost weight, an ultraviolet divergence shift, but it can be absorbed into the shift or the boost weight of the hard particle. And the soft particle is actually of the form of a current algebra correlator on the celestial sphere with level gamma. And this is a very standard thing to see in conformal field theory. Whenever you have a current algebra, the correlation functions divide into two pieces. Okay, so first of all, it's very nice that we can clearly extract the infrared safe information in this context. But even nicer is that A hard is nothing but the infrared safe scattering amplitudes with Faddeev-Coolidge dressings in their unique conformal primary form. Now, one of the things that bothered people about Faddeev-Coolidge dressings is that they involve an arbitrary function of the momentum, and so there are infinitely many of them, and they form an overcomplete state. That does not happen in the conformal basis. Conformal basis conformal invariance allows only a unique function. That function would not have been considered by Faddeev and Coolidge because pieces of it, it's not an energy eigenstate, and pieces of it have infinite energy, as do all conformal basis states. So Faddeev-Coolidge would have thrown that out by putting some arbitrary cutoff at high energies, We don't need to do that. Similar things occur for gravity, where this charge here becomes the translation operator, and this prefactor isn't just a number, it's an operator which acts on the infrared safe matrix element. Now back to so I'm very happy about this, that there's a way of thinking about an S matrix, which doesn't have IR divergences in it. And of course, part of the reason I'm happy about it is that just in order to ask if the black hole S matrix is unitary, we have to have an S matrix. Otherwise, there's not even a question to ask. And it's well known that if you take a generic S matrix, even E plus goes to E minus, and you integrate out the soft sector, what's left is completely incoherent. So if we want to carefully keep track of quantum information, we need some kind of S matrix, and we need to say something about the soft particle. Now, there's a lot more interesting structure that has come out of this analysis, but there'll be a paper out soon, hopefully. Finally, to add to, or
sorry,
echo,
you have 1 minute.
Okay, to add to and echo what Shiraz said in his beautiful talk, what various things like this that Nima has been saying, a really sharp problem is what's the most general form of the graviton 4-point function. And Shiraz had a whole bunch of constraints which greatly limit. There are more of them. Subleading soft symmetry is not imposed, or I don't think supertranslation or conformal invariance have been imposed. One thing I'm excited about is the possibility of putting all these many different people in the community have been thinking about this from different ways. And possibly if we put it all together, we can get a unique or nearly unique 4-graviton scattering amplitude. And the $1 million question is, does that amplitude, how unique are the ones that the only ones we know, namely the ones that come out of string theory. So finally, the reformulation of Minkowski space as a collection of correlators on the celestial sphere is leading to novel insights, and there's a lot left that we have to understand. Okay, thank you, Nastya.
Thank you. Let's thank Andy for the great talk. And now we have 8 minutes for questions. So could you please raise your hand? There were a lot of discussion in the chat, but if I don't see any. There are a lot of people discussing in the chat. Would some of you like to ask a question? Okay, Dan Harlow.
Yeah, I think the issue, so the question was about where the singularities are located in the correlators. In particular, there seem to be singularities away from coincident points, which is not standard for Euclidean CFT. So do you have any comments about those kinds of singularities?
Yes, that of course is a very important point. And so in momentum space, of course, all scattering amplitudes are either 0 or infinite. They're 0 if the momenta don't line up, and they're infinite if they all line up. Here, one of the singularities of momentum conservation remains, and that's a delta in the real part of the conformal cross ratio. And so a question is, how could you get such a thing in a conformal field theory? And we have a possible answer to that question. We don't know if this is how it goes. I'm working now with Anna Reclario and Alex Atansov. We've done a conformal partial wave expansion. Nastya has also done such things, and a conformal block expansions. And this singularity is a direct result of translation invariance. And the conformal blocks are not translationally invariant. They're mapped into one another by the act of translations. And so there's something that we'd like to call, usually you talk about SL2C blocks. There's something that we'd like to call Poincare blocks, though we're not even very sure what they are yet now. But anyway, it appears that the delta functions come, you have things like z over z bar to the n. You add those over all values from n, from plus to minus infinity. That's what you're forced to do to implement translation invariance. And when you do that, that turns into a delta function. Delta of the imaginary part of z is the sum from n goes to minus infinity and infinity of n over n bar. So you can get other kinds of infinities in conformal field theory when you have infinite number of fields. But here, the infinite number of fields are the sequence of fields that you get from infinite numbers of translations. And these divergences are no more difficult to deal with than they're 1/4 as difficult to deal with as the divergences that you get in ordinary momentum space quantum field theory, though they appear very novel from the point of view of two-dimensional conformal field theory.
Shiraz?
Hi, Andy. Great talk. I wanted to ask about, you have this way of getting a clean finite S matrix for QED and for gravity. The problem of finding finite S matrices and non-trivial interacting conformal field theories seems sort of similar but more difficult. And I was wondering whether your methods might lead to a prescription for finding clean S matrices and non-trivial interacting field theory, conformal field theories as well.
You mean ones without IR divergences?
No, ones with, so if it's a conformal field theory, presumably it always has IR divergences in it. So say n equals 4 Yang-Mills at lambda equals 1.
Okay, well, yeah, so I mean, I'm very optimistic, though I have to say even my close colleagues don't share my optimism, that techniques like this can get us infrared finite, because I think we've understood conceptually where infrared divergences come from. They are the penalty you pay for trying to compute things which are zero due to conservation laws. If you don't violate the conservation laws, you don't get any infrared divergences. Now, I'm optimistic, and indeed we've already done this work on color memory and so on, that we can find infrared finite amplitudes even for n equals 4 non-abelian gauge theory. And indeed there's a very beautiful algebra. The superconformal and the conformal transformations tie in with the leading gauge transformations to give you the subleading gauge transformations. And so it's a very tight structure that there aren't going to be many ways around.
Sorry, and one follow-up, if I may, Anastasia?
Yes, go ahead. Yeah.
These finite S matrices, the finite S matrices that you have, they obey some sort of Kutkowski's rules. Do they obey unitarity cutting rules by themselves? Even in the case of QED.
You broke up, Shiraz.
Yes. Do your finite S matrices, do they obey unitarity cutting rules like Kutkowski's rules?
That's a very good question. I imagine that question, I don't know. Let me say, I don't know the answer. I would imagine that question was addressed in some form, which will be very hard to read, way back in the 70s, when Fadeev and Kulish were doing this kind of work. And there's some question of whether the intermediate states will be dressed or not. And if they're dressed, what do you how do you think about it?
Thank you.
Okay, unfortunately, we have to really move to the next talk. So let's thank Andy for the great talk again. And now we're gonna move to the next speaker, Samir Mathur from Ohio State, and he's gonna tell us about the Vicro hypothesis. Samir?
So I'm just trying to share screen now. Okay, so, and then I do maybe view full screen. Okay, does that look good? Can you see the screen there?
That's great.
Okay, thank you. Thank you for inviting me to speak at this wonderful conference, and thanks to everyone for making possible this conference in these very difficult circumstances. So I would like to share with you some ideas I have been thinking about over the past several years. And in particular, a summary of those ideas are in this last paper, which is titled The Vector Hypothesis. So let's begin with the black hole information paradox. So here I have a shell which collapses. Classically, all the stuff goes to the center, and then we produce these entangled pairs at the horizon, which you can schematically model as 0, 0 plus 1, 1. And there will always be small corrections of order epsilon coming from some quantum gravity effects. But in this picture, the entanglement of the radiation with the black hole that stays behind, well, that just keeps monotonically growing with time. While for a normal body, that entanglement should go to 0. And that gives us the information puzzle. Now, with the fuzzball paradigm for understanding black holes, we don't face this problem. So what is the fuzzball paradigm? You consider branes in string theory and make their bound states, because that's how you should think of black holes in the theory. At weak coupling, these branes might simply make some bound state whose size might be Planck length or string length. But then what happens when you increase the coupling to the point where you expect a black hole? Now, at first, you might think that the brane bound state remains Planck size and a huge empty space develops around it with a horizon. And in that case, you would get a traditional picture of the black hole and you would still have the information puzzle. But what was found was that that's not what happens. The size of the brane bound state actually grows with the coupling and the number of branes in the state, so that the size of the bound state is always order the horizon size. So a traditional horizon actually never forms. And so, in fact, what you end up getting is just an object which conceptually is no different from a piece of coal or a planet. It just radiates information from its surface like any other body, and there is no information puzzle. So in fact, in one sense, if you just accept that what we have been seeing from string theory is the answer, and now there's so much evidence that in fact it is, then the information puzzle is solved. Black holes are just like pieces of coal. But what we'll see in this talk is that we will learn a lot by asking a slightly more refined question. Where and when does the semi-classical approximation break down? So again, consider the shell which was collapsing. When it passes through its horizon radius given by these dotted lines, all curvatures are low. And then when it goes all the way near the center, in the region between the shell and the horizon, the light cones actually turn inwards. We are actually going to assume there are no large violations of causality in our gravity theory. Okay? But in that case, what is happening in the semi-classical picture at the center, it cannot actually influence what is happening at the horizon, because those two places are very far apart causally. So in that case, how does the semi-classical picture change in such a way that somehow at the end, instead of just getting this normal horizon with normal physics at the horizon, we end up with the fuzzball? So this, of course, is the central aspect of the information question. As you do the semi-classical collapse, all curvatures are low. When you get to the singularity, you can ask for new physics, but then you cannot causally actually influence the horizon anymore. So you'll keep getting the entangled pairs and you are in trouble. So in fact, this is the central puzzle, and this is the question we will try to give an answer to in this talk. Of course, this question is qualitative, and so our discussion today will also be completely qualitative. It will be a discussion of a picture, but that picture will resolve this basic puzzle. So we will argue for a picture of the quantum gravity vacuum, which will resolve the puzzle. We call this picture the vector hypothesis, and its acronym is given here. We will see the meaning of these terms as we go through the talk. But the rough idea is as follows. We have seen that the microstates of the black hole are these extended objects. This E extended stands for the E in the vector acronym. And so the extended objects of size a little bit larger than the horizon radius. But if these are the real objects in the theory, then the quantum gravity vacuum, the state with zero energy, must contain virtual fluctuations corresponding to these objects. So here I have depicted the fact that around every point of space and time, there will be these virtual fluctuations of these fuzzball type configurations of all sizes around every point at every time. Now, you might think that the fluctuations of an object with size much larger than Planck length will be highly suppressed. And of course, you will be right. But the point is that if you look at on-shell fuzzballs, there are an exponential of S Bekenstein number of such objects, which for large R is a very large number. So in fact, there will be a large phase space of such configurations. And we will assume that this large phase space will offset this suppression so that overall, these virtual fluctuations will remain an important component of our vacuum. So in fact, we'll have one more property of these vectors, the compression resistance, but we will come to that later on. But then this is the vector hypothesis. The quantum gravity vacuum contains an important component consisting of virtual fuzzball type configurations, and that this component plays a crucial role in situations where a horizon is predicted by a semi-classical theory. And so just when a horizon would have formed, what happens is that these virtual fluctuations, they turn to on-shell configurations and they resolve the puzzles that arise. So in this talk, we'll be talking about the puzzle that comes from what happens during gravitational collapse. But other puzzles which are addressed in that paper I mentioned is that it also resolves the bags of gold problem. It answers the question, are the Rindler black hole and cosmological horizons similar? They look similar at the classical level, but in fact they are not. They differ in their vector fluctuation. And in fact, we'll see that it can also impact cosmological issues like inflation, cosmological constant. And if I get a chance at the end of the talk, I'll talk about how it could change the picture of bubble nucleation. Okay, so let me begin with a brief review of fuzzballs. Lots of people have worked and contributed to the fuzzball game. I've listed some of their names over here. But again, just starting with the very basics, it goes back to this observation that if you try to estimate the size of a bound state of, let's say, D1, D5, and P charges, then the size depends on the number of branes and the string coupling. These are parameters appearing in the compactification, and the size which you estimate for this bound state is a complicated function of these variables. But in fact, remarkably, this complicated function you get is of the same order as the horizon radius of a black hole with those charges and that mass. So in that case, that's what suggested that, in fact, you never actually end up getting black holes in string theory. A black hole just doesn't form. And since then, many, many examples of explicit string solutions have been constructed for these bound states. And in each case, we have found that there is actually no horizon. You always get a fuzzball instead. And so the fuzzball conjecture just says that no microstate in string theory will have a traditional horizon, which is defined as something which has the vacuum in its vicinity, where you get pair production up to order epsilon corrections of the kind that Hawking was envisaging. In fact, you just get a normal body with a surface, and the radiation then depends on what you have on the surface. You might at this point ask, how did we bypass the various no-hair theorems for classical gravity? And in fact, there are special features of string theory with extra dimensions, extended objects, Chern-Simons terms, etc., which in each case allow you to bypass these theorems. We could still ask, though, what about the spirit of something like Buchtel's theorem? If you take a fluid sphere where the pressure is decreasing outwards and the radius is greater than less than 2¼ m, well, then you put the pressure to 0 at the surface of that sphere. And if you integrate the pressure balance equation inwards, you find that the pressure will diverge someplace before you reach R equal to 0. You will then say it's not a good solution and must therefore collapse to make a black hole. Well, let's just look at a toy model, which will help us understand a little bit of how all these extra features of a theory like string theory can help us evade these puzzles. Take a geometry which is Euclidean Schwarzschild plus time. So it's a geometry in 4+1 dimensions. These 4 dimensions make Euclidean Schwarzschild, which has geometry of a cigar with a compact circle labeled by this coordinate tau. Tau has this periodicity over here. And then I just tacked on an extra Minkowski time. This entire geometry is a solution of the vacuum Einstein equations in 4+1 dimensions. But let us dimensionally reduce on the direction tau to get a 3+1 gravity theory coupled to a scalar field which comes from the size of the tau circle. That scalar field has the normal stress tensor of a minimally coupled scalar. And from the point of view of the 3+1 theory, you could now ask, why is this shell or scalar field not collapsing inwards? Why is it staying where it is? In fact, if you work out the stress tensor of the scalar field, you find that its components diverge as you get to the tip of the cigar. So this is actually singular from a perspective of somebody who was trying to do a Buktal type analysis, and you would discard this solution. But in fact, the solution is completely regular in 4+1 dimensions. It's only from the 3+1 dimensional perspective and the compactification that the decomposition broke down. And so in fact, the overall solution is completely regular and just stays in there, even though the pressure seems to be becoming sick in some fashion. So we can keep this at the back of our mind as a toy model of the fuzzball for what's going to follow. In general, fuzzballs are made with lots of extra things like strings, brains, fluxes, and so on. But for present purposes, you can just imagine we have these little things. Each of these little things I've drawn here, you can think of as one bubble of Euclidean Schwarzschild, and these bubbles are fitted together in a way that they hold themselves together to make some kind of a bound state. And I'm not saying fuzzballs are really have to be anything like this in any particular detail, but is it just a good toy picture to keep in your mind for the purposes of what we are going to discuss qualitatively in this talk? Let's then get back to our causality puzzle. So here was the puzzle. Let's take a shell which is made, let's say, of massless gravitons. So it's collapsing at the speed of light. You can just, that gives us the stiffest contradictions. And then at some point it'll pass through its horizon, at which point the curvatures are still low. So it seems there's nothing which can stop that. And then once it goes inside, even though new physics can happen, because the light cones point inwards, how does it actually influence what happens at the horizon? We will in fact assume causality, because as far as I know, string theory does not manifest any large violations of causality. So if curvatures are low throughout a space-time region, then we will assume causality holds to leading order. You can always have small corrections from any quantum gravity effects anywhere. And causality means the signals do not propagate outside the light cone, and there are no non-local interactions between points that are space-like separated. Again, there can be small effects, but not large enough to suddenly change my horizon completely. Well, in that case, how do we actually go from a picture which was giving us this to actually making a fuzzball? In fact, you can make the puzzle even more precise by looking at what I call partial shells. So this was again my shell which was collapsing, and this was the horizon radius. Let's consider two situations. One where we allow the shell to just go through its horizon, and then we do expect in the classical theory, or in fact in the full theory, for a black hole to form. But then the other thing we could do is, when all the shell reaches the radius, let's say like 4m, we just stop all the other parts of the shell, but one little piece we allow it to go in. And in this case, you actually don't expect a black hole to form, because a little piece of the shell is almost like a planar Eichelberg's axial wave. And when Eichelberg's axial wave passes through any point of space, then that point of space just has local quantum gravity fluctuation, of course. And when the wave passes through, it may mess them up a little bit. But once the wave is gone, the space-time returns back to the vacuum. So in fact, nothing actually happens. There's no memory of that left once you pass it there. And so if you could actually look locally at each of these pieces, even in this case, you would see that nothing should happen, and the thing should just semi-classically go to the center. So then you just get tracked by the causality puzzle. But now you can begin to see why we are thinking in terms of vector fluctuations as the things which will come and solve our puzzle, because these fluctuations have an extended size, and in fact, they can therefore feel around the scale of the horizon that we are going to create. And so they can know whether the entire shell is coming or only a part of the shell is coming. And so in fact, what we are going to argue is that these virtual fluctuations of large size, which are not suppressed because there are so many of them, the phase space factor overwhelms their action for suppression. These vector fluctuations are the ones that will actually will see that the entire shell is about to make a black hole, and they will actually become on shell instead of virtual fluctuations at the point where the black hole really forms. So that was a qualitative picture of where we are going. And so now let's take a slightly more detailed look at the vector hypothesis. So again, for that, we've been saying very roughly things like virtual fluctuations, but what really is a virtual fluctuation? So if we just take a free scalar field, for example, then you can look at each Fourier mode phi k. I've plotted its amplitude on the x-axis and the potential of that on the y-axis. And that's just a harmonic oscillator potential. And because I'm in the vacuum state, I just get the vacuum Gaussian as the wave function. Well then, the wave function has a tail which is going into regions where pi square is negative. And that's what we just call the virtual fluctuation. You don't actually have an on-shell oscillating wave function there, but you do have this tail where the pi square is negative, and you can call that the virtual fluctuations of scalar field particles in the vacuum of this scalar field theory. Now, suppose the scalar field actually arose at the size of a compact circle, then this is the compact circle that I have drawn here. And then when the circle size fluctuates a little bit up or down, well, those are exactly this tail out here. But in fact, you can also have large fluctuations where the circle pinches off and you make a new topology where you create a hole in the middle and the rest of it closes off like a cigar. That's a bit like the model we had for the Euclidean Schwarzschild, which was our toy model for the fuzzball. So in fact, there is a part of this tail which goes into the region which is not captured by the scalar field. It's actually into the region where we have these new topologies which give rise to fuzzball type configurations. And so again, as we had said, bound states of these kinds of local Euclidean Schwarzschild was our toy model for the moment of what the fuzzball was doing. So let's continue with that picture for a moment. So then let's ask, how do bound states show up in the potential we were just sketching? So you could have virtual fluctuations of the fundamental field, let's say electrons and positrons, but then you also expect that bound states like the positronium or even a benzene ring would show up as fluctuations in the vacuum. Now, an on-shell positronium state is orthogonal to the vacuum. So what do we really mean by saying there are fluctuations of the positronium in the vacuum? Well, what really happens is that the way a bound state manifests itself in these potential diagrams we have been drawing is that if we draw the configuration space of all configurations in the theory on the horizontal axis and the potential for that configuration on the vertical axis, if I just had E plus E minus in the theory, I would have a potential, let's say, like this purple curve. But if there are bound states like the positronium, then in those directions of field space where the bound states form, we simply get a lowering of the potential. And so here the potential gets lowered correspond to the bound states in the theory, and then the vacuum wave functional actually spreads a little bit more because the potential is lower, and this wider spread of the vacuum wave functional is how we see the existence of virtual fluctuations of these bound states in the vacuum. Well, then we come to the question we had noted before, which was very important. The fluctuation to any one large fuzzball configuration will be highly suppressed. You can write it as the probability as something like exponential of minus an action, and the action you could write as energy times time. And if I put the energy to be the mass of a black hole in d space dimensions, and the time also be just like the crossing time, then in fact the suppression you can see is rather large when R is much bigger than LP. But then, as we said, there are a large number of fuzzballs. If I write that number as e to the s Bekenstein, then you find that the exponent you get over here is such that this p times this n, the p is small and the n is big, but at least for on-shell fuzzballs, this two can cancel and give you something of order unity. So the suppression is indeed, in this case, offset by the large degeneracy. Now, of course, we are going to talk about virtual fluctuations, and we understand much less about that. This was for on-shell fuzzballs. And so we'll just make as part of our hypothesis that the part of the wave functional which leaks in these vector directions is actually going to be significant even when we come to large vectors because of this offset between the large phase space and the suppression. The last point we were going to talk about was the compression resistance. So the fuzzball configurations are such that they are rather resistant to compression. If you squeeze them or stretch them, it costs you energy. You can see that by looking at actual vector configurations which have been fuzzball configurations which have been made, but you can also argue more abstractly by looking at the equation of state for the black hole gas, which would now be a gas of fuzzballs. So at least for on-shell fuzzballs, one can argue that the equation of state P equals rho is what you get, and that's the stiffest one allowed by causality. So anyway, we'll just assume that whatever we have learned from on-shell fuzzballs also applies to the configuration which show up in their virtual fluctuations. And the scale we learned for the compression energy in that case is that if you take a vector of radius RV and you compress it to a radius 1 minus delta times RV and let delta be order 1, suppose you compress it to half its size, then the amount of energy increase you get is of order the mass of a black hole with radius of the order of RV. You can make a heuristic model to sort of model that, but that won't be important to us. I'm just saying that the compressibility is what I just said in words over here. So anyway, with all this, we have arrived at a qualitative picture for the behavior of these vector fluctuations. There are these virtual fluctuations around every point. They're extended. They are very numerous. So this is an important component of the vacuum under this hypothesis, and they are compression resistant. We have some picture of what these virtual fluctuations should behave like. Let's now see how it comes back and solves a puzzle. So if you just first take just a vector in flat space, that's over here, and then you put some ordinary object like a star in the middle over there. Well, the star has a gravitational pull, so it slightly pulls the vector in, the vector gets compressed, but of course it's compression resistant, so after compressing a little bit, it stabilizes. And so I've drawn this gray thing a little bit smaller than this, but that's all that happens. And this part of the dynamics is of course just included in the dynamics you get from the Einstein action, because after all, this vacuum was part of, these vectors are part of the vacuum wave functional. So whatever they did was part of the effective action you were seeing in gravity anyway. But now let's look at the situation with gravitational collapse. I have a dust ball which is now collapsing. Once it goes inside the horizon, the light cones turn inwards, and finally now this ball can't stop, and so the whole thing goes to a singularity. That was the traditional picture of black hole collapse. But now we have to ask, what are the vector fluctuations doing? Now inside the horizon, as we said, the light cones point inwards. So any vector fluctuation that you have over here, it also cannot be a stable configuration which just stays where it is. It must keep compressing just by the structure of light cones. It cannot stabilize. Now, if it keeps on compressing, then an order unity compression of the vector actually distorts the wave function completely. And it distorts it to the point where the vector actually turns into an on-shell fuzzball. So in fact, we'll see that because in this case, the compression must keep going on and on, the vacuum doesn't just change a little bit and stabilize in its wave functional. The wave functional has to change by a large amount. And that's what I've drawn in this picture over here. You have the vectors which are inside the horizon. They're forced to keep on compressing. And so that's what's special about when you make a horizon. Once you make a closed trap surface, these vectors have to keep on compressing. And then at some point, they start turning into on-shell fuzzballs. That's depicted by these dark rings over here. And then over a time of order a few crossing times, you actually end up with an on-shell fuzzball. So in terms of the potential graphs we were drawing, this was the wave function we had. The steps of higher and higher energy were in fact the vectors of higher and higher, larger and larger size. But now what is happening is the vectors which were larger, the ones which were of the order of the horizon size, under the attraction of the star, the very intense attraction you get near the horizon, their energy rose very steeply. So the part of the wave function which was leaking over there, well, that must actually squeeze inwards. And in squeezing inwards, it actually becomes oscillatory in part of the region where you actually had vector configuration. So in fact, that's literally what we meant by these pictures, that the wave function actually turns from being just in a region where pi square was less than 0, part of the wave function over the vector configurations, that now has pi square greater than 0, which just means you formed on-shell fuzzballs. And that is our picture for how the puzzle is actually resolved, the causality puzzle resolved, and you actually end up making the on-shell fuzzballs. So as an illustrative model of what just happened, you could look at something as simple as the Schwinger effect. So take two plates, one positive and one negative, and let there be a very large number n of flavors of the charged particles. So, the vacuum gets polarized, but if I choose the separation between the plates to be less than a certain critical value, I cannot actually create on-shell particles of E plus E minus. So the vacuum is highly polarized, but there are no on-shell particles. But if I increase the separation of the plates now to be larger than this critical value, then I will indeed get a cascade of on-shell particles, which will just, there'll be a very large number of them because I've taken a large number of flavors. Now, suppose somebody had not realized that the vacuum had this very high polarization from these large number of flavors of charged particles. This large number n is like the large degeneracy of possible vectors that we can have. Suppose nobody thought much about the vacuum polarization, then when he actually crossed the critical distance and suddenly found a whole cascade of on-shell particles coming, he would be surprised what happened here. But then if he had always been aware of the fact that these polarizations were there, then in fact, all that happens at the critical transition is that things which were getting close to being on-shell now actually just turn on-shell. And that's essentially what we are saying also happens with these vector fluctuations. The vacuum actually has a large number of these virtual fluctuations. They're all just part of the vacuum wave function, but they cascade to on-shell fuzzballs once these vector fluctuations suffer an unbounded compression, which comes when they're inside a closed trap surface. So that is our picture. Let's just take a couple of minutes to say how this might influence things that we see in cosmology. So this is completely speculative, but just to tell you how it could be of interest. We said a black hole has a closed trap surface, and that's why vectors inside there just cannot be stable. They have to keep compressing, and then these structures just get destroyed. Now, cosmology is just the opposite. Under T2 minus T, it's the same, but because we have an expanding cosmology, we have anti-trap surfaces. And now you can see if we have a vector which is bigger than the size of the cosmological horizon, then it is actually going to be torn apart. So in fact, there just can't be any vectors this time which are larger than the horizon, just like here you couldn't have vectors which were smaller than the horizon. So in fact, an important ingredient to think about in cosmology as well is now in any space-time, an important thing to think about is what's the number density of vectors as plotted with the vector size RV. So in Minkowski space, we said we have vectors of all sizes, but in the cosmology, the vector size actually has to trail off and end at order H inverse. So let's see what this might do in a situation of bubble nucleation. So suppose I have a scalar field with a potential which has one metastable minimum, and at that I would kind of, if the field is here, I get a de Sitter space, and that's drawn out here in blue. But if the field tunnels down to this zero energy configuration, then I will get a bubble of flat space-time with some radius r, and then this bubble expands. This thing in black here is the bubble wall, and as r goes to infinity, the speed of the bubble wall goes to infinity. It goes to the speed of light. So why does it go to the speed of light? Because the energy we get from the potential drop from here to here is proportional to the volume. And the energy which is in the bubble wall is only proportional to the area. So as r becomes big, the extra factor of r here is made up by the fact that gamma, the boost factor, goes to infinity, which means v has to go to 1. But now we should actually ask, what are the vector fluctuations doing? In the de Sitter phase here, the vector fluctuations were limited in size by H inverse, while flat space needs vectors of all sizes. So in particular, if the flat space region has size r, we need vectors all the way up to r. But to make a vector of radius r needs at least a light crossing time across that distance. For example, if you want to make a benzene ring fluctuation, you must at least have time to go across the diameter of a benzene ring. But that tells you that the flat space region can only expand at a speed which is less than or equal to half the speed of light, which means gamma must remain of order 1. But then we actually cannot get this energy balance where all the energy went to the bubble wall. And in fact, the picture must change, saying that the energy which is which we got from transitioning from the blue phase to the white phase must actually remain distributed all through inside. We can't just go to flat space immediately inside. We have to slowly trickle down to the flat space, and the bubble has to actually expand slowly, all the while depositing its energy all through this bubble. Now, I don't know if this is completely going to be the right theory here, but I think it's very interesting because one of the early studies of bubble nucleation, they were actually having this difficulty that the energy all stayed in the bubble wall. But in fact, if the energy distributed themselves all throughout, it was better for what we see up in the sky. So in fact, if these effects are there, they may be very relevant to cosmology. Okay, so let me—
Sorry, Samir, 3 minutes.
Thank you. Okay, so let me just go to my summary, but I would like to remind people that when we talk about the black hole information paradox, we should always focus on what we have learned from the small corrections theorem. So this inequality actually makes the puzzle precise. And so let's just remind ourselves of what this theorem is. Suppose we make two assumptions. Here's a black hole creating entangled pairs. The pair member B is outside, C is inside. And so the leading order Hawking effect, let's say, is modeled by 0, 0 plus 1, 1 entanglement. But now we allow small corrections. So in fact, we add a small correction, some epsilon k times the orthogonal state to this basic pair state. The second thing we allow ourselves, the second thing we assume is that once the radiated quantum gets far out away from the hole, let's say beyond some point 10 m, it doesn't get modified any further. So here we just have normal physics. That's what happens for a piece of burning paper. Once the photon goes out, it's gone. So once you make these two assumptions which look completely innocuous, then this theorem actually proves that the entanglement between the hole and the radiation will keep growing. So Hawking's answer was linearly rising with a small correction that could be slightly less by an amount to epsilon, but in fact cannot turn around and become the page curve. So why was this worth proving? It's worth proving because you can actually make a very complicated state by using these small corrections. If at the first step, when you emitted a pair B1, C1, if they were 0, 0, you could correct the second pair B2, C2 by adding some particular correction epsilon 1. But if the first pair was emitted with 1, 1, you could correct the state with a different epsilon. Let's call it epsilon 1 prime. And you can see after n steps of emission, there are 2 to the n correction terms where every thing which was emitted depends on all the previous steps you emitted, but always with small corrections. And then you might think because n is very big, maybe even with small epsilon, the corrections accumulate and somehow could manage to bring your page curve down. But what this theorem does is it tells you, no, you cannot do that. Okay, so I think this is very central because it gives you two very sharp solutions to the information puzzle, which I call the fuzzball paradigm, and for lack of a better word, let me just call it the wormhole paradigm. In the fuzzball paradigm, you do not actually have the vacuum around the horizon. And in fact, you don't have normal pair equation of states. It really burns like a piece of paper and the page curve comes down. There is nothing novel there. And in fact, when you add the Vector hypothesis, you solve all the puzzles in a consistent way that we've had with quantum gravity. In the wormhole puzzle, on the other hand, in the wormhole picture, one assumes that here we actually have a state which is close to the state of the vacuum, and we do produce pairs, which at least when you look at a few pairs at a given time, they actually behave like what Hawking had. But in this case, you must do something new. And in fact, we have been seeing very interesting new ideas come up. Some part of the interior of this black hole is not like in the piece of coal. In a piece of the fuzzball is really like a piece of coal, inside, outside, everywhere. But here you now have to have new ideas where inside the black hole there's a region which is really part of the radiation outside. That part is not like what we would normally think from the piece of coal. And if you want to have a process where the radiation outside can actually pull information out from the inside, then in fact the physics in the region far out, let's say R of the order of n cube or more, cannot be the physics we have in a StatMed book for particles which have gone out to flat infinity. So I think there are very interesting ideas here, but I do not believe that they are correct, because in fact we get a complete solution of the puzzle in string theory by just finding that when you actually make states in the theory, they just look like ordinary pieces of coal. They just don't have a horizon, and there is nothing further to think about. So what I would like to emphasize by this last slide, which I have put up here, is that sometimes people have this confusion about the information paradox. They would like to say that they would the full theory might be doing something which was actually going to bring the page curve down. And just these small little corrections that they have can encode the corrections and do what they need. But that is not true. When someone says they have approximately like a black hole in some classical limit, the question you should always ask is, well, do you actually have an entangled pair like this? Are these two equations true? If they say no, then you have to say, well, how did you go to your gravity theory and break the no-hair theorem? You need something like a fuzzball construction, which only works in the full string theory, and you have to go and do that. If they say yes, they do have this kind of pair production up to small corrections of order epsilon, you cannot actually have, if you say, I don't want any non-local physics, you actually cannot get the information out. So I think this is a very important distinction to maintain when people just say the black hole is almost semi-classical, it's almost classical, but I have small effects. The small correction theorem tells you, no, that is not so. You have to be precise. Once you assume this, you will need new physics. Either you'll have remnants and baby universes, or you need non-local physics to get the information out, but you can't have the whole thing burning like a piece of paper. Okay. Thank you very much. Thank you for your attention.
Thank you. Let's thank Samir for a very nice talk. And now we have 8 minutes for questions in order to start the next talk on time. Please raise your hands for questions. Surat?
Hi, Samir. I just wanted to clarify an issue about the small corrections theorem. So there's a sense, of course, in which I think you would agree that one can have small corrections to ordinary correlators and not violate this theorem. But what you're really talking about when you say small corrections is that the full wave function cannot have small corrections from Hawking's computation. Is that correct? And if that is correct, I mean, what implications does that really have for the question of an experience of an observer who's trying to fall through? Because generally, if you have an observer who's trying to make physical measurements, that observer doesn't try and obtain fine-grained details of the wave function, but just of simple observables.
Yeah, good. Yeah, thanks for that question. I think that really brings us to the heart of exactly what I was trying to say on this last couple of slides. I have always maintained that if you want to address the information puzzle, you have to talk about the wave function. This is a puzzle about the entire wave functional on a complete Cauchy slice and what you get from the semi-classical evolution and why it is not agreeing with what you would like from something like the page curve. And the small correction theorem tells you that small corrections to each particular entangled pair near the horizon, if you only allow small corrections, you cannot solve the puzzle without having non-local effects or some new physics, which is far away from the black hole, new physics far from the black hole. So it is indeed a statement in terms of the wave functions. So that's why I think when people talk in terms of operators or endpoint functions or two-point functions, I think they always miss the puzzle. Because if you want to ask something like, okay, what does an infalling observer feel as he's going through, then we have this particular model. You can make a bit model for what I call fuzzball complementarity. If the infalling observer has an energy E much bigger than T, the temperature, then in fact you can make a bit model. We don't know if the model is true, I actually realized it with fuzzballs, but at least you can make a model where you can effectively reproduce the behavior for order crossing time as if he is falling freely in, even though those are not the actual states of the fuzzball. It's just that the collective modes of the fuzzball have the same frequency as the modes seen in empty space, but again, only for modes for E much bigger than T. The important point to always ask for the information puzzle and for the page curve, which we have, for example, up on the screen, is for quanta of energy T, because those are the Hawking quanta. For those you ask about the state, you ask for the state of each pair which is emitted. You don't care what happens once a pair goes far inside. Once a member falls far inside, anything can happen to him. It's not important for the theorem. You only want it once the guy is outside, you don't touch it anymore once it's beyond 10 M. Once you say that that looks like 0, 0 plus 1, 1 plus order epsilon, you need new physics at infinity. That is the lesson. And I would agree with you that if you just look at infalling observers and things like that, there are many effective behaviors you can have. But again, they are for E much bigger than T. And that's not exactly the information question. I call that the info question.
Fine. I just even if you look at observers who are spread out all over the black hole and make low energy 2-point functions, even they would see the same as the conventional geometry, right? It's only
Yeah, that I think is very much possible, because I think even if you just take a normal piece of coal, no black hole, no gravity, nothing, and if you just have observers, let's just spread throughout this room, forget coal, just throughout this room, and they're looking at local 2-point functions, because the state in every particular corner of the room is entangled with every other, just one big state, they would not actually be able to figure out if the state of this room is entangled with the state in the next room or not. But that's just a property of any large StatMech system. But that's not the information puzzle. In the information puzzle, we assume we have the entire state. And now we are talking about a property of the entire state. We can make any measurements of any precision we want, and we still have a contradiction with the semi-classical picture. But as I was emphasizing, the point is that you shouldn't say the semi-classical picture is almost correct, because the almost doesn't work. That's the real power of the information paradox. If you say semi-classical is correct up to order epsilon, you cannot get out of it. And if you want to make an order 1 correction, you have to go and see how in your gravity theory, you will beat the no-hair theorem. And that is exactly what the fuzzball people actually do. But for that, you need the full string theory, and effective theory or just reduced gravity theories will not do that. But thanks for that question.
Okay, we'll take the last question from Steve Giddings.
Hi, Samir. So I agree with the statement of the small corrections theorem that you need an order 1 correction to the state. Really, in some sense, that was implicit in the page analysis. But one thing I think that misses is that you can have interactions which are small with the quantum state of the black hole that produce an order 1 change in the state. When you look at the actual quantum probabilities for interactions, you can have a cancellation between a small interaction or small amplitude, and then have that compensated by a large number of final states. So that, I think, is one way of evading the conclusion that you have to have very, evolution near the horizon that doesn't look normal in your language.
So I think what you just said actually is not true. I think I did read one of your earlier papers. I haven't read your recent paper about it. And I think there was a step where I can point to that something is behaving in a way which is not allowed by unitary analysis. But somehow I don't actually have that in front of me right now, so I'm not able to tell you exactly what I had in mind. But maybe there's something I would very much like to discuss offline. So let me just make the statement I'm making, at least the claim I'm making is, if you actually have a state where the overlap with the vacuum this is not the one I had in mind here. If you actually have this condition that the overlap of psi with the vacuum is close to 1, that is, you basically do have the vacuum there up to small corrections, you cannot actually do anything. So if that's something that we're not agreeing on, then absolutely, let's talk about it offline.
Well, I think you can write down model interactions that lead to an order 1 change in the state, basically, and they're small interactions, but we could continue this later, sure.
Sure, we can talk about that.
Yeah. Okay, let's thank Samir again. And we're going to move to the next speaker. Our next speaker is Jeff Pennington from Stanford. He's going to talk about replica wormholes and the black hole interior.
Okay, thank you very much. Share my screen. Okay, is that working? Can people hear me, see the screen, stuff like that?
Great.
Yep, okay. Awesome, so yeah, thank you very much to the organizers for inviting me to give a talk. So my talk is called Replica Wormholes in the Black Hole Interior. It's about this paper that came out last November, which was with Steve Schenker, Douglas Stanford, and Jianbing Yang. And there was a paper that came out the same day by Almiri, Hartman, Maldacena, Shabulian, and Tedjini. And really, a more accurate title for this paper would be Section 2 of Replica Wormholes in the Black Hole Interior, because that's all I'm actually going to talk about. Douglas is going to be talking next, and as part of his talk, he might talk a bit about some other aspects of the paper. So what is the sort of claim of this paper? It's very simple. It's that we can successfully calculate the page curve for an evaporating black hole just from a gravitational path integral. And a more precise version of this claim in this talk, I'm just going to be talking about a very highly simplified model. It's not really an evaporating black hole at all, but it is a black hole with an information paradox. And the advantage of that model is that we can do very, very precise calculations in it. You can do the full path integral in that model and so on. And so we can really calculate anything you might want to calculate. But it really seems to be the case that the sort of basic story of how these calculations work is very general. It applies to higher dimensional black holes, applies in flat space, it applies whatever. So yeah, one thing that is really worth emphasizing is that the sort of arguments and ideas I'm going to be using came out of ideas from ADS-CFT. But really, when you actually think about it in terms of the gravitational path integral, there's no reason that you need to have a CFT, that you need to have string theory, you need to have anti-de Sitter space or anything like that. This is really just a calculation that involves the sort of low energy effective field theory, the gravitational path integral. But it needs to be, the rules for that effective field theory needs to include a sum over arbitrary space-time topologies. And in particular, it needs to include topologies containing what are called space-time wormholes, shortcuts through space-time connecting distant regions. So I'm not going to talk about them in my talk, but you can actually use very similar arguments to the ones that give you the page curve to show that not only do you have a page curve where the entropy starts going down, but you also actually have information escaping from the interior of the black hole into the Hawking radiation. Very complicated and cleverly designed operators acting on the Hawking radiation can in fact learn about stuff that seems to be in the interior of the black hole. So this is something that Douglas will talk about a bit. But yeah, for my talk, the first thing I really want to do is just introduce and motivate this sort of simple model we have. And really the motivation for it, as I say, is just to, we really think this is pretty much the simplest possible model you could have that meaningfully has black holes and has black holes with an information paradox. But in order to motivate that, then I'm going to have literally one slide talking about the actual traditional information paradox and evaporating black holes in flat space. So, this is, of course, a very familiar story, but let me just go through it very briefly. Okay, so for an evaporating black hole, you have Hawking radiation, and that Hawking radiation is entangled with a sort of partner mode that sits inside the interior of the black hole. And as the black hole evaporates, then you get more and more Hawking modes coming from closer and closer to the horizon. They're entangled with more and more interior degrees of freedom. And eventually, you reach this point called the page time, where the sort of entanglement entropy between the Hawking radiation and the interior modes seems to be larger than the Bekenstein-Hawking entropy of the black hole. Now, whether this is a problem or not depends on what you think the Bekenstein-Hawking entropy is. But if you believe that it is truly the sort of statistical entropy of black hole microstates, it's really counting the number of degrees of freedom that describe the entire state of the black hole, not just its horizon or something like that. And that's certainly something that seems to be true in string theory and ADS-CFT. Then this is a paradox, because there aren't enough black hole degrees of freedom to be able to purify the Hawking radiation. So at that point, you sort of only have two possible resolutions. You either need Hawking's answer that information is just actually lost, the S matrix is not unitary, or you need the sort of, this calculation where the entanglement entropy keeps going up to break down and the entanglement entropy to start decreasing at or before the page time, such that the entanglement entropy always remains bounded by the Bekenstein-Hawking. And this is the answer where you get a page curve, and that's obviously what we're going to find in this talk. Okay, so now we've sort of extracted out the essential features you need to get an information paradox. Then we can try and throw away all the annoying technical details, things like 4 dimensions and so on, that make it hard to actually do path integrals. So we want to make a gravitational model as simple as possible. What's the way to make quantum gravity easier? Well, you just go to fewer dimensions. So what's the fewest number of dimensions where you can have a black hole? It's 1 dimension of space and 1 dimension of time. So we're going to be considering one-sided eternal black holes in 1 + 1 dimensions. And if you have a one-sided black hole in 1 + 1 dimensions, you need to have the sort of space-time end somewhere. So we're just going to have it end on what's called an end of the world brane. This case is it's a 0 brane that the space-time just ends on. Okay, so that was the Lorentzian space-time. We can also consider its annular continuation to Euclidean time. And in this case, we see that the end of the world brane now goes out to the boundary. And that's good because that means we can sort of create this end of the world brane state by preparing it with a Euclidean path integral. That's in fact what we're going to do. Okay, so now we need some analog of Hawking radiation to actually create an information paradox. So one way you could do that is just add some matter fields to this 2D model. But even that's kind of annoying. You have to deal with quantum field theory and so on. There's an even simpler way. You're just going to add internal degrees of freedom that are just going to sit on the end of the world brane. These are modes, degrees of freedom in the interior of the black holes. There are interior modes. And then we're going to maximally entangle them with just some external quantum mechanical reference system. So I'm going to be a bit more concrete about that. So these internal degrees of freedom on the end of the world brane, you can think of as just having a large number of different flavors of end of the world brane. We can label by I, and then we have these set of microstates, psi I, where we have an end of the world brane in state I. And then we're just going to construct by hand. This is not happening from the dynamics. This is just a state where there basically are no dynamics. This is just a state that we're building completely by hand. A state where we have sort of, a superposition of psi I tensor some reference system in state I, where I is just some canonical orthonormal basis for the reference system. Just construct this highly entangled state. And then we can get our very simple version of the information paradox. You just take the number of states k of the end of the world brane and the reference system to be very, 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 very large. Bigger, in fact, than e to the Bekenstein-Hawking. And then naively, seems like the entanglement between this end of the world brane and the reference system is bigger than the Bekenstein-Hawking entropy. We have exactly the same information paradox that we had before. Okay. So that's all great. We seem to have an information paradox. This model is simple enough that we're just going to be able to, actually compute the entanglement entropy properly. And when we do that, we're going to find that this naive entropy that can be arbitrarily large is not the sort of real entanglement entropy, and the real entanglement entropy obeys a page curve. Okay. So the first way I'm going to get this answer, it's a very simple way that uses this rule for computing entanglement entropies in gravity. In this context, known as the island rule. It's really a special case of something more general called the quantum extremal surface prescription. And hopefully, I was actually asleep because it was at about 3 a.m. California time. But hopefully, this is something one talked about this morning. So what does this rule say? It just says the first thing you need to do is you need to find all technically quantum extremal surfaces that are homologous to the thing you're trying to find the entropy of. Okay, and then you're going to take all of these extremal surfaces and you're going to look at each of their generalized entropy, which this quantity that's like a sum of area over 4G Newton plus entanglement entropy across the surface. The extremal surface that's the smallest generalized entropy is called the minimal quantum extremal surface. And the rule says that its generalized entropy tells you the entanglement entropy you want to compute. Okay, so how does this rule apply in our case? Well, in this case, we have two extremal surfaces. They're codimension 2, so they're just a discrete number of points in 2 dimensions. The first extremal surface is just the empty set, and the second is just, in this case, is a classical extremal surface that sits at the bifurcation surface of the black hole. What are their generalized entropies? Well, the generalized entropy of the bifurcation surface is area over 4G Newton, so the Bekenstein-Hawking entropy of the black hole, plus the sort of entanglement entropy of this dashed line region. And there's no bulk degrees of freedom in this dashed line region, so that's 0. So the full generalized entropy is just the Bekenstein-Hawking. What about the empty set surface? Well, in that case, its area is 0, doesn't contain a point. But now this dashed line region contains the end of the world brane. And that end of the world brane has an entanglement entropy that is given by log k. So the generalized entropy of this empty set is log k. Okay, so put those two things together with the rule I just gave, and we get an answer that the actual entanglement entropy is given by the smaller of log k and the Bekenstein-Hawking. Log k we call this the naive Hawking answer. So this is the page curve. So great, that's the answer. We're done. Very simple model. There we go. But this at the moment, this is a bit unsatisfying because this is just some arbitrary rule that I just claimed was the right thing to do. But the good news is that this rule wasn't just made up out of nowhere to give the right answer. I mean, I guess in some sense, the original version of it, the Ryutaki-Nagi formula, the original paper sort of was made up to give a sensible answer. But going back to Lukowitz and Maldacena in 2013, we've understood that these sort of rules can be just derived just using a gravitational path integral. And this is a derivation that's sort of really very closely related and morally analogous to the derivation of the Bekenstein-Hawking entropy using Euclidean path integrals. So in some sense, it's slightly mysterious that this low energy effective gravitational theory sort of knows about these quantities, but there is a long history of it doing so, and it will in this case. So really the rest of this talk is just going to be showing how that derivation works in the case of this very simple model. And I'm actually going to sort of do this derivation really 3 times at increasing levels of precision. First going to just do the derivation at the level of the sort of topological part of the JT gravity action. And that's going to be enough to give us a formula for the page curve that's sort of the smaller of log k and the 0 temperature entropy of the black hole. Then we're going to get a bit more precise. We're going to look at the sort of geometry of the leading classical saddle. And that's going to get us the formula for the page curve I gave before of the smaller of log k and the actual Bekenstein-Hawking entropy of the black hole at that temperature. So including the finite temperature corrections. And finally, because it's such a simple model, we're actually going to be able to do the full path integral, not make any assumptions about being far away from the transition point or anything like that. And going to get this somewhat more complicated looking formula for the entropy that involves this function R that is really just the solution to an equation that you need to solve numerically or approximate or whatever. But this formula is in fact non-perturbatively exact in an appropriate limit, in the limit of a large black hole, basically. And it corresponds to the more naive page curve that we'll get from the simpler calculations with non-perturbatively small corrections far away from the transition and sort of a bigger correction that smooths out the sort of kink that you get at the transition. Okay, but before I can talk about any of that, we need to talk about how you actually compute entanglement entropies from a path integral. Because this is a sort of non-trivial thing to do, right? What a path integral lets you compute is things like expectation values of observables. But the von Neumann entropy is not an expectation value of an observable. But fortunately, it's closely related to some things which are called integer n Rayleigh entropies. So they're given by this formula. But the important part of this formula is this trace of the reduced state on the radiation to the power n. And that is, in fact, an observable. It's at the expectation value of an observable, but it's just the expectation value of an observable on n copies of the system. The observable in question is the Hermitian operator that permutes those n copies of the system. So this is something we can calculate with the path integral. And then we do this clever thing called the replica trick of just calculating this for arbitrary n as a function of n, and analytically continuing that function to non-integer n and taking the limit where n goes to 1. Take this formula, take the limit n goes to 1, apply L'Hopital's rule, you'll get the von Neumann entropy. So that will give us the answer we want. And the sort of key idea, the thing that's going to enable this sort of simple, very standard answer to give such a counterintuitive result that disagrees with the sort of Hawking answer, that when we do that gravitational path integral, we're going to include topologies that connect together the different replicas via space-time wormholes. Okay, so these different replicas are just independent spacetimes that are not directly connected using classical geometry, but they're going to get dynamically connected together in the bulk via space-time wormholes. Okay, so let's start with just the simplest thing you might want to calculate, which is the purity. It's called trace of rho squared. Okay, so this is a step towards being able to calculate general Rayleigh entropies and then eventually von Neumann. So to calculate this, we just use a Euclidean path integral. And the Euclidean path integral just has certain fixed asymptotic boundary conditions, standard rules for doing gravitational path integrals. And the boundary conditions are determined by the sort of formula for the state that we had before. And in fact, they're this. And so what we have is, because we have two copies, then we have two asymptotic boundaries. And the asymptotic boundaries have end of the world brane at one end in state I, and in the other end in state j. And then we're going to sum over I and j. So now we need to consider the different sort of geometries that can fill in those asymptotic boundary conditions. And the most obvious one is that you just have two copies of something that looks like the original black hole. Okay, so the first thing to note about this particular geometry, topology even, is that we have end of the world brane that up here is in state I, and down here is in state j. Okay, so this contribution is only non-zero if those two states are the same. It means this double sum over I and j is really just a single sum because only the diagonal pieces contribute. That means it gives us one factor of k from doing this sum, but we had a 1 over k squared out the front here just from the definition of the state. And so the overall answer, once you calculate everything and normalize by dividing through by the normalization factor, which in this case is again just two black holes, then the gravitational action all cancels between numerator and denominator, and we're left with a final answer of just 1 over k. So a purity of 1 over k roughly corresponds to a von Neumann entropy of log k. So this is the naive answer. As we take k bigger and bigger and bigger, the entropy just starts increasing and increasing and increasing, seemingly going on forever. Except that there's also another topology that matters. So what is this topology? Just the two black holes are now connected together by a space-time wormhole. Looks like this. So what is the gravitational action of this topology? Well, the Einstein-Hilbert action in 2 dimensions is just the Euler characteristic. The Euler characteristic of this thing is just a disk, so it's 1. But in the normalization, we have 2 disks, so it's 2. So that gives us an overall gravitational action that looks like e to the minus s0. So this space-time wormhole contribution is tiny. It's non-perturbatively suppressed in g-meter. But it's like a tiny, tiny instanton effect. But the important thing to note is that now this space-time wormhole in state I is just connected to another space-time wormhole in state I. It's not connected to one in state j. So that means when we do this double sum over I and j, there's no reason that they have to be the same. We get a full factor of k squared from the sum. That cancels out this 1 over k squared. And we find that this tiny space-time wormhole contribution doesn't decay to 0 even if we take k to infinity. Even if we take the limit where naively the amount of entanglement between the end of the world brane and this external reference system is infinite. Then the entanglement between the black hole and the reference system still seems to be finite. It still looks like roughly the Bekenstein-Hawking. Okay, so that's the purity. But yeah, there's an important point here, which is that this quantity, this calculation has some weird features. And the key one is that there was no reason to get these saddles that we needed to sum over I and j. We could have also found the same saddles if we were just computing the inner product squared of psi I and psi j, the overlap of these 2 different microstates. This wormhole topology is telling us that that is non-zero even when I and j is different. There's some tiny exponentially small overlap between these 2 seemingly orthogonal microstates. So that's a pretty reasonable thing to think happens in gravity. But there's a much weirder thing, is that if we just computed psi I psi j rather than its modulus squared, then we would find that that's 0 when I is not equal to j. We can just do the full path integral in this very simple model, and there's just no geometry, there's no way for the I to be matched up with another I when we're just computing the inner products itself rather than its modulus squared. It's called a factorization problem. We're computing something squared, and we're not getting an answer that's equal to the thing itself, what you get when you compute the thing itself and then square the answer. The explanation for this is just that the gravity calculation, at least in this simple case, is not actually calculating an inner product in a single quantum mechanical theory. It's actually calculating the average of an inner product across a whole ensemble of theories. On average, this inner product between the 2 microstates is 0, but it has small random fluctuations. And so its average modulus squared of its average, the average of its modulus squared is non-zero. Okay, but we're really not interested in the purity, we're interested in the von Neumann entropy. So let's go to calculating that. This is going to be our first very simplified answer. So in general, for trace row of the n to the n, there's a lot of topologies that can be imported. However, in the limit where k is sufficiently small or sufficiently big, then there'll just be, in fact, 1 family of topologies that dominates. For small k, the dominant thing just comes from n independent black holes. Just like for n equals 2, then it came from 2 black holes. This is just because this has the largest gravitational action. It has the largest Euler characteristic. So again, the gravitational action cancels between numerator and denominator. In this case, in the numerator, we only have 1 sum over I. In the denominator, we have n. And so we get a final answer of 1 over k to the n minus 1. This gives, we'll take this answer, you take its log, divide by n minus 1, analytically continue to n equals 1. You get an answer for the von Neumann entropy of log k. What about a very, very large k? Well, in this case, the dominant contribution is going to come from the sort of leading topology where all the different end of the world brane indices can be independent. And so it doesn't get suppressed by any factors of k. The answer for what that topology is this multi-boundary connected wormhole where they're all connected together like this. Euler characteristic of 1. In the denominator, we have something Euler characteristic of n. So this gives an answer of like e to the minus n minus 1 s naught. analytically continue, get the von Neumann entropy, and we get an answer of the entropy is equal to the 0 temperature entropy of the black hole. However, so far we have only considered the topological part of the action. JT gravity, you have other terms. So let's try and make this calculation a bit more precise. This is going to be our second attempt to the von Neumann entropy. And we're now going to actually look at the geometry of the leading classical saddle. Looks like this. So the key thing to note is that this geometry has a cyclic replica symmetry. If we commute all these different boundaries around in a circle, then we preserve the geometry. So what does that mean? It means we can quotient out by that symmetry and just look at one of these little wedges and imagine gluing this thing here to this thing here. This now almost looks like the original black hole, except that we have a conical singularity from this fixed point. In the limit where we take n goes to 1, i.e. to get the von Neumann entropy, that singularity vanishes and we get back the original unback reacted Euclidean black hole. But very close to n equals 1, you have a tiny back reaction. And it turns out that the von Neumann entropy is just given by the area of that replica fixed point, which in this case is the bifurcation surface. So this is the original trick that Lukowitz and Maldacena used to compute these sort of things. And it tells us that actually it's not just S0, it's actually the Bekenstein. Okay, so finally, this is going to have to be somewhat quick because I don't have terribly much time.
Sorry, you have 4 minutes.
Yeah.
Sorry, 4 minutes. Mm-hmm.
Yep. Okay, so we want to actually compute the sort of full von Neumann entropy using the full path integral. So now what I'm going to assume is I'm going to assume that both K and the Bekenstein-Hawking entropy are very large, but I'm not going to make any assumptions about their ratio. So what topologies matter in this case? Well, it turns out it's the ones that are planar, that can be drawn. It can be drawn in on a single sheet of paper. Why is that? So for example, this one we have a planar topology that contributes in this limit. But in this one, we have sort of a handle sitting here, and that handle decreases the Euler characteristic, and it means that this topology gets suppressed relative to this one by e to the minus 2s0. So we can ignore it. Here we have one where it doesn't have any handles, but we have overlapping things that's no longer planar. And in this case, you can count the number of independent end of the world brane states we sum over. We get an answer that's suppressed by 1 over k squared. Okay, so now we need to do this full sum over all the relevant topologies, and then we need to analytically continue the formula to n equals 1. So it turns out that's kind of hard, but there's this beautiful trick was found by Jembin that goes back to some tools from free probability. And that involves using this thing called the resolvent matrix. It's just defined here, just the inverse of lambda minus rho, but it can equivalently be written as a sum over powers of rho to the n. So graphically, it corresponds to doing a sum over path integrals with different boundary conditions with different numbers of boundaries. Or in the bulk, summing over all bulk topologies with the correct boundary condition. So the clever trick is that we can just reorganize this sum over topologies in terms of the number of boundaries, other boundaries that the first boundary is connected to. So this term is including all the terms where the first boundary isn't connected to any other boundary. And so that just looks like one boundary sitting here, and then just a copy of R, an arbitrary number of boundaries doing whatever else they like. And then we have higher powers that look like this. The path integral for these topologies can be computed. It's just given by this slightly complicated formula. And the nice thing is that its dependence of n just appears in the power of this function. The other dependence of n just comes from the power of R. Again, it's just power of n taken to the nth power. And so we can just do this infinite sum by evaluating it as a geometric series. And that gives us this quite nice equation for R, which here is R here is the trace of the matrix we had before. And the great thing is that this resolvent, this trace of the resolvent matrix, in fact, encodes not only the entanglement entropy, but in fact the entire entanglement spectrum of the state. Why is that? Just by using Cauchy principal value theorem, then the sort of density of states is just given by the imaginary part of this resolvent. So if we can solve this equation, we're basically done. We have everything you possibly want. You can't actually quite explicitly solve it, but you can certainly solve it numerically. And it's also, there's a very good approximation that consists of taking just a thermal spectrum, cutting that thermal spectrum off after k eigenvalues, and then just shifting it slightly. I know I'm basically out of time. I will be done in like one more slide. Just to make some comments about the final answer, you can actually calculate the page curve up to really quite small corrections, order G Newton near the transition, and in fact, far away from the transition up to exponentially small corrections. And in fact, you can compute those exponentially small corrections. Near the transition, you get pretty large corrections to the sort of naive page curve that smooth out the transition. These corrections are actually significantly enhanced compared to sort of naive non-gravitational time models. The enhancement comes from the fact that you have fluctuations in the energy of the black hole. So here is just the actual page curve, numerical in black, our approximation is dashed, and compared to sort of a naive page curve you'd see for something like a random state. So really very, very final slide. Why bother doing this much more complicated calculation when we basically already got the right answer for the page curve just by looking at the leading classical saddles? It is, after all, just a stupid toy model. The first answer is because we could, and it was fun, and it involved a lot of cool tricks. The more reasonable answers is that there's some interesting physics in these enhanced corrections. Some recent papers by Mao from Wang and Dong and Wang that talk about the same phenomena in higher dimensions for related quantities. So it's pretty universal physics, not just in this toy model. These non-perturbative corrections to the page curve very far from the transition are also really crucial to making the result work. Goes back to a paper by me and Patrick Hayden from a couple of years ago. And it's also evidence that we should really take this full gravitational path integral seriously. Like it's really, beyond just some leading classical saddle, it's really giving us sensible answers. And in fact, the sensible answers it's giving us have very close correspondence with the answers you get from random tensor network calculations. So that's some reason to think that we should really take seriously the sort of random tensor network toy models as genuinely saying something deep about ADS, CFT, and quantum gravity. So yeah, sorry, I ran a couple of minutes over. Thanks very much.
All right, thank you. So let's thank the speaker for a very nice talk. And we have a few minutes for questions, please. Please raise your hand. But there got to be some questions. Okay. Okay, Ronak Soni. Oh, Edward Witten. Yeah, Edward Witten, please.
I'll defer to all a second. Okay, that's Sony. Tell Sony to go ahead first.
Ronak Soni, please.
Hi, sorry. Why should you not, so in the replica, in the Renyi calculation, there's Zn upon Z1 power n. And why should you not consider connected topologies in the denominator?
Yeah, it's good. So in the denominator, all the connected topologies are suppressed by either powers of k or, well, they're all suppressed, in fact, by both powers of k and powers of e to the s. So the limit we're working in, where we take k and e to the s naught both to infinity, but keep the ratio arbitrary, then yeah, there's no non-trivial contributions to the denominator.
All right, thanks.
Okay, Edward Witten.
Can you say a word about what you meant at the end about how the gravitational path integral gave answers similar to random tensor networks?
I'm afraid I think my internet went a bit bad there, but as I understood the question, it was about this connection with random tensor networks that I mentioned on the final slide. Is that right? Yeah. So the basic answer is that this sum over planar topologies. So we can, in random tensor networks, you can do a calculation by using this thing called Schur-Weil duality, where you replace integrals over unitary ensembles by sums over permutations. And the permutations involved are basically in one-to-one correspondence with these planar topologies. They're both classified by what's called non-crossing partitions. And in fact, there's a more precise statement, which is if we look at the sort of fixed area state or fixed energy version of this calculation, we look at sort of microcanonical rather than canonical version of it, then the full sum over topologies gives exactly the same answer as you get with just looking at a random state. And that generalizes in sort of higher dimensions to fixed area states, you get exactly the same thing you'd get from a random tensor network. So this is discussed in Appendix E of our paper. Can maybe, yeah. But basically the different ways of gluing together a gravitational path integral correspond to the different terms in this Schur-Weil duality sum.
Thank you.
Okay, Andy Strominger.
Yes, so Ashok-san computed universal log m corrections to the entropy in 4 dimensions, which are determined just by the massless spectrum of particles. And so one would expect log m corrections to the page curve. We looked at corrections using the island rule prescription in some 2D models and got answers which at the log m level seem to be self-inconsistent. I'm wondering if you think that this formalism can be used. But the results we found could just be attributed to the model isn't consistent. But one wouldn't want to say that about 4-dimensional black holes in the sky. So I'm asking whether one can get log m corrections which shouldn't depend on microphysics out of this kind of analysis.
I would hope so. I'm afraid I haven't read your paper carefully enough to be aware of the details of the problem. Certainly hope you would. Yeah, like you know, there's a question of like sometimes the island rule itself is too naive, but the replica trick will give you the right answer. So certainly. Yeah, it's possible that's the honest answer is I don't know. That's a very interesting question. I'll have to look at your paper and
well, I'm not really asking about my paper.
Yeah.
I'm happy with the resolution that our paper is trying to describe a model that doesn't exist. I'm more asking whether it might or might not be. I'd be happy if that were not the answer. But the more
I would say in this model
is whether one can get it for 4-dimensional Schwarzschild, log m corrections to page.
Yeah, the answer is, I mean, yeah, within this model, you obviously don't have any massless particles, and so it works out right. I would certainly hope so.
I'm talking about the real world.
Yeah, I know. I haven't done the calculation in the real world. I would hope so, but who knows without doing the calculation.
All right, let's thank the speaker again. And we're going to move to the next speaker. The next speaker is Douglas Stanford from Stanford, who is going to comment on replica wormholes.
Okay, thanks. Let me get this going. How does that look?
Look great.
Okay, great. Well, thanks very much to the organizers and for the opportunity to speak. This talk is based partly on work that with Jeff Pennington, Steve Schenker, and Zhenbin Yang, and partly on some work that's in progress. So what we're going to do is discuss 2 questions, 2 sort of unrelated questions having to do with replica wormholes. The first one is this: how can acting in the radiation create a particle behind the horizon? If the radiation of an old black hole describes the island behind the horizon, then it should be possible. But how exactly does geometry show us that it works? So that's the first question. And the second one is, to what extent do the replica wormholes involved in the page curve require an ensemble interpretation? Sometimes these space-time wormholes, Euclidean wormholes, do require an ensemble interpretation. Is that the case here, or is it not? Okay, so that's the plan. So first part, how to create a particle behind the horizon. And the main reference for this part is this paper. But I'd also like to highlight this earlier paper here, where a tool called the PETS map was introduced to holographers, and also a beautiful paper by Yiming Chen with another method of solving the problem that we'll discuss. So I'm going to continue working in this very simple toy model that Jeff described. And I'll remind you that here's the black hole solution, the basic black hole solution in Lorentzian signature on the left and Euclidean signature on the right. The black dot here is the horizon, and we can think of a horizontal slice going through here as a spatial slice, which is common to both the Euclidean and Lorentzian geometries. So in particular, the region between the black dot and this blue end of the world brane, that's like a spatial slice of the region behind the horizon. This is like the spatial slice of the region inside the black hole. Okay. So we're going to be working in Euclidean signature. So we'll be drawing diagrams like the one on the right here. And what is our goal? Our goal is to create a particle behind the horizon. And we can represent the action of a particle creation operator behind the horizon as giving us a space-time like this. This is the kind of space-time that we want to create. There's a branch cut here that separates versions of the interior with and without this extra particle. The particle is drawn with this dashed orange line. The question is, how does this happen? How do we actually produce a space-time like this by acting in some way on the radiation? And I should warn you that I feel like our understanding of this is not optimal, but I'm going to tell you kind of what we know, what we think we know, and maybe somebody can push it further. So here's the basic picture. Somebody acts with a special operator, very finely tuned in the radiation system. And then when you go to compute the matrix element, some matrix element of that special operator, the dominant contribution to it comes from a wormhole geometry. So here's a picture of the wormhole geometry. We'll discuss a little bit more about it later, but it has two, for the moment, two asymptotic boundaries. One of them corresponds to our actual physical black hole, and the other one corresponds somehow to the radiation, or to a quantum computer acting on the radiation. And okay, so there's this particle here, which is the dashed orange line, which is going on this Euclidean trajectory between the two boundaries. All right. So this wormhole, at least topologically, can be rewritten by gluing together two geometries, like I showed on the right here, gluing them together along their branch cuts. And if we focus on the rightmost subdiagram, then that's actually the space-time that we wanted to construct. So that was our target. That was the thing that we wanted to understand how it arises. And here we see that it arises as sort of half of this wormhole. The wormhole appears when you act with this special operator. So if we can think about this wormhole, I guess, sort of like we're computing some funny observable. And the funny observable has a dominant contribution from some kind of instanton effect. But because of the large amount of entanglement, the large K parameter in Jeff's talk, this instanton effect is actually not suppressed. It's order 1. Okay. So this is the basic picture. And what I'm going to try to do is answer a couple of obvious follow-up questions that you might have to this picture. So one question, what operator are we supposed to act with on the radiation to make this happen? And then what does it even mean for a wormhole to connect to a quantum computer? And then finally, this one is more of a comment than a question, but this equation here is true topologically, but not geometrically. What's going on with that? Okay, so let's go to this question first. What operator are you supposed to act with on the radiation to make this happen? So a very simple example is to think about a case where there's just two states of the total system. So the total system consists of the black hole and the radiation. And state 0 is a state, an entangled state of the black hole and the radiation with no particle behind the horizon. State 1 is the same thing, but just with a particle added behind the horizon. So these are both entangled states of the black hole and the radiation. State 1 has the particle, state 0 does not. And our goal is to turn state 0 into state 1. And while it's obvious that this operator here would do the job, but this operator is not allowed because it acts on the total state of the system. It acts on the tensor product of the black hole, B, and the radiation, R. And what we want is an operator that acts only on R, only on the radiation. So this one, while it would do the job if we were allowed to use it, is not allowed. Okay, so there's a very naive guess for how you can fix it. You can just take the trace over the black hole of the naive operator and then multiply it by some constant. So this is, I feel, a sort of ridiculously naive proposal. It's like, here's an operator that works. You want an operator that acts only on the radiation? Well, I'll give you one. I'll just trace it over the black hole. But actually, this sometimes works. But a choice of operator that works better, more generally, is a sort of a fancier version of this, defined using this tool called the PETS map. And for details on that, I'll refer you to the paper I cited a couple slides ago. But for this particular case, what it works out to is the following. We take the ridiculously naive operator that we had written down before, and then we multiply it both on the left and the right by this operator sigma to the -1/2, where sigma is a similar trace over the black hole of the projector onto both of the states that we're interested in. Okay, so that's the operator that we're supposed to act with on the radiation. And when you compute matrix elements of this operator after the page time, a wormhole geometry dominates the computation. And I'm not going to show this to you in detail because it's very similar to the discussion of the entropy in Jeff's talk. In particular, the interplay between the K parameter and the e to the -s0 parameter is the same. I also want to mention that this operator is highly state dependent in a way that was anticipated in earlier work by Papadopoulos and Raju and by Verlinde and Verlinde. Okay, so next question. What does it mean for a wormhole to connect to a quantum computer? And the answer to this question is not going to be very satisfying, but it's the best that we can do at the moment. So the operator that we're acting with, this PETS map operator, acts only on the radiation. That was the rule, has to act only on the radiation. But it involves, in various places, a partial trace over an operator that acts on the black hole. So there's some version of the black hole inside this operator. We're tracing over it. And you could imagine that to implement this operator, a quantum computer might simulate a second copy of the black hole. And it's this simulated copy of the black hole that can connect by wormhole to the physical black hole. That's actually what's happening in these wormhole geometries. Okay, and then the final question, this equation, this basic picture of the wormhole here inducing the geometry that we wanted on the black hole side. This thing is true topologically, but it's not correct geometrically. Like the conical angles don't work out at this point. So fixing this is actually the role of these factors of sigma to the -1/2 in the PETS map. So to explain this, it's helpful to think about this PETS map operator using a type of replica trick, where we temporarily define a more general operator with powers sigma to the power n, and then we'll take a limit, n goes to -1/2. And if you work out the type of wormhole that forms for integer n, it looks like this pinwheel diagram, where the shaded blue part is the part that's associated to the physical black hole, and the rest of it is associated to either this factor here or the factors of sigma, n factors of sigma above and n factors below. And now there's an honest geometrical statement, which is as you take n to minus 1/2 of this geometry, then the shaded blue region becomes exactly what we wanted. Okay. So that's the end of the first part. Now we're going to switch gears to a different topic. And I want to highlight some recent work by these authors, which addresses the same type of questions, but from a somewhat different perspective. So it came as a surprise about a year ago that semi-classical gravity can compute the page curve. And over the past couple of years, also that it can compute average values of late time correlation functions. Previously, I guess it was thought that to compute these things, we would need a bulk description that has manifest microstates. I certainly thought that. But in retrospect, we may have been sort of misunderstanding what semi-classical gravity describes. And so here's a possible improvement on that picture. Maybe it's right, maybe it's wrong, I'm not sure. But the proposal is that gravity describes an ensemble average of quantum systems, including finite entropy effects, over an ensemble that may or may not be well defined. So it seems kind of obvious that a simple gravity description doesn't have enough stuff in it to fully describe a large, complicated quantum system. But what seems to be true is that gravity doesn't just throw out the fine-grained, finite entropy, intrinsically quantum grainy features. Instead, it sort of averages over them, and that's subtly different. So sometimes people like to think about an analogy. They say gravity is a little bit like hydrodynamics. But it seems like maybe a better analogy would be gravity is sort of like hydrodynamics, but also with some kind of average description of Brownian motion, something that you would have thought required a molecular description. Anyhow, so that's some proposal. And there are some simple pure gravity theories where souped up semi-classical gravity, basically simple gravity, is all there is. And such theories are fundamentally dual to ensembles. So JT gravity with defects, maybe 3D gravity. But in string theory, semi-classical gravity is not all there is. We have strings, we have branes, and frankly, we have more work to do to really understand black holes here. Some ideas along this direction include fuzzballs, eigenbranes, baby universes. This stuff is really interesting and I think really important, and I'm not going to talk about it in the rest of the talk. Instead, what I'm going to do is try to explore a little bit more the interplay between this ensemble average picture and the page curve computation. So I'm going to start by reviewing a sort of old story, the connection between space-time wormholes and ensemble averages. And I'll do this in the context of ADS CFT, and to draw pictures, actually, we'll use ADS2 CFT1. So in this version of ADS CFT, the way the dictionary works is that time contours of the boundary theory become boundary conditions to be filled in by the bulk theory in some way. So my favorite example of this, a simple example, is suppose we're just trying to compute the thermal partition function in the boundary theory, z of beta. That's trace e to the minus beta h in the boundary theory. Well, the time contour associated to z of beta is a circle, the thermal circle of length beta. That's the contour of the system that you put it's the contour that you put the system on in order to compute this observable. And in ADS CFT, we think about that circle as a boundary condition that should be filled in with gravity, like some kind of geometry like this, which has a circle as a boundary. Okay. Now let's consider the quantity z of beta squared. The time contours to compute that are just two copies of the same thing. So two of these circles here, two thermal circles for two independent copies of the system. And because z of beta squared is, well, it's the square of z of beta, then we might expect that we should just fill these in the same way that we did in the first step. And we'll just obviously get the square of the previous computation. But, and this is where it gets interesting, there can also be contributions from a connected geometry, a wormhole that connects together in the bulk these disconnected boundary conditions. And there's just a flat out contradiction between saying that z of beta is equal to this and saying that z of beta squared is equal to this. So one possible resolution of this is to say that what gravity is computing is an ensemble average. So we invent some angle brackets and put them around all the observables. And then we say there's no contradiction between the statement that the average over some ensemble of z of beta is given by this geometry, and the average over that ensemble of z of beta squared is given by these geometries here. What it means is that the variance in this ensemble of z of beta is given by the wormhole. So as I said, this is really an old story that goes back to work of Coleman, Giddings, and Strominger, and in the context of ADS-CFT, to Maldacena and Maus, Arkani Hamed, Polchinski, and Orgera. And qualitatively, the flavor of the discussion around wormholes has been, roughly speaking, that wormholes are bad. They represent some kind of failure of factorization, and we need to figure out how to cancel them or remove them. So they're sort of viewed in a negative way. So over the last 2 years, we've seen something sort of positive come out of these wormholes, though, which is that they give the right answer for the ensemble average of noise in various quantities due to the underlying discreteness of quantum mechanics. I'm not going to describe these in detail, but because of the discrete spectrum of states in the quantum system, certain observables have a type of irreducible quantum noise, random, erratically fluctuating curve that's sort of a little bit like the trace of a particle undergoing Brownian motion. And these geometries, these results by these various authors, compute quantities that basically give the ensemble average of that quantum noise. So they accurately compute, they give the right answer for something, but it's not an individual erratic trace. It's some kind of average of that. So they're doing something good. But it's something good that has to be interpreted in the context of an ensemble. So here's the question we want to address. Do the replica wormholes for the page curve need an ensemble interpretation like this? So let's start by setting up a case where the replica wormholes for the page curve are relevant. So this contour here is going to take a tiny bit of explaining, so let's do that. What we have is a state of a black hole interacting with a bath, evolving forwards in time. So these semicircular arcs here of the black hole system and of the bath system represent the Euclidean state preparation. They're preparing some kind of thermal state of the bath and some kind of thermal state of the black hole. And then we evolve forwards in time. The red dashed lines indicate interactions between the bath and the black hole system. To make the drawings a little bit simpler, we're using this two-sided black hole. So the black hole starts out as two entangled copies, and the bath also starts out as two entangled copies. And we're interacting one copy from each system and letting them evolve forwards in time. So that's the time contour for what we're describing. And if you want to think about a bulk picture, then it looks roughly something like this. The black hole geometry gets filled in by this two-sided black hole that Juan described in his talk, where we're evolving forwards on one side of the black hole coupled to the bath. Okay. So we start out with a black hole in a pure state and the bath in a pure state, but we evolve forwards in time and they interact and the entropy increases. So suppose we want to compute the entropy, and to make life easy, let's imagine we want to compute the Renyi entropy. Trace rho squared for the two blue dots, so the total black hole system? Well, that's given by a time contour that looks like this. If you look at the southwest corner of this diagram, it looks like the time contour that we drew in the top left. And they get glued together in this interesting way. 2 copies of the black hole, 2 copies of the bath. The red lines indicate interactions. At late times, the dominant way of filling in these boundary conditions, these time contours, is a wormhole. So geometry wants to fill these things in with a wormhole at late times. The wormhole connects together the 2 copies of the black hole. So this is the replica wormhole of the page curve. But notice that it's actually okay. There's no obvious contradiction yet because the different boundary conditions are themselves coupled together by the interactions. So there's no immediate problem with a wormhole connecting the 2 black holes because the boundary conditions are also connected. So we don't yet require an ensemble interpretation. But what happens if we replace the interactions with the bath in this picture? So the interactions between the 2 black hole systems mediated by the bath. What happens if we replace the interactions with the bath by some fixed operator insertions? So that's the time contours that are drawn here. We've deleted the bath systems altogether. And we just have a collection of insertions of these V operators and W operators. Notice that now these time contours are factorized. So there's no interactions between them. We just have operator insertions. So first of all, what does this quantity mean? And second, is the wormhole still there? So first, let's address what the quantity means. So each of these 2 identical time contours computes the inner product of 2 states of the black hole. They're the 2 states of the black hole that are left behind after 2 different specific histories of Hawking radiation. So this contour here with the Euclidean part and then the Lorentzian part going forwards and back, that represents the inner product of these 2 states where we have Euclidean state preparation. And then we evolve forwards and condition on the black hole emitting a particular sequence of Hawking radiation. So you can make a pure state of a black hole by requiring that it emit a particular sequence of Hawking quanta at particular times. That data is labeled by these V operators. And we take 2 different sequences, a sequence of Hawking radiation labeled by these V operators and a sequence labeled by these W operators. And we can consider the inner product of the state of the black hole that's left over after those 2 different evaporation histories. So we'll denote that as the inner product of W with V. So in Hawking's calculation, if these histories are different, then the leftover states will be close to orthogonal. And I'm going to suppress a little detail here and say that basically the inner product will be 0 between these states. At late time, though, if we can have lots of different histories of Hawking evaporation, then this is too many orthogonal or nearly orthogonal states. For a real quantum system with finite entropy, inner products between states like this will be sort of erratic. They'll depend on W and V in an erratic way. The typical value will be that the square of this inner product is of order e to the minus s. So it's small but non-zero. And actually this value of e to the minus s is necessary to get the page curve. Roughly, trace of rho squared is related to a sum over W and V of this quantity, as Jeff explained in a somewhat simpler context in his talk. So the e to the minus s value of this inner product squared is closely related to getting the right answer for the Renyi entropy. Okay, so second, is the wormhole still there when we try to compute this quantity? And the answer is that it is still there. And what gravity gives is the following answers for this quantity. So the inner product of W and V is computed just by a disk topology. This is basically Hawking style calculation. And that gives something that I'll approximate as Kronecker delta of W and V. But the square of this inner product gives that contribution, 2 separate disks, plus the wormhole. And this is very similar to the wormhole that appeared for the Renyi entropy computation. The replica wormhole that appeared there, it gives a contribution proportional to e to the minus s. So this e to the minus s term is good because it gives an answer that's consistent with the page curve. And that's not really too surprising because it's kind of the same wormhole that's appearing in both cases, a wormhole connecting these two copies of the black hole. But now we can see that there's, again, just a flat out contradiction between the answer for this quantity here on the left and the answer for this quantity here. So in order to interpret these computations, we need to go back to some kind of ensemble interpretation where we introduce extra angle brackets and we interpret the gravity as computing the ensemble average of either this inner product or the square of the inner product. So the little summary of this result is that these inner products that underlie the computation of the Renyi entropy are given by the same wormhole as the Renyi entropy was, but, well, that's in quotes, but now we need an ensemble interpretation. Okay, so let me just say a little bit about the wormhole. You can work it out pretty explicitly for, let's say, JT gravity coupled to matter fields. In the microcanonical ensemble, this wormhole is a classical solution. And the solution's kind of hard to visualize, but we can get a sense for what it's like by studying distances between different points on the boundary through the bulk. It gives you kind of a sense of what the geometry looks like if you know the distance between points on the boundary through the bulk. So let's examine 3 different points here on these boundary time contours, point 1, point 2, and point 3. Then the result in this solution is that points 1 and 2 are close together. And the distance between them is this function here. And if T1 is close to T2, then the points are close together. And actually, this function, for those of you who've been studying ADS2 will recognize it. This is the distance function that you get on opposite sides of the thermal field double, this 2-sided black hole that Juan mentioned. So
sorry, Doug, 4 more minutes.
Okay, yeah, thank you. So these 2 points feel as though they're on opposite sides of a thermal field double. In particular, they're close together, even though they're on different disconnected boundaries. On the other hand, points 1 and 3, they kind of look like they're close together on this diagram here, but they're actually far apart due to a back reaction effect associated to the W and V operator insertions. So actually, they sort of feel like they're on opposite sides of what you could call an out-of-time order correlator time fold. The distance function looks like this. It has a piece that's small if the times are equal, but then it has a piece that's big if the times are equal, as long as the times themselves are large. So qualitatively, these 2 sides of this contour are far from each other, but they're close to the corresponding contours on the opposite copy. Okay. You can also compute this thing, not classically, but exactly using a quantum description of JT gravity. And an important ingredient in that is this rectangle propagator that takes you from a geodesic of length L to a geodesic of length L prime. It has some expression involving Bessel functions. I'm not going to go through this in much detail, but following work by Phil Saad, there's a really beautiful way of doing these kinds of calculations where you just glue together these rectangles. You're gonna make this cylindrical wormhole, and to make it, you glue together a couple of rectangles and integrate over the lengths appearing in this propagator. One advantage of going through this quantum calculation is that you find that the answer precisely matches an ensemble average computation in a collection of theories described by ETH statistics. So you can get a very precise answer, and that answer very precisely matches a reasonable definition of an ensemble average. Okay. So let me just conclude here by restating the question and some sort of partial answer. So the question we've been discussing is the following. do the replica wormholes for the page curve need an ensemble interpretation? And well, if you treat the replica wormhole computation as a black box, then no, because the different boundaries are coupled together. So there's no immediate contradiction with a wormhole connecting them. But you can look inside this black box at quantities like the square of the inner product that are sort of building blocks of the Renyi entropy. And it seems kind of obvious that the simple gravity description that we're using here is not rich enough to describe the true form of this inner product squared, which would depend on W and V in some complicated, erratic way, depends on the quantum noise. A less ambitious theory than gravity would just break down if you ask it about this type of quantity. But gravity doesn't break down. Instead, it gives the answer for an ensemble average. It sees no problem with computing this kind of quantity. And it says the answer gives a particular answer, which is the answer that you get in an ensemble average. So here's a key question that I think we need to think about. In cases where there's no ensemble, so in the bulk dual to n equals 4 Super-Yang-Mills theory, are replica wormholes right? Now, the Renyi entropy or the von Neumann entropy, these quantities are self-averaging. So an ensemble averaged answer is going to be close to the right answer anyhow. So at the level of the answer, we're going to be close to the right answer, even if we compute something in a fictitious ensemble. But we could ask for more. We could ask, are replica wormholes actually the first term in some computation that can be systematically improved? And if so, I hope it's true, but if so, what is the next term? Okay, so thanks very much for your attention. I'll stop there.
Great, thank you, Douglas. So let's thank Douglas for a very nice talk. You can, and we have time for a few questions. Let's see. Okay, so we have only 10 minutes for questions. Douglas, do you see raised hands? Would you like to pick your question?
Let me see. If I do this, has it gone? I'll just stop the share and see.
Yeah, do you see raised hands? Would you like to pick your questions yourself?
Oh, wow, I'll just go in order, right? Suvrat.
Okay.
Yeah, okay, thank you. Thank you for the nice talk. I had a couple of, actually it's a two-part question about the first part of your talk. In the first part, you were talking about these operators that could create particles behind the horizon. But I thought the interesting thing would be for the operators to be unitary. Because, I mean, just to say, you can always find an operator that acts in this room and that creates the room in the Andromeda galaxy. But that doesn't mean anything because you're only allowed to act with unitary operators, and just some operator that uses the entanglement may exist. So that's the first question, if you're looking for unitary operators. And second, I asked you this earlier, but I'm still not clear about the answer. In this work with Kyriakos, we did find such unitary operators that would act on the radiation and create a particle behind the horizon. And the way we did it was we created a particle outside the horizon, and then we pushed it behind the horizon by conjugating it with the modular Hamiltonian. In our case, that was just the Hamiltonian, because we were looking at typical black holes. So I'm wondering if it really turns out to be the same thing, or there's actually a distinction between this and this.
Okay, thanks. Yeah. So the first question, the way I like to think about this is the following. This PETS map does not take unitary operators to unitary operators, but it does take Hermitian operators to Hermitian operators. And if you have a Hermitian operator, you can exponentiate it and make a unitary. So if you have a Hermitian operator that does close to the right thing, then we can make a unitary operator out of it. So regarding the second question, I think that the approach that you're describing there is probably closely related to the nice paper by Yiming Chen, where he used something similar. It looks superficially a little bit different from the strategy of the PETS map, but maybe there's some deep connection between them. I don't know.
Okay, sorry, but just to ask about the unitary once more. I mean, as I said, one can find a Hermitian operator in this room that creates the moon in the Andromeda galaxy.
No, that's not true. That's not true. I don't think that's true. It's not Hermitian. If you could do that, then you could take a small amount of it and exponentiate it, and then sort of slightly create the moon using a unitary operator.
We can chat more, but I mean, you can certainly find 2 Hermitian operators at least, but we can talk more about this.
Yeah, the weird operators that create elephants somewhere else are not Hermitian.
Well, I think you could do a lot with Hermitian operators because but we can talk more. I mean we can talk more offline. I think if you
anyhow
the question of phases. So yeah, but okay. Maybe I should.
Ahmed.
Can you hear me?
Yes.
My question is about these black holes where you sort of projected on the state of the Hawking radiation.
Yeah.
Is it correct that if you time evolve this state backwards, the black hole probably has shock waves and firewalls and it's just
yes, it has shock waves.
Sorry, just shock waves?
Well, I don't know if you call a shock wave a firewall, but it has shock waves.
Okay.
But we don't need to use that to do the computation. We just use the forward evolution.
I see. Okay, thanks.
Greg.
Yeah, I had a simple technical question. In your replica approach to calculating the PETS map, why is the analytic continuation in N unique?
Well, it's the same kind of discussion as for the von Neumann entropy. And to do it really precisely, well, okay.
The point
to
is,
do it really precisely, we have to do it.
Sine pi z is an analytic function that vanishes on the integers.
Yeah. So okay, so there's.
But sine pi over 2 is not 0.
There's a. Okay, so the place I'm most confident about this is in the simple model that Jeff described. And there you can do this computation very precisely and show that there is a representation of this integer n quantity that can be nicely continued in n. So
that doesn't mean it's unique.
Well, no, I think it does mean it's unique, right? So there's a certain amount of uniqueness that's provided by Carlson's theorem. And so if we do have a nice representation, then it's the unique one with that doesn't grow exponentially in n.
Well, you need to know something about the asymptotics in n. And the point is that you can multiply sine pi z by any entire function. And so
it's similar to the entropy computations where this thing is not growing in n. So
along the positive real axis. But
right.
But what I'm saying is that it's a little different with the half.
With the half?
Yeah, because you can multiply some. Well, okay. Never mind.
Well, the half is okay because we have a nice continuation in n just for general n, like complex n. There's a way of writing this where you have a nice continuation in n, complex n, and then n equals minus a half isn't so weird.
Probably you mean a nice continuation in a half plane or something. Don't you, Douglas? That's what Carlson's theorem usually involves.
Oh, yes, you're right. But I think it continues to n equals minus a half for this observable. The analog of the half plane would include minus 1/2 because we have a copy of this density matrix inside the operator. So the total number of these things is like 1 plus 2n. So the limit n goes to minus 1/2 is like the limit n goes to 1 in the von Neumann entropy. Sandeep?
Yeah, hi Douglas. I want to ask you a question which is a little bit tied to the past, so forgive me. A lot of people in the conference and you too evoked the similarities with the wormholes discussed by Coleman, Andy, and Steve Giddings and so on. But I think there's a crucial difference, it seems to me. In those cases, ultimately, there was no loss of unitarity. And it was essentially because, the baby universes, since they don't carry off any energy or momentum, have to result in ultra non-local interactions, as a result of which you can rephrase that in terms of a local unitary theory, but with adjustable coupling constants. Here, it seems wormholes are behaving very differently. Can you comment on this?
It's similar. It's just that the analog of the adjustable coupling constants is like in the boundary theory, not in the bulk. So the bulk description is describing the boundary ensemble, but it's structurally, I think, quite similar to the Coleman story.
But there you didn't lose unitarity. You didn't have to go.
You don't lose it here either. It's an ensemble average of unitary theories. So the same as with Coleman. Schumit?
Hi, I think you probably already answered my question. I was going to ask, is there a clear notion of unitarity in a theory which is an ensemble average? I mean, can I get probability?
No, there definitely is. There's the statement that the individual elements of the ensemble should be unitary theories.
And then if I get calculate something like a correlation function and look at analytic properties, they would be similar to what in usual field theories would have following from unitarity?
Well, I guess they won't have all the usual properties, like it won't have cluster decomposition, but it will have some of the usual properties, like 2-point functions at very late time won't decay. Raphael?
Yeah, thanks for the great talk. I really like this picture of the black box that you suggested at the end, where we need no ensemble interpretation if we just look at the output, such as the page curve. But if we look inside, it looks like we do. And I just wanted to see if you agree whether this has something to perhaps tell us about the AMPS paradox and the smoothness of the horizon, in the sense that it's only when we look inside the box that we see the smooth horizon. We have these pictures where we're sort of reaching behind the horizon, extracting the information. But that's precisely the picture in which we would need an ensemble dual. And so in a sense, the dual doesn't actually have the unitarity property that AMPS assumed. Whereas if you work with a box and don't look inside, then that's great, you get the answer you wanted, but you can just go ahead and still apply the AMPS argument to that.
You're asking whether there are firewalls in non-disordered theories?
Yeah, I'm asking whether you view that as a reconciliation between the appearance of a smooth horizon inside the box and the AMPS argument.
Yeah, well, I think it's basically A equals RB is the kind of where we're at right now, and making sense of that, and it seems to sort of work. I mean, you could ask, the other part of the answer to your question is that we're now trusting the gravity description more. So you have to ask it the question that you actually want to ask, but then you get to trust its answers. So I think if you set up, if we actually ask the question about what happens when you fall across the horizon, then we should take its answer seriously. And the answer is that for most reasonably formed black holes, then the horizon is smooth.
Well, that's indeed the answer we get, but if that's the answer that's computed for an ensemble average of dual theories, of true quantum gravity theories, then presumably we don't believe we actually live in a world described by an ensemble average.
So suppose we think that gravity is computing the ensemble average of some honest theories, then we can ask a question like, if I fall across the horizon, do I measure a firewall in the average of these theories? And the answer is no. And I could ask some question like that would be sensitive to fluctuations in the ensemble about whether I find, in other words, if you believe gravity is computing the average in some ensemble, then computing the horizon is smooth in that is enough.
I think that presumes that is a well-defined question in the boundary theory, right? In other words, so far what gravity has given us are predictions for things like the thermal entropy, and then now the page curve, so the microcanonical entropy of the radiation, all of which are clearly objects that have to exist in the full theory because they are asymptotic.
I think that's a fair objection. Yeah.
Thank you.
I think we're out of time, so I'm not sure if I should take further questions or not.
Yeah, we're going to have 2 more hours of discussion, maybe. So Jeff, I just contact him. So one more question.
Okay, Andy?
One more, yeah.
Yes, beautiful talk. I haven't followed all the details. I have a general question, which is, so there's an ensemble, you're talking about theories in which there's an ensemble average going on. But when you have an ensemble average going on, you would think it would wipe out the page curve. would destroy the correlations. So how is it that in a theory which produces ensemble averages, there's a formalism which produces ensemble averages, we're also getting a formula that gets the page curve?
The ensemble averaging happens at the end of the computation. So the type of thing you're worried about is if you do an ensemble average at an intermediate step. We're trying to compute minus trace rho log rho. If I compute the average of rho and stick it in that formula, I'll get a bad answer. But if I do the averaging at the very end, then I get a good answer. And what we're learning is that you just actually have to ask gravity the question very honestly. Not, I want to compute rho in gravity, and then I'll do the rest of the math. You have to say, I want to compute trace rho log rho in gravity. And if you do that, then you get the right answer. Or at least you get an answer that's consistent with an ensemble of unitary theories.
So it's kind of like your answer to Raphael's question. Yeah.
Well, my answer to Raphael's question ended up being that I thought his objection was kind of fair. So I don't know.
All right, let's now thank Douglas and all the speakers in the session again. And we are going to take a 5-minute break and then meet again for a 2-hour discussion, 2-hour panel.
Hi, Malcolm.
I've unmuted myself and you should be able to see me.
Malcolm, I'm going to make you a co-host.
Okay.
Anastasia, thank you so much for chairing the session.
I'll do my best. Now, one thing that I can't tell from here, how do I see who is raised their hand and what do I do about it?
Okay, so if you go to the participant window,
yes,
you should be able to see everybody. So right now, Sumit Das has his hand raised, I think from the previous session. I've now lowered it. Can you see?
The answer is no, I can't see anything now.
Okay. Can you see the participants?
So I can see you and I can see me and I can't see anybody else at the moment.
Okay. So at the bottom of your page, there's a list of buttons.
Oh yeah, participants.
One of those is participants. Click on that. It should open up a window.
Okay, I've got it.
Great. So if somebody raises their hands, you'll see a little blue hand.
Right.
That's raised. Floats to the top of the list.
Okay.
In order. So then there, Lucas Lindwas has just raised his hand. You can see that.
Yes.
Right.
So
they ask a question. Once the question is asked and answered, you can lower their hands, and that'll float them down to the bottom again. So you just start from the top and work your way down to the bottom.
Do I need to click on them? Presumably yes.
You don't need to. You can just see them and ask them to unmute themselves and ask the question.
I see. So they will be able to hear me.
Yes.
Okay.
Okay.
That's it then.
Great. So the plan is, as you'd said in your email.
0 to 5 minutes for everybody first.
Yes.
And then we just open it up for questions and see what happens.
Right.
Are the other panel members continuously unmuted or?
No, everybody, all the other panel members, I think we'll do it the way we normally do it, which is everybody stays muted until called upon, and you get to call upon people.
Okay.
So.
And in this case, they unmute themselves?
They can unmute themselves, yes.
Okay. That's all that matters.
Yes. So
they can just simply get on with it.
That's right.
Okay.
Okay. So I'll be hovering in the background as well. So this is now to everybody. We'd like to take a conference photo. So I would like to ask you to all, if you're comfortable with it, turn on your cameras so that I can see you all, and then I'll take some screenshots and hopefully capture as many people as possible. We've got about 416 participants in the room at the moment. I'm going to go to gallery view, and I can see pretty much everybody. And there's 17 pages. Let's see how fast I can take screenshots. So you don't have to say cheese or anything, just exist. Thank you. This is great. Still going. Don't move. Nearly there. This takes just as long as a regular conference order. Done. Thank you very much. Okay, so Malcolm, I think we're ready.
Okay.
So welcome everybody to the panel discussion on black hole information. We've had a great 2 sessions starting off today, and we're going to continue that with a panel discussion which includes our speakers of the day. So Juan Maldacena, Samir Mathur, Jeff Pennington, Subrat Raju, Doug Stanford, Andy Strominger. In addition, on this panel, we will have Ahmed Almeri, Netta Engelhardt, who spoke earlier this week, and Don Merrill, who will join us, I understand, in about 30 minutes. And the session will be chaired by Malcolm Perry. Malcolm will explain the rules for the panel, and then we will open it up to, after everybody gets, I think, a chance to speak, we will then open it up to discussion. And this will continue until 9 o'clock my time. So that's 9 o'clock South African time. So we'll have a 2-hour discussion session, and then David Gross will carry on with the vision session. Malcolm, over to you.
Thank you, Jeff. So the way in which this is going to work is that everybody gets a chance to speak for 0 to 5 minutes at their choice. And the order is going to be Juan Maldacena, Ahmed Almiheri, Netta Engelhardt, Samir Mathur, Jeff Pennington, Suvrit Raju, Douglas Stanford, and Andy Strominger. And then at the very end, Don Marolf. He's supposed to arrive at 7:30. So we just have to hope that he actually manages to do that. So our first speaker is Juan Maldacena, and over to him.
Okay, can you hear me now?
I can hear you.
Okay, good. So I would make just one point, and it's related to these average overcouplings. As Douglas just said, when we have 2 field theories and we couple them to each other, it is natural that we should allow wormholes. So here are the 2 boundaries. We are coupling them to each other. And then it's natural to develop wormholes between them. And the wormhole geometry should not be forbidden. And in some cases, there are strong indications that it is actually needed. Now, I think this is particularly natural in cosmology, where we can think of this space as a late time slice in our universe. And then we are averaging, or we're summing over, if we think about the Schwinger-Keldysh formalism, we are summing over the possibilities in the future of our universe. And so it's natural in that context to expect that there should be bracket wormholes. So wormholes that connect the bra and the ket geometry, wormholes that connect the geometries that connect the bra and the ket. And so we could live in a universe where ensemble averages are very important, and are very important perhaps to determine the actual state of the universe. This is just a vague comment. Thank you. That's all.
Thank you, Juan. I guess our next contributor is Ahmed. I hope you're there somewhere.
Yeah, I'm here. I'll try to share my screen.
Yes, you succeeded.
Okay, do you guys see this?
Yes.
Okay, so thanks for the chance to participate. So what I'm going to talk about, or what I'm going to make, are a few comments regarding the experience of an infalling observer, and in particular the question of whether the island formula removes the firewall or not. So here's the island formula. Can you guys see my cursor? Maybe. Okay, so here's the island formula on the left-hand side. And so the thing that I wanted to say was the space-time diagrams featured in many of the talks. They come in as leading to certain computations. For example, the usual semi-classical picture of an evaporating black hole is something like the leading saddle of trace of the intensity matrix of the radiation. You can think of this as path integral of the entire system. Another is, another space-time is what appears for the Renyi calculation, which near n equals 1 is precisely the original semi-classical space-time, but now with these branch cuts and branch points. This observation that near n equals 1, this geometry is the same as the original semi-classical space-time, is the origin for why the matter entropy in the island formula is evaluated in the semi-classical state. My worry now, with regards to the final question, is that these semi-classical spacetimes, at least from sort of a literal perspective, they're not sort of predictions of what the actual spacetime is. Rather, they are representations of the calculation, in particular here of the entropy of the radiation. To conclusively answer this question of whether there's a firewall or not, we would need to do two things, at least it seems to me. First is to identify the operator that creates the firewall, something like a firewall number operator, and then compute its expectation value by the path integral, and then just see what the path integral gives. And I guess the one hope would be to show that the semi-classical saddle is the one that dominates for this operator, and then we would declare victory. So that's all I had. Thanks.
Thank you. I guess next is Netta Engelhardt. Are you there?
Yeah, I'm here. So I already had a chance to talk about my perspective earlier in the week, so I'm going to be pretty brief. Just a couple of points that I think are very important for us to think about. The first is something that Douglas has already mentioned and has come up a couple of times, which is trying to address what the gravitational path integral is computing in higher dimensions. So I think we're not supposed to worried about it in JT gravity, in the sense that things make sense. It makes sense that it might be an ensemble there, but in higher dimensions, we're talking about n equals 4 super Yang-Mills. We would like to understand better what we mean by an ensemble average. Is this just a calculational trick, or is this something which is actually telling us something fundamental about the theory or about gravity? And on the same note,
Sorry to interrupt, Neta. Sorry to interrupt, but we have a sound problem. So Malcolm perhaps can unmute himself. Malcolm, could you unmute yourself?
Yeah. Is this better?
It was so bad that I would recommend that we let Neta start over.
Okay.
Yeah, Neta, please start over.
Yeah, no worries. Okay, so I was just describing a couple of my own personal opinions on what are some of the important questions that we should be asking ourselves right now. Some of the more urgent questions, such as what is the gravitational path integral of computing in higher dimensions. So I think in JT gravity, we might be okay with the idea that there's some kind of an ensemble average happening, but in higher dimensions, it again was mentioned in previous talks and in Douglas's talk in particular, we would like to understand better what is this just a calculational trick and there's something else behind it, or if it literally is an ensemble of theories, then what is the ensemble and how is this different from what we've been looking at all along in terms of semi-classical gravity and higher dimensions. Now, on a sort of similar point, this is something that I mentioned very briefly at the end of my talk. When we're talking about ensemble averages and the contribution of replica wormholes, we can also look at something like the free energy, which is possibly the simplest thing we can be calculating. And it really makes a difference whether we're calculating log of the average, ensemble average of Z, or the average of log Z. And I think that there's a lot to be learned from the differences in something as simple as the free energy. And then the final point I want to make, and again, I'm trying to be brief here since I had my chance to talk at this conference already, is I think we really, at least I would really like to understand how to do the calculation that the gravitational path integral is doing for us, just purely on a quantum mechanical level. In particular, so that we can compare the just a quantum mechanical formula for entropy that gives us the page curve in quantum gravity with the calculation that Hawking did, and once and for all really understand the difference between the two. And so this is just my my perspective and where I think we should be going right now. Thank you.
Thank you. Samir is next.
It says sharing is paused for me. So I think somebody has to allow me to share the screen.
Try now.
Hello?
Try now, Samir.
Yeah, can you still see? Yeah, shall I try to share again?
Yes.
It didn't allow me to share last time. Okay, can you see the screen now?
Yes.
Okay, let me just try to go to view the screen. Okay, so that should work. Can you hear me and see it?
I can
yes.
Okay, great. In my talk today morning, I was just talking about what fuzzballs do and the perspective we get from there. And I do think that gives us a complete picture of what should happen with the information paradox. But what I would like to do in a couple of slides here is share my thoughts on what I think the other approach through wormholes and the recent work on the page curve seems to be doing.
Samir, we can only see a little bit of your presentation. Could you make it full screen? Or?
So it is full screen on my side. How does it look?
It's not on ours. Maybe.
Yeah, it was full screen on my side. Do you see the top line saying, what does the Gibbon Hawkins tell us?
We do, but it's just a window on your screen as opposed to the full screen.
Yeah, it's not maximized.
Yeah.
So I did maximize it and somehow it's not maximizing over there.
Maybe
I only see half of except at the S.
He's showing the wrong window.
That's right.
I'm sharing the wrong window? Okay. So
Desktop should be, yeah.
I'll do a stop share and start sharing again.
Yeah. That's it.
Okay.
Perfect.
Much better.
Okay. Does that look fine now?
Yes.
Thank you. Okay, so I'm just going to share with you my thoughts on what I think the recent calculations are telling us as far as the information paradox is concerned. And for that, let me just go back to what the Gibbons-Hawking calculation of entropy told us 30 years ago. So here is the kind of disk geometry that we use to do the Gibbons-Hawking. It's a cigar across a sphere, and you can add handles to it. In principle, they are suppressed, but then whatever answer you get from here is always a finite answer, and then you can use it in a thermodynamic relation to find a Bekenstein entropy. So now you might think that you learned something about the entropy of black holes, but that is not the puzzle. The puzzle is that if you actually go to the Lorentzian section, then you find an infinite number of states with the same energy equal to m, so that the z actually becomes infinity. And so that's, of course, clear. You can make those states explicitly. This kind of slice with just in the Ellington-Fickerstone diagram just keeps going on, and you can put both positive and negative energy quanta on it. You automatically generate that kind of states if you feed and evaporate a black hole for a long time. And in fact, clearly the entropy is infinity. So a version of the information problem is then just this. What you get from the Euclidean calculation is a finite number, but what you get from here is not. And so then what are you supposed to do to solve the puzzle? Well, you have two choices. In the full quantum gravity theory, you can either go and show that this Lorentzian picture was completely wrong. A small correction to it wouldn't change it because the bags of gold problem is also robust to small corrections. Or you can actually say, no, I can't change that picture. And then I accept that S-Beck does not give me the total entropy that can be stored inside the horizon. I can store an infinite amount of entropy. And relativists like Ward, Jacobs, and all sort of agreed you might get remnants of baby universes. S-Beck is not the entropy of the black hole. But what you cannot do is say that the simple Gibbons-Hawking calculation you did, if it spit out a finite answer for you, you can't say that semi-classical gravity was clever enough to tell us the black hole can have at most S-Beck worth of states, because that is begging the question. So I think that people would basically agree with. And I just want to compare that with what the kind of calculations we are doing now. So again, we start with the Gibbons-Hawking disk, but now we cut a slit in it. We put states psi and psi prime above and below and compute a explicit density matrix. You can add handles and do the full thing, maybe in a computer if you wanted, and get an answer. And the question is, whatever answer you get, what does it mean? Well, it has some meaning only when you go back to the Lorentzian section. And here's a picture I took from one of Juan et al.'s papers. And the Lorentzian picture you get actually is the same as what you would get from the CGHS model. The quanta inside go to the island, the quanta outside go out, and the entanglement of the radiation, ascent of just R, the radiation, it keeps growing. And that's not surprising because it is just like the CGHS model. So you should get that. So the way the page curve comes down is that from the point of view of the JT gravity, you actually change the quantity you are actually measuring. Instead of looking at S of R, you look at S of R union I. Now, of course, I'm not just saying that they're just cheating and changing the quantity they want to measure. This was actually supposed to come from quantum effects, which are not in JT gravity. And so with the QES prescription. And so the question really shifts to what is the quantum physics? So because we actually can't learn anything from the classical JT gravity, in my opinion, really the burden of the whatever has been done shifts to the quantum physics. And there we are inputting something. There are two quantum physics directions possible. Either you just say that you don't actually have the vacuum at the horizon, don't produce entangled pairs, you have the fuzzball, and then you actually construct those states in string theory. Or you assume you still have a smooth horizon up to small corrections, and then you have all the new effects you like, which then tell you that the interior of the black hole is not like a piece of coal, because there's a piece inside that coal, which is not really inside that horizon radius, and it can be actually affected by things from outside. So the point I was trying to make was that it's not that the semi-classical gravity has been clever enough to tell us anything about the information paradox or the page curve. So this is just the last thing I want to put up here. I think that from what I have seen, we should not say the following: we have computed the page curve and shown that information comes out. That is not what we have seen, because when you go to JT gravity plus scalars, you get the same remnant / baby universes or whatever you would have liked to do at the singularity as you had in the CGHS model. To me, it seems the claim is actually that holography / QES ideas motivate a picture in string theory, which we then input into what we say the black hole is doing. And the conjecture we then make is that new topologies need to be considered in the Lorentzian section. There will be disconnected sectors, baby universes. Inside the horizon is not like a piece of coal because a part of it is connected to the outside. Note, however, that just the fact that the inside is connected to the outside by entanglement is not enough to get any information out. you actually need a physical interaction to move bit from one to the other. So one is also asking for some interactions across what appear to be long distances from the semi-classical picture. So this is just the point I wanted to make. We are actually inputting a physics here that horizon remains smooth. So opposite to the fuzzball physics where you just construct the fuzzballs and you find it's not smooth. Here we're inputting the fact, no, we have a mental picture that we do want horizon to remain smooth. And then it logically takes you down the path that you actually have a remnant or a baby universe, which in fact it always did. And I think it's a very fascinating picture, though I don't think it's the correct one. But again, it's not a semi-classical gravity has been clever enough to tell us something. It's the curious prescription which has just motivated a picture. And I think what we are seeing is what that picture is supposed to lead us to. Thank you. That's all I wanted to share.
Thank you, Samir. Next is Jeff. Are you there?
So I hadn't really planned to say anything because I've just given a talk, but let me maybe make a brief comment or two. So I just want to spend a couple of minutes actually just thinking now of saying what to me is the best reason, though it's certainly not a conclusive reason, to think that there is actually a smooth interior and that there's not a firewall or a fuzzball or any other replacement for the interior. And it's not a terribly sophisticated point, but it's really just the fact that Hawking radiation, that the Hawking radiation calculation works and gives the right temperature in Lorentzian signature, right? We don't just get the Hawking temperature from the Euclidean calculations that give the entropy. We actually look at the state of interior plus exterior, and we assume that it is in the vacuum state, and then we get this thermal radiation. So that is obviously not a new comment to anyone, but I think there's some value in re-emphasizing it. But there's also, in the context of these quantum extremal surfaces and islands, but there's another thing that the smooth interior picture gets right that sort of, it doesn't seem to me like there's any reason it should be, you should get the correct answer if that smooth interior isn't in some way physically relevant. And that's just looking at the actual, let's draw an island. It's looking at the entanglement between some late time Hawking quanta and all the earlier quanta down here. So, in simple toy models, we often like to say that the late time quanta are just maximally entangled with the early quanta. But that's not actually true because black hole thermodynamics is irreversible. So the actual answer is that you have some, it's an entangled state, but it's not maximally entangled. There's a mutual information. But there's an incredibly sort of neat result, at least to me, which is that if you assume everything outside this quantum extremal surface is not encoded in the early radiation, but everything inside is encoded in the early radiation, and then you just look at the change in entropy from moving this extra little mode across to this early radiation, you get exactly the right mutual information. This is a quantitatively exact correspondence, and it really just always happens just because this surface is quantum extremal. Yet, the reason we're wanting it to be quantum extremal has absolutely nothing to do with any calculations you give it that. So it just seems to me that if this whole region is just totally fictitious and just a sort of coincidence this calculation works, it's very mysterious why on earth that exact that there's like the exact correspondence between the mutual information here that we get from unitarity and the mutual information between this mode and these modes in the island region should be exactly the same. That's all I have to say, I think.
Well, thank you. Next is Surat. Hopefully there somewhere.
Surat? Subrat, are you there?
Sorry, I'm here. I'm just not being able to share the screen. Now I can share. Yes, thank you. Thank you. Okay. Can you see the screen?
Yes.
Okay, great. Okay, so I'll just try and be. Can you? I hope I'm sharing the right screen.
Yeah, it's not.
Oh wait. Yeah, just 1 second. I shared the wrong screen, I think. Now is it full screen?
No.
It is not.
You're not sharing?
I'm not sharing at all?
No.
Okay, 1 second. Let me try again. Now am I sharing?
Perfect.
Okay, great, fine. Okay, so I'll also try and be very brief. I just wanted to address some of the questions that actually came up in the chat that I couldn't address. In the talk, I tried to argue that all the information that's available on null infinity is actually available on its past boundary. And one of the points I tried to emphasize was that this is not an abstract result, but leads to a concrete protocol for extracting information near infinity. There were some questions in the chat about whether this works in ADS. So I just wanted to explain how it works very beautifully in anti-de Sitter space as well. And the story is as follows. So I'm going to simplify a little bit, but the essential story is as follows. Let's say we have some astrophysicists who live in some global state G, which is the state with a red ball, and they want to determine if it is the state F, where F is some other state. And there were questions about whether G and F could be related by a global symmetry, and they could be in this example. And just for simplicity, I'll assume that F and G are both low energy states. And it's clear that in a local quantum field theory, these astrophysicists have to go into the bulk and determine the shape of these bumps and see and check if G is the same as F or not. But the point is that in gravity, they can do this purely by acting with local unitaries and by making measurements near the boundary and in a very small time interval from 0 to epsilon. And the protocol is as follows. Let's just assume for a second that both these states are orthogonal to the vacuum for simplicity. So the first step is you can find an operator, it's Hermitian operator as we discussed, which acts on the vacuum and creates the state F. You're not allowed to act with the Hermitian operator, but you can act with the unitary operator e to the IAXF. And after that, you just measure the Hamiltonian and you count how many times you get 0 up to second order in this parameter A. So this is a completely allowed process in quantum mechanics for these observers. And then you just compute what the result of this experiment is. And you see the first unitary changed the state in this way. And after you measured the number of times you got 0 for the Hamiltonian, you see the second order, you immediately get this overlap between G and F. So this is an example of a process that would have been impossible to do in a local quantum field theory by these astrophysicists, but can work completely explicitly. And even if these states are related by a global symmetry, one can determine if they're orthogonal or if they're not. It's by extrapolating these kinds of arguments, that one comes to the conclusion that the information is always available outside the black hole. Of course, once you start going to black holes, these operators, these unitary operators become more and more complicated. And so then the questions become more subtle. You can't find them explicitly, whereas for low energy states you can. But I think the interesting question, which I'd like to focus on, and I'll end with this, and I don't know the answer to this, is a question of whether it is easier to recover information after evaporation than it is to recover information before evaporation. And I think the small black hole is an instructive example. So if you think of the small black hole that forms and evaporates in anti-de Sitter space, you can ask just from the conformal field theory, what is the complexity of the correlators you need to measure to determine the microstate? So before the black hole forms, it's very low. You can probably determine the state of the dust using some 2-point correlators. After the black hole forms, you need very high point correlators. You need S-point correlators, which you need to measure to accuracy e to the minus S. But the important point is, even after the black hole evaporates, you need very high point correlators. In fact, you need higher point correlators because the Hawking radiation has larger entropy, and you need a larger accuracy to determine what the state is. Now, I want to emphasize that this is not a watertight argument because small black holes are very atypical states that we don't understand well. But I think it's an interesting case to consider. And I think it might suggest, in particular for the case of black holes evaporating in flat space, that if we think of these two nice slices, this one that bends down and this one that goes up and collects the Hawking radiation, it's not necessarily easier to recover the information by making measurements in the green region than it is by making measurements in the red region. So I think the small black hole example is an interesting example to think about. Okay, so I'll stop there. Thank you.
Thank you. Douglas is next.
Thanks very much, but I'm going to pass so we have a little more time for discussion.
Okay, then that makes Andy next. Andy, are you there?
I am there. Can you hear me?
Yes.
Loud and clear.
You got my screen?
Got that too.
Great. Okay. So it's the only one. So in 50 years of discussion of this, there's been remarkably little agreement on anything, and including even what it would mean to solve the black hole information paradox. So I am going to present my view of what it would mean to solve the black hole information paradox, which probably not everybody will agree with. But first of all, I'd like to say that there's two parts of the paradox: how the information is stored, that is accounting for the Bekenstein-Hawking entropy, and how it gets in and out. It's like what makes up the chips in your computer and how it's connected to the internet. They're different but closely related. Secondly, I would say we should not be allowed to make it's a bottom-up problem because we want to understand the black holes in the real world. And we're not allowed to make specific microphysical assumptions such as string theory or so on, but general ones I would view as okay. You could assume symmetries. My favorite example is Boltzmann, who derived the laws of thermodynamics from statistical mechanics, and he had to assume something which was then very controversial, molecules, but he didn't have to make very specific assumption about the behavior of molecules, just that there was a smallest piece. I would also view the idea that you should add Euclidean terms in the path integral. That's fair. But general types of assumptions, just not very specific microphysics. I would say we would like to get a microscopic derivation of the Schwarzschild entropy and the universality of the area, which also applies to cosmological horizons, and the log corrections, which also should not depend on microphysics found by Eschot-Sen. And here, the kind of example I have in mind, you say, how can I have a microscopic derivation without microphysical assumptions? Well, I think we have a kind of example in mind of BTZ black holes in ADS3, where we just have to assume that we have a consistent completion of quantum gravity on ADS3, and it is unitary and local and all that. And then we have a conformal field theory. Maybe we have to assume modular invariance and more properties, but general properties. And then we can understand the counting of the entropy without ever knowing the details. We don't have to know it's ADS3 times T4 times S3. We just have to know the ADS3. And we would like something similar for the information flux at Scri+, which everybody is guessing is the page curve. To test our understanding, that should have log corrections because the entropy law, area entropy law does. We'd like to be able to control it well enough that we can compute those. And finally, I would add, there's no guarantee that this is possible. In fact, when Gorman and I first computed black hole entropy from string theory, it depended so much on the 2 pi's and the dimensions of moduli space and properties of algebraic geometry and so on. We were convinced that you needed a microscopic theory to get the entropy right. But later we realized that it all came from holography and general properties, that it was guaranteed to work. So it could happen that to answer this question, we have to find the theory of everything first. I think most people probably agree to me that it's reasonable to try to solve this problem without doing that. Anyway, so this is my brief summary of my view on what it would mean to solve the black hole information paradox.
Great, thank you, Andy. Last but not least, is Dot there? Is a real question.
I'm here,
Splendid.
and with your electronic permission, I'll share my screen and say a few words.
Please do.
It says, okay, now maybe I can do it now. Let's try one more time. Share screen. Share. All right. Can you see that?
Yes, it's perfect.
Okay, great. It is perfect. So I'm mostly going to do some cheerleading given the late time and the short time. But this is kind of my picture of where we are. I think this is a very exciting time for talking about black hole information. I feel like before the discovery of replica wormholes, there were some thoughts, there were some ideas, but it was a lot of feeling around in the dark without really a guiding principle. And I feel like the discovery of replica wormholes has at least turned on a lamppost that gives us an interesting place to look for answers to even some of the questions that Andy was talking about. In particular, we learned that the gravitational path integral, something that we thought we had some idea how to work with, at least at the semi-classical level, still has a lot to teach us, again, even at the semi-classical level. So it's sort of clear what to do in the near future. We should go to this lamppost and we should dig into the replica wormhole calculation as much as possible. And so that's what we need to do. And I think it's going to keep us all busy for quite some time. And it's been very interesting that doing so has already suggested that there's a lot of interesting physics at play. Space-time wormholes, baby universes, possibly dualities involving ensembles, et cetera, et cetera, et cetera. And I'm not saying this is the final answer yet, but there's a lot more things to explore. Now, the thing that I am personally the most excited about that has appeared in this process is the idea of what I'll call novel null states. And I'll say just a few words about that. So the basic idea is, very briefly, that the replica wormhole calculations themselves really suggest that the gravitational path integral provides a sort of dynamical mechanism to enforce entropy bounds, which means that even if you write down some setting where you've tried to put more states into a black hole than its Bekenstein-Hawking entropy, the actual entropy appears to be bounded by the Bekenstein-Hawking entropy. That's what the replica wormhole calculations seem to suggest. I'll mention that this idea that the Bekenstein-Hawking entropy is really a bound, of course, it's an old idea, but you can make an argument for it just using the gravitational path integral under the assumption that the path integral defines a positive definite inner product for the states in the theory. And I'm not going to review that argument now because I don't have enough time, but this is one of the things that came up in a recent paper with Henry Maxfield, and it's sort of related to the ideas of Daniel Jafaris from a couple years ago. And I wanted to mention that there's a general argument, but in particular, Henry and I looked at a toy model where you can see this come about from non-perturbative gravitational corrections to the inner product, which have the property that they take states that without the coupling to gravity would have been linearly independent, and so you would have thought of them as completely separate, and they generate linear dependencies. So that's a novel, exciting property that I do not fully understand, but I would like to understand much better. And calculations in JT gravity show evidence, I think, of similar behavior. So that's a weird thing, and I didn't explain all the details, but I'd like to just illustrate again what I said, which is really you can describe a lot of these calculations as you think about having some system of, let's call it matter degrees of freedom. It doesn't have to be really matter, it could be gravitons, but let's call it matter degrees of freedom. And you might first think of it as this blue box where you write it down on some fixed background. Maybe it's a black hole background. Maybe you do perturbative analyses of quantum field theory inside black holes, and you find that, yes, inside old black holes, there can be vast numbers of states that appear to have vastly higher vastly higher entropy than the Bekenstein-Hawking entropy of the associated black hole. So this is part of the black hole information problem. These states appear to be there, and how can you fit them inside a black hole, which only has a finite entropy. Well, what appears to happen in these calculations is that when you turn on dynamical gravity, this blue box gets compressed until it exactly fits inside the black hole box. That's an interesting mechanism that, as I say, one would like to explore better. It's also a confusing mechanism. It leaves us as physicists rather confused because, of course, if you take a large space of states and you compress it into a smaller space, you can't preserve all the information perfectly. Some of the distinctions between the original states become lost. So this leads to open questions, which is, how do we really understand physics in this environment? What does it mean for observables inside black holes? How should we discuss, quote, what really happens inside black holes if things that without this dynamical gravity effect we thought were completely different, okay, in fact become kind of the same? All right. So I don't really know the answer, but as I say, it leads to interesting possibilities. And an exciting possibility is, as my collaborator Henry likes to say, that everyone's a winner. That in some sense, all of the ideas that have been discussed about how black holes can return entropy, can return information in Hawking radiation are in some sense true. Even ideas where it wasn't returned are true. It may be that information is in some sense lost when black holes evaporate due to entanglement with beta universes. But it may also be that this information loss, it can never actually be observed by anyone outside the black hole, because in super selection sectors of the universe, in fact, the information is returned. So it's returned in every possible operational sense. It may also be true that due to this lack of distinction, or because of this compression inside black holes, due to these null states, some of the things that have been described before as state dependence may in fact be better described as gauge dependence. Maybe this is a way that ER equals EPR manifests itself. And because of this compression and lack of distinction between things that you thought were physically distinct, maybe smooth horizons and firewalls are also gauge related. I don't know. And there's also room in this for final state boundary conditions. There's also room for highly non-local interactions, which relate to other ideas about returning information in quantum gravity. And finally, this all has to do with the inner product of a gravitational system, which you could imagine is related to corrections to the non-perturbative gravitational constraints that people have also talked about. So there's room for lots and lots of ideas, and I would like to understand this structure better. And that's my story. Thank you.
Well, thank you. Well, I guess what we should do now is just open everything up for general discussion. There are around 456 participants, some of whom must want to ask a question, of which Emil seems to be first.
Yeah. So I had a question, maybe to one, but I'd also be interested in other panelists' opinions. So there was a picture of a sequence of Penrose diagrams of an evaporating black hole, at which the last one was an island that was disconnected from an ADS region coupled to a bath. So I was wondering what that sequence of Penrose diagrams would look like if I just took a small black hole in an isolated ADS and let it evaporate. So just make a black hole by, putting some operators on the boundary that make a small black hole. Now that's supposed to evaporate. And so it seems like the information is still on the island, or is encoded in the entanglement between the island and the stuff which is still in the CFT, because I haven't coupled the CFT to anything. And so it seems like I have a remnant within ADS CFT, and I'm puzzled as how do I get the information out of the remnant.
Well, first of all, when you calculate the entropy, you would always include the whole black hole interior for all times. And so the entropy is 0 for all times, and it manages to be 0 by including always the black hole interior, even after the black hole evaporates. So you can think of the black hole interior as some other baby universe that comes out. So at least from the point of view of entropy, you always have the right entropy. Now, I think your question is more like, what is the right state? How do I figure out what the right state is? Because the state that is outside looks thermal, that is in the ADS region. And I think that's what we don't understand. We don't understand how to get the right state from gravity. Now, it might be that, okay, so the true thing is that we don't understand. Now we can go to speculations that maybe there is effectively some kind of final boundary condition, for example, in the interior that forces that state, projects that interior state onto some particular state, and then we will get a definite state outside. That's one possibility. But maybe there could be many other possibilities. Maybe the singularity is secretly connected with the exterior particles, and there is some some way that the actual state is encoded in the singularity. That might be somewhat similar. So the short answer is I don't know how to get the right state from the gravity picture.
Okay.
Can I make a naive comment on this question?
Sure.
We don't know how to compute the right state, but there's some kind of complicated state that somehow comes out. And I think Emil's question is really, does the region that ends at the singularity exist a month after the black hole is finished evaporating? So you could simply say it doesn't, that there's just a complicated state of the radiation. On the other hand, if you understand in detail what the state is, you could do some complicated measurements on that state. And if you were able to think of just the right measurements, you could probably come up with some that could be usefully described in terms of the picture where you did say that the region behind the horizon did exist. So it's actually going to be really up to you, and depends on what you want to do and what you understand, whether you say that region exists or not after the black hole's evaporated.
Yeah, but in the calculations that are being done, the mileage is being made by assuming that there's some semi-classical region behind the black hole. And in the calculations, the information that's in that semi-classical region never gets out from inside the black hole. It's just sitting there entangled with some radiation quanta that are outside.
True, and a month after the black hole's evaporated, you can forget about that region if you want to. Or you could say it's useful for asking some very special questions.
Well, but then I think that the qubits that are stored there have to go somewhere. So where do they go, and how do they go there?
I think there are two things you could do. You could keep the exterior and the interior, and you have some representation of the state, or you could maybe remove the interior, maybe similar to your Donald's remarks about gauge equivalence. Remove the interior completely, and then have a very complicated state outside.
Okay.
Can I make?
Go ahead, please. Go ahead, please.
Okay. Yeah, I think I just wanted to make some comment about and the question, kind of open-ended question about what Andy said. What's the information problem, and how information is encoded in the final state of the Hawking radiation? That's probably not necessarily most important thing. It's like dropping a glass, and how the initial state is connected to the pattern of the final glass is on the floor. It's probably not the first one we want to discuss. So from that point of view, from exterior, unitarity, if you believe ADS-CFT, is pretty much kind of solved. So the problem with information problem to me is like interior. What to think of interior? For that, a piece of code and the black hole is a very, very different object, because if your horizon, if your surface is recede up to where local Hawking temperature becomes string scale, then it's a chaotic. Everything's chaotic. That's why if you focus on some mode, whose energy is higher than Hawking temperature, then you automatically have a structure of the states of thermophile double. Only if it's a completely chaotic, across all low energy species. That's not the case for a piece of coal. A piece of coal, of course, maybe a photon may be radiated, but not a neutrino. Then, of course, you cannot have a space-time picture interior of the piece of coal. But the black hole is very special because it's a string dynamics, no global symmetry, everything is distributed. So then at least you have a state after cross-graining, have a thermophile double state, including the Boltzmann coefficient. And then you can also build a Hamiltonian, which is local by doing just usual Lindner to folding frame. Then the question is also what Ed was saying, by the existence of those operators, which is a very, very, very complicated subtle operator encoded in radiation and some black hole softmodes, is enough to claim that that's the observation. Like, so in the end, what's the observables in quantum gravity, or what's the observation? Is it enough to have that kind of algebra? But at least we have a local algebra. So if you believe that if it's a local, then something is enhanced and become classicalized and observable, so still already observable, then I think we have interior. But if you need to have infinite far away decoherence, then you could claim, okay, interior doesn't have any operational meaning. So it's ultimately, so when we are satisfied, I mean, does the existence of local Hamiltonian plus correct states is enough or not? Is my question, which I don't know because this is kind of quantum measurement question in quantum gravity. That's it. That's all I want.
Does anyone want to comment on that?
Could I say something about Emil's question previously?
Sure.
Yeah, I just wanted to say, I think, I agree we don't have a watertight argument for understanding what's behind the horizon. But I think the question before that is, do we have a good reason for believing that the region behind the horizon is not what is given by the conventional solution? And I'm not sure that we do really, because if one just looks for information recovery, I think that can be done without having structure at the horizon. Then I think something that Daniel pointed out during the main session, I think it's true that if one looks at typical pure states in large black holes in ADS, I think these arguments that Joe Polchinski and Don Marolf gave about state dependence and some of the issues that could arise with that might be the best arguments we have to argue for whether there is structure behind the horizon or not. But once again, I think that should be distinguished from the case of black holes in flat space, because black holes in flat space are not typical states. And so I'm not sure that there is really any good argument we have for believing that the region behind the horizon is not what is given, what we expect it to be. So, I mean, the default assumption I would have is that the region behind the horizon is what is given by the conventional solution.
Daniel, you seem to be next.
Oh, I was just going to comment. I think even in flat space, you can certainly think about a black hole in a typical state. It's just a black hole that you form by collapsing an exponentially complex cloud of Hawking radiation over a time of order m cubed. And then at t equals 0, that should give you a black hole in a typical state. I don't immediately see how to apply the Marolf-Polchinski argument to it, but I feel like this problem exists also for black holes in flat space.
Well, the argument relies on the fact that these, they want the black holes to dominate the ensemble, which flat space black holes never do.
Well, you can define an ensemble where they do dominate, though, right? It's not the thermal ensemble, but just the ensemble of microstates of the black hole of energy E sitting at the middle of space, right? I want to, can I push a little bit also on this comment of Andy about not needing to know string theory? I mean, that for me, that would be very disappointing, right? I mean, I guess it may be that some aspects of this problem can be understood without using string theory, but I think
I love string theory, by the way, just for the record.
Yeah, thank you, Andy. But I mean, I think some of the conceptual questions that we're running into, like, do you average, do you not average, what happens in typical states? I mean, I guess I would be a little surprised if you don't need some input from knowing what the structure of microscopic quantum gravity is to be able to resolve those questions. I could be wrong, of course. I was wrong about the page curve, but
I guess I just want to say we won't feel we fully solved it if at some point we have to say the words string theory and that it depends on string theory being the theory of everything.
Why? Wouldn't that be great? Wouldn't it be great if it depended on that?
Well, that's a possible outcome. That's a possible outcome. And we sort of thought that's how it was for a while, but now it's looking less, it would be a less powerful outcome.
My feeling is that the current understanding is more or less similar to the Bekenstein-Hawking situation. We knew how to compute the entropy. Now we know how to compute more sophisticated entropies of either the Page curve, ensembles and late time averages, etc. But to get the macrostates, we still need the tools of string theory.
But maybe string theory is the only theory of quantum gravity, Andy. So then it's really not, depending on string theory.
Yeah.
I mean, I think if we have just one reasonable theory of quantum gravity where we can resolve the information paradox, we'll already have learned a lot.
Yeah. Also, I want to comment on, Douglas made the statement about wormholes being bad. People thought wormholes were bad. I never thought wormholes were bad. I thought some of my papers that I wrote on wormholes after the first 2 or 3 were bad. And we've been waiting for a better one, the return of the giant wormhole. And maybe it's coming now, a good one, in which wormholes are put to a really good use.
Yeah, sorry, that was pretty reductionist. By the way, Azadeh Malik Najad has had a hand up for a while.
Yes.
Yes, thanks for noticing that. I thank you all for such great talks. I really enjoyed all of your the talks today. I have a very basic question for Andy about the microscopic description for the entropy, which is super charming. So I'm wondering how it's doable perturbatively, like neglecting the back reaction effect. What's missing that we still don't have that that microscopic prescription? And also, it's related to some physics that we don't know yet. So is that physics is just going to show around black holes, or are there any other like parts of physics that it might show up, like early universe or something like that we can check? Yeah.
Well, I don't think that in any of our lifetimes we will understand all the laws of nature, the theory of everything. And it could happen, but I'm not holding my breath. I think we can solve the black hole information paradox in a shorter time scale. And, Ed used to like to talk about alternate planets on which they discovered string theory before gauge theory in gravity. But we could also think about alternate planets where we discovered holography before we discovered string theory. So you could have started with Brown and Hanot, you could have said conformal field theory, it would have all been a little fuzzy, wouldn't have understood it as well, but we could have started trying to get the outlines of it. We could have said something about black hole, BTZ, black hole entropy. We could have started trying to get, it's not very hard to imagine. And indeed now lots of people teach courses in holography in which they never say string theory. It kind of has a life of its own. But it's more of a bottom up than a top down. And obviously both approaches, the approaches have informed each other, and every approach should be pursued. But what I'm hoping for is a kind of bottom up approach that will give us some picture of what the microstates are, how they come in and out. I think that this recent work is a very inspired guess that extrapolating ideas from ADS holography to flat space holography, and it may help guide us towards a bigger sort of framework and way of thinking about things that does not, the reason stuff, as if it's not patently obvious, there's no assumptions of any string theory. It's all semi-classical gravity and so on, and it seems to know something about quantum information and so on. So, for that reason, I think it has a very good feel with it and goes along with my idea that not my idea, but the idea that we might be able to make a lot of progress on this problem without having to find the theory of everything, which would also be fun. We shouldn't give up on that, but it's not necessarily the same problem.
Yeah, sorry, maybe I asked several questions at the same time, so
yes.
it wasn't clear enough. So my main question was if this microscopic derivation, how perturbative it's doable. I totally agree with, I'm totally happy with the semi sort of classical dealing with gravity, but my main problem is that in that calculations, we are doing quantum field theory in a background with a fixed mass, while the mass is decreasing because energy is extracted from the black hole to produce those particles, and that's my main problem. How much this back reaction effects or this non-linearity sort of are important in this microscope?
Are you asking about my computation with alpha?
No, actually, this is a very basic and naive question. I'm not referring to any specific calculations. I'm just asking about your last comments during this discussion panel.
Yeah. I think you'll have to, if you don't have the complete laws of nature, you have to live with some uncertainty in the equations. And that makes it hard. And you have to be able to derive things using general principles, and sometimes you can get in trouble. If you're a condensed matter theorist, you just may make a wild leap, and then you have an experiment to help you out. But as a high energy theorist thinking about quantum gravitational theorists thinking about black holes, we have this very strong constraint of self-consistency. It's hard to say anything which doesn't become self-inconsistent, that's what we have to go with.
Thank you.
Okay, Daniel, you've still got your hand up.
I did have another comment, but is there anyone else who didn't talk yet who has a question? Maybe you should do that first.
I have my hand up, but...
well, it's true. Henry had his hand up next.
Okay, so I just wanted to get the panel's opinions on where we've gone with the what progress we've made with the original information paradox, which was asking about a calculation for the experiments or experience of asymptotic observers. This seems to give information loss, but there was nothing obviously wrong with the semi-classical calculation. So this is an easier question perhaps than asking about interiors and so forth. It seems that we've got an improvement on that, and semi-classical gravity does give us predictions for asymptotic observers in line with what one calls the central dogma. But the cost does come with replacing that with a new paradox that it seems to, as motivated, for example, by Douglas's talk, that it seems to give us ensembles or baby universes or alpha sectors as the cost. And we now have a paradox because n equals 4 super Yang-Mills doesn't seem to be, it seems to be a perfectly good theory of gravity by itself. So actually it's the information problem has now been replaced by the factorization problem. And I'd like to solicit thoughts on if people agree with that perspective, or it mirrors something going on in the chat at the moment as well.
I mean, if the question is, I don't think that one necessarily needs an ensemble interpretation to understand these things. I mean, at least if one looks at situations where gravity is dynamical throughout and the information can be obtained from far away, I don't see that necessarily requires us to turn gravity into an ensemble. So I'm not sure that I would think that there's a new paradox that has been introduced. And it seems to me that one of the Hawking's calculation, of course, neglected exponentially small corrections and also neglected the fact that gravity localizes quantum information unusually, which wasn't understood well then. But so I think we have made some progress towards understanding that.
Maybe could I add a couple of thoughts on that? You start by saying that one can think about the black hole from outside. And in fact, in the paradigm that Juan mentioned at the start of his talk, well, from outside, the black hole should look like a piece of coal. So that perspective actually has always not made that much sense to me. I think there's no well-defined question of saying, how does something look like from outside? If you can throw things on it and get things back, yes, of course, you can stand outside, but there is no, you can't even address or ask the puzzle. That thing is part of your space-time, you're interacting with it. So in fact, the puzzle or the issue only comes when you consider everything. If you stand only outside, you can actually say, well, this happens or that happens, it just looks circular to me. So the question again is you have to say, okay, what happens there? And I think the way to phrase the question is, when you take some region away from the black hole, let's say 4m outside or 10m outside, what is your rules there? Are you changing physics or saying it's basically close to normal lab physics, which you can pull out of a condensed matter textbook? Suppose we say it is that, it's normal physics. Then the question becomes, at the horizon, do you have smoothness or not? And I think that is a precise question. I don't really agree with Maron's idea that everything could be just representations of each other, because there is a precise question. Is there any description in which the local entangled pairs are being produced in the typical state 0, 0 + 1, 1? If they are, and the member which is outside has now gone to a place which is semi-classical physics and can't be touched, these are all real things. You can make them as precise as you like. And then once you are in here, you have a paradox. So I think you really have to focus on how you're asking the question, but not try to evade it by saying that you won't look at the inside, or the inside could have many manifestations. Once you take into account the pair creation expression, and you also say that outside 10m, nothing is to change, you have to go to a baby universe or a remnant. So at least there are some things we know for sure, which I don't think can be just wished away by language. So I know that Subrat may disagree with that, but let me just make my perspective on that. I think the entire black hole puzzle can be recast without going anywhere near infinity. You can make a tiny black hole at CERN, hopefully one day with 10 Planck masses. You get only 10 quanta outside. The fact that something is very complicated is gone. We just 10 quanta. And you can ask very precise questions in exactly the language that I was saying. And it seems to me that what we have learned from string theory is that microstates just behave like real pieces of coal, and you don't get the entangled states 0, 0 + 1, 1. They just become fuzzballs, and we were done long ago with that perspective. But if you do want a smooth horizon, yes, there are very many hard things that you have to consider. Okay, so that was my perspective, and thanks.
Can I just respond very, very briefly?
Sure.
Yeah, I think that the first point is I don't think in these notions where you're identifying degrees of freedom, either in the talks that Juan or Jeff gave, or in the description I was giving, that you're ever adding any new physics. You're never adding non-local interactions by hand, which is something I think you also mentioned in your slides. This is just something that naturally comes out of semi-classical gravity just by making a careful analysis. So I think that's one clarification. There's no addition of some interactions that are going to couple the interior and the exterior. The second thing is, I think we all agree that the true description of the wave function cannot be that of 0, 0 + 1, 1 raised to the power n. So the true ultraviolet wave function cannot be just entangled pairs in n of them. But I think there is an effective description in terms of that, in the sense that there are operators that you can measure which are entangled, but it is still true that the true description of the wave function is very different. It just has one copy of the degrees of freedom at null infinity. But it's true that it looks like you can find effective degrees of freedom that live in the interior, which are entangled with degrees of freedom outside. But I think we all agree that the wave function is not really what the Hawking wave function is. It's not just 0, 0 plus 1, 1 raised to the power n. So those are just two clarifications I'd like to make.
So let me just briefly comment that, in fact, what you just said is what I do not agree with. I do not think you can make a bit model where there's a true wave function and there's an approximate wave function. This is what you would like. The true wave function does something which actually unitarily gets information out like a piece of coal. And in the approximate one, it looks like 0, 0 plus 1, 1. And also in the approximate one, once you go outside 10M, you touch nothing. So I think you try to make such a bit model, you will fail. But if you do have one, I would like to see that. So I'm really contesting that.
I think in the papers with Kyriakos and so on, we constructed such operators, one of which looked like, so that if you looked at 2-point functions, it looked like the wave function was 0, 0 plus 1, 1. In fact, it looked like that up to very high order and correlation functions. And eventually the description broke down once you measured very high point correlators. So I mean, and we had concrete qubit models where you could take qubits and just find these operators, which were entangled with the operators outside. And I mean, we can discuss this offline, but I think it is possible. I don't think there's any obstruction to saying that for up to p-point correlators, the wave function looks like that. And beyond p-point correlators, the wave function has a different description. This description in terms of 0, 0 plus 1, 1 to the power n just breaks
So
down.
we should do that offline, because I think that is the mistake that you might be making there. 2-point correlators, small point correlators do not actually tell you what the wave function is doing. That is not what one should do from the start. I'm talking about the state, and I'm saying the true state cannot have the approximation where you keep a smooth horizon and get the information out without non-local correction. There are no such approximations. If you measure few-point correlation functions, you're looking at the wrong thing. You cannot come to any conclusions. But we should take this offline. Maybe let's give maybe other panelists to comment on that.
Okay, thank you. I guess Igor is next.
Okay, thank you. Yeah, I just want to make some, sorry if they're superficial, some partly historical comments, because I was one of the few people here who was working on Coleman's wormholes back in exactly 32 years ago. And I want to echo some of the comments that were already made by Andy and Douglas. Basically, I'm not sure if they were thought of as good or bad, but there was definitely a feeling that the theory was built on quicksand. I mean, when you scrutinize this theory because it was built on Euclidean path integral, and that's sort of ill-defined in 4 dimensions. So basically the story kind of fell apart pretty quickly because of Joe Polchinski's objection from the phase of the sum over spheres and so on. And then, so in these 32 years, the emphasis shifted to string theory, then ADS-CFT. So it's sort of amusing to see this return to Euclidean path integral, albeit in a much simpler theory like this JT theory. But, and I think this was already said by a few people, I'm not sure if we go above 3 dimensions, we have the luxury of just doing Euclidean path integral. And Coleman's theory is an example of that. So I would certainly hope that, so since this whole ensemble story is also a bit, there are questions about it, I would certainly hope that there is a way to understand page curve in theories without an ensemble. And even in low dimensions, there are examples of something like holography without an ensemble. For example, the duality between 2-dimensional string theory and matrix quantum mechanics. Of course, it's not what we want yet because we don't understand black holes in that theory. But I guess the question I have is there a way to understand any of it without the ensemble, even in toy models, without higher dimensions? Like, let's just go to some model of 2-dimensional dilaton gravity plus stuff. I mean, I feel like we should still strive towards understanding without the ensemble, but would be curious to hear what people think.
I feel that the calculations of H curve could be done without the ensemble. It's just the other more sophisticated other calculations, like the one that Douglas said, maybe in a complete theory, in a string theory, maybe they might give a different answer.
Yeah, I think there's a sense in which a theory that didn't have an ensemble would necessarily need to be richer than one that does. Like the simplest theories naturally end up being ensembles. And it may well be that in higher dimensions and in richer theories and string theory and so on, then you don't get that. But the toy models where we can calculate the most tend to be ensembles, but I think there's a lot of effort going on now to find toy models that are not ensembles. See what happens with that.
I guess an issue with the JT model is that it's not UV complete, right? So if we come up with a sort of top-down model, even in low dimensions, that may be totally free of the ensemble issue, right? So
can I elevate a point that was in the chat to maybe get some people to comment on the questions that were asked there? This is related to this issue of how you would restore factorization of the partition function for something like n equals 4 super Young-Mills theory, or any case where you have a single unitary theory describing a gravitational system. And I guess I'd like Douglas's perspective on that, or any of his collaborators, or anybody else. But my understanding is that we would need additional contributions that basically restore factorization. And it seems unlikely to me that those could arise from a geometric calculation where we still see a smooth horizon. But I think that would be the challenge. If that could be done, then it's in that setting that we could ask how the horizon can be smooth in a unitary theory.
I feel like I've said enough about this already, but I'm not sure. I'm quite curious to hear what other people have to say.
I should also perhaps point out that in a theory like a 2,0 theory in 60, not only do you like to restore factorization, but you better have the same answer as square of the partition function. So what you would need is something extremely fine-tuned, so that you get the answer as if there were no other contributions apart from the standard semi-classical ADS 7 geometry.
Maybe I could comment briefly or tangentially on what Rafael was saying. So indeed, I don't think that if we just look at normal string theory, look at for the eigenstates, nothing ensemble averaged, well then I think the horizon is not smooth. That's the fuzzballs you get and it solves the puzzle. I also am not sure that there is a good sense in which you can average over microstates and thereby get something smooth. So what I'm trying to say is, if you take, let's say, one piece of coal, and when you fall in, you hit the surface, so you can't go in. And you take another piece of coal with different shape, and you again hit the surface, and you can't go in. I don't actually know if there is a sense in which you can average the states and say, hey, now I can float freely into this piece of coal. So I think it would be interesting to know. I mean, so the fuzzballs are just behaving like pieces of coal. They have extra properties like the entropy, which is high, like the Becquerel entropy, and they have certain properties. But apart from that, if we just think of a StatMech system, it would be good to see if one can make a toy model where you can't go into one pure piece of coal, you can't go to another piece of coal, but somehow you can freely float into the average of the pieces of coal. So I'm not quite ever understood if one can do that. And I'm concerned that at least that you can't do. I think one is talking maybe more of trying to find some correlation function, but let me really press the question on you that do you really think that you could get a horizon that you could smoothly float into, or where you could then naturally create entangled pairs. I'm just talking about the actual Hamiltonian at the horizon being smooth, the vacuum being the actual vacuum. Is there some sense in which one could do that for maybe a piece of coal? So
I think that one important difference, right, is that there's a very specific entanglement structure across a surface in space, and that gives rise to some spectrum of the density operator on one side, which is shared by the radiation that comes out of a black hole. And it's it's that feature which, for example, is exploited in approaches like Papadopoulos-Raju and ER equals EPR, which I think would not generically be shared by the radiation coming from a piece of coal. So there's at least a shot that you have in gravity, I think, that you don't have for the coal, though I'm skeptical, as you may, but I think there's an important difference.
Yeah, you even have to break a global symmetry. You really have to carry it throughout to get right entanglement structures between exterior mode and the rest, including Boltzmann coefficient of the sum-free double states.
I just want to ask a question to Samir and maybe Rafael. You see that just statistical mechanics tells you that if you so this is slightly different from the ensemble average question, but if you really were to take like a superposition or a typical pure state, the experience of an infalling observer in one typical pure state has to be exponentially close to the experience of the infalling observer in another pure state. I mean, that's just because it's a large system, and so all these observables have to be within e to the minus s of each other. So there must be some universal geometry that describes the experience of the infalling observer. It can't be all discrete fuzzballs which describe this. And so the question is, if that universal geometry is not the conventional black hole, what is that universal geometry? Because there must be some universal geometry just by statistical mechanics for a typical pure state.
I could tell you what I think would happen with the fuzzballs. And first, let me actually say that if you have a quantum system and you want something to be similar, I think you're really asking the question at a quantum level. And if you take a single spin maybe, and you send it into two different glasses of water, I don't think the evolution of the spin is the same, even though the water is a big system. In one, it may flip up, down like this. In the other, it may go up and down in a different way. If you ask a bad question, like what's the average value of sigma z, well, then you'll get the answer in both cases, the average value is 0. But that's not the actual question we should ask. We're actually asking if, I carry a spin in, will it really stay in the state, and can I do the interference things I would do with two spins and so on. The way I think it would actually work out with fuzzballs is if you actually went inside a fuzzball, started knocking around, two different fuzzballs would look as different as two glasses of water, and then you wouldn't have seen anything. But I think the way that this fuzzball complementarity ideas we were trying to develop would work, in case they were correct, is that if you throw in something with high enough energy, it's not the original fuzzball that you actually end up exploring. If you add an energy E, you actually create new fuzzball states, because density of states is very dense. In fact, you create new excitations, which, by the way, are not entangled with anything because you just created them and they've come with extra energy. And the evolution of this new part of phase space, that can be universal. So the idea of the fuzzball complementarity was, if you come with enough energy, you are creating new excitations, which are motion on a space of configuration, which were not right now occupied. So the fact you've gone from energy E to E plus delta E is the delta E, the new degrees of freedom, which are having a universal evolution. And so delta E being much bigger than T was important and was the approximation. So I think I'm just answering your question at two different levels. If a spin goes into a glass of water, I don't think just because a glass of water is big, it sees the same thing in both cases. So that's how I'm trying to define the problem. But the reason it can still do it in the case of the black hole is that because the states are so closely spaced, you don't actually end up exploring the fuzzball you had that you fell into. When you bring the energy E in, you actually create a whole band of new states, and it's the evolution of those new states, how the wave functional spreads over that new phase space, which I think can be universal to a good approximation. And that was the idea of fuzzball complementarity. We don't know if it is true, but you can make a bit model exploring that. Okay? We made a bit model which does that, but I don't know if that is reproduced by actual fuzzballs. Okay, that's all I had to say. Maybe Rafael has some comments.
Well, I would say that I agree that I would expect an infalling observer to experience in a coarse-grained sense more or less the same thing, no matter what state the black hole is in. But I think the question is whether that thing is a smooth fall across the horizon or going splat on a firewall. And I think the key difficulty is that the vacuum at the horizon is a unique state, but a black hole and its radiation should be able to correspond to either the A/4 state. And so it's very easy to get the same experience for every observer if they go splat on a firewall, because there's presumably, if they exist, many different ways of making one. But it's very difficult to arrange for that unique state that you need at the horizon for an infalling observer to arise when there are so many different states for the black hole, as you know very well. But that's how I would, yeah.
But I think horizon could be unique at the coarse grain level. In other words, at the semi-classical level, you have a parameter m, which is even continuous. So it's not even e to the A/4. You have continuously many different black holes. That's right, A/4, a blank square, h bar is denominator. So if you go to the classical, and e to the A/4 is a different mass, continuous mass even. And that all looks like a vacuum at the coarse grain level. It's not sensitive to the detail value of m. That's.
I have an outsider question for the experts here, if I may. How literally or seriously should we take this averaging that goes outside the main framework? Should we take it literally? We just have to average? Or should we view it as kind of a temporary caricature of what will eventually replace it? The example that comes to mind is the Bohr atom before the Schrödinger equation. So is this something like that, or should we take it more literally?
One possible answer to this question is that it depends on which theory we're talking about. And for some theories, we're supposed to take it literally. And for other theories, we're supposed to improve our understanding later.
I don't understand what it means. There is the ultimate theory of gravity. If people study that, say, in 100 years, how do you think, what's your view now, the way they will view it, say, in 100 years? This was a step in the right direction, but there isn't really an ensemble of theories, or yes, there's an ensemble of theories and a complete picture with a unique theory before that point was completely wrong. Which of the two options you think will materialize? You might also say that you don't know what will happen.
I guess I'm trying to reject your two options. Like, I think it can happen both ways. So there can be theories of gravity that make sense, where there's an ensemble. Maybe they're very rare, but there are some. JT gravity is an example. And there are theories of gravity that do not have an ensemble, like the dual to n = 4 super Young Mills. So for the theory of gravity that's dual to n = 4 super Young Mills, the ensemble is not the right answer. And I'm not sure if we'll later think of it as a first step in the right direction or something that was a little bit misleading. Time will tell.
Are the theories of gravity with the ensemble, are they theories of quantum gravity? Is it quantum mechanics? Is there a quantum state that evolves, or is it something different?
Yeah, it's a theory of quantum gravity defined by the path integral. If you'd like,
I don't understand this discussion. I was following the whole day, and at the beginning of this section and earlier today, there was a whole discussion, especially from Andy, whether we need string theory or not, and there's a unique theory of quantum gravity or not, and to what extent this depends on the microscopics and all that. And now your answer is, well, it depends on which theory of quantum gravity. So I don't see how these two parts of the discussion can be simultaneously correct. Now, my understanding is that in ADS, this is one particular background, and it might be that one particular background is easier than other particular backgrounds. But I don't think that we need an ensemble in some theories of gravity, but not in others. But what do I know? I'm an outsider here.
Nati, would it help if we made a distinction between whether an ensemble could exist as a mathematical duality that is interesting to study, such as the kind of things that were studied by Sachenko and Stanford, versus what the actual theory describing nature is? In other words, if you make a black hole in your living room and you want to know you want to describe the radiation that comes out. Personally, I would expect that that should be described by a single unitary theory. I have no idea what it would mean for the real world to be described by an ensemble. But it seems like we're learning a lot by studying models in which such a duality can be made fairly precise.
Perhaps we could go to some of the hand-raised questions. Seth Catalano has his hand raised for a while. Seth, you can unmute yourself.
All right. Hello. This is to anybody that would want to answer, and it relates a bit to something that had been talked about earlier. But I was wondering what you all think about whether or not we should try to be incorporating ideas from other quantum gravity frameworks, such as the idea of manifest background independence, or using a connection as the fundamental object rather than the metric when we develop our quantum theories of gravity? Or is there reason to believe that these are dead ends still in 2020?
I would like to mention on one idea for quantum gravity that had been proposed in the past by Gurau, for example. And that idea then got incorporated in our current understanding of the SYK model. It's closely related to tensor models and the SYK model. It might be that some other ideas that are floating around of quantum gravity can be incorporated in some way, maybe reinterpreted as necessary. Probably we'll also have to reinterpret string theory in the future.
And you say that was who?
Razvan Gurau.
Okay, thank you.
One comment I would make is that I think the path integral calculations are manifestly background independent. Certainly if you're doing full gravitational path integral, you're fixing the asymptotic boundary conditions, but other than that, you don't have a background geometry.
For that matter, string theory is background independent. You calculate the S matrix in an asymptotically Minkowski spacetime, and the definition really depends on the asymptotic geometry. Everything is fluctuating inside.
Wait, I'm sorry. Can you repeat that? Because if you're using a background to initially
define
put the model.
What's correct? Let's discuss general relativity before we just classically. What's correct is to define the asymptotic background, and then you consider anything that can happen in the interior given that asymptotic background. What people usually call string theory in Minkowski space is really string theory in an asymptotically Minkowski spacetime. So it's misleading to characterize it as not being background independent. It's background, it's the correct treatment with that asymptotic background. On another point that was raised, the question of whether one uses a first order or a second order formulation is technical. It's not a conceptual difference. So on the scale of things that have been discussed by the panel today, that's a kind of infinitesimal difference, or one or the other might be convenient for some purposes.
I see. Okay, thank you.
I guess Raghu is next.
Yes, I wanted to ask about the singularities. In particular, so we've learned that we can compute trace rho log rho using these replica wormholes, but all indications are if you wanted to compute like rho ij, where I and j are specific, Bryan-Ket indices for the density matrix, you will not get this from the replica wormhole. So does the singularity have to come in at some point in these calculations? And the second part of this question is, in the spirit of what Andy was saying, in string theory, do we have a slightly generic mechanism for resolving singularities? It seems like there are specific instances of how we can resolve them, but is there a sort of a more generic mechanism in string theory to resolve singularities?
I could comment on that. I think there's very noticeably not a general mechanism for resolving the Schwarzschild singularity. It would be interesting if there were. There's some singularities. There's a lot of singularities that we've had great success in solving. But that, of course, is a question that you would expect to need microphysics to answer.
Right. So I would expect that
it's a good sign of whether you have a good microphysical theory or not, whether it can resolve the singularities. And the failure of string theory to resolve the Schwarzschild singularity or to say much new about it at all, of course, is one of the things we have to deal with.
But Andy, string theory can resolve the singularity of extremal black holes, which is behind the horizon. So we know very well that the way singularities are resolved, a la Polchinski-Strasser and Klebanov-Strassler, in exactly the same way, the singularity of extremal black holes, which is behind the horizon, can be resolved by string theory, and it's exactly the same mechanism. Branes and fluxes and topology change. So given
those are time-like singularities. So there have been spectacular successes in resolving a huge host of disparate time-like singularities. And I think it's one of the best reasons we have for having confidence in theory. What?
But the Schwarzschild singularity with one electron, it becomes time-like. If you throw one electron into Schwarzschild, it becomes time-like. So it's only space like when the charge is exactly zero, but just throw one electron.
You perturb that a little bit and it becomes null. So
I know, but time-like
horizon. So I think it's a different story. Anyway, whether it's different or not, it's one that hasn't been.
I think it's interesting that these theories that have ensemble averages that are well understood ensemble averages like JT, they don't have a singularity.
But do they go through phi equals 0, those theories? Most of those theories are, phi is integrated out at the beginning, and the singularity that would be the relic of the higher dimensional singularity would be the thing at phi equals 0, and that's sort of thrown out from the beginning, right?
It's really phi equals minus infinity.
Yeah.
Yeah, it's thrown out, but the reason I make the point is that perhaps understanding this issue of ensemble versus non-ensemble will teach us something about the singularity.
I see.
Yeah, right. I guess the question is, are the quantities which are non-self-averaging intimately related to the singularity in some sense? Like the individual matrix elements of the density matrix or the S matrix.
I'm not sure.
Okay, thanks.
Well, let's move on to Steve Giddings, who seems to be next.
Thanks. So coming back to this question of ensembles, and this goes back to Nadi and Sandip's question during Douglas's talk. So if the ensemble story is like the old alpha parameter story, then you can focus on a member of the ensemble, which corresponds to, in that case, just having a particular set of couplings. And then within that member of the ensemble, you're back to the original question, how do you describe the unitary evolution in that member? So in a sense, you don't have to worry about the ensemble. Once you've done that, you forget about it, but you're back to the original problem. And then the problem is, how is evolution unitary? In the conventional description, you have, the black hole subsystem. It builds up a huge amount of entanglement with the outgoing radiation. And the big question there is, how does that entanglement transfer out? Now, I've argued small interactions can accomplish that. We can debate that. But then, if you're going to take the point of view that there's an island story, that looks like some other re-identification of the black hole subsystem or part of it with the outside radiation subsystem. And there's the question of how you make sense of that in that context. So I'd like to just maybe throw that out and pose that partly as a question there.
I think what they might be doing that's different than what we did back in the 80s is we just we used the kind of 0th order approximation. No couplings between baby universes and no coupling between baby universes and other things in the geometry. And I've tried to reinterpret what they've been saying as, if you do a very special measurement, you'll couple more to you'll couple more strongly to a baby universe, and that can grab some information out from behind the horizon. But those are just words.
The simple ensemble story I was just referring to, it's true, involved ignoring baby universe interactions, and you and I considered other aspects of baby universe interactions.
Yes, we did. Yes.
But it's not really clear that that's sufficient to give the extra juice to this story to make it run.
But that could be said about anything. It's not really clear could be said about almost any statement in those follow-up papers.
Okay, but in any case, if one wants to make a claim that that's going to solve the problem, it would be nice to understand that.
Yeah.
So I'd just like to emphasize once more, I think, related to what Steve said. I don't think in this whole story there should ever be a need for adding interactions by hand that transfer the entanglement from the interior to the exterior. And I think that if there is this story of having to identify degrees of freedom in one place or the other place, I think, as Samir also emphasized, this is something that should work even in the absence of black holes, and I think it does. And I think it's something that we can examine even in empty space, even about the ADS vacuum, where I think we understand things very well. And I think we should take that seriously and think of that as a physical model for what is happening about black holes as well.
I think in some sense you're arguing that a black hole is not really a subsystem, because if it is initially a subsystem that builds up a lot of entanglement with the outside, and if you want to get the entanglement out, you have to have some interaction that transfers it out. And I think it sounds like your arguments are saying it isn't really a subsystem, that really the entanglement or the information is encoded outside. I'm not sure if that really holds up when you look at perturbative construction of the dressing and so on. That's another discussion.
Well, I would say it's not an exact subsystem, but I mean, it is a subsystem to good approximation. But I think this goes back to the question that Samir was asking. I mean, if you start asking fine-grained quantum information questions, then sometimes these things that look very different might need to be identified. But then for a lot of coarse-grained questions, they're clearly separate. And I think there's no inconsistency in that.
I'm not sure who's assigning who speaks.
There's a
question. Hand up.
Can we? There's a question from Andrea Pum about the averaging story on the chat. Maybe somebody wants to. I can read it out, and somebody can.
Sorry, I have the hand up for some.
Sorry. Okay, go, Abhijit.
Yeah. Sorry. This question is mainly for Edward. Slightly tangential, but I think still relevant for this discussion. In your paper on global gravitational anomalies, you talk about, you try to find a principle which will teach us what to include in the gravitational path integral and what not to. And the answer part of this principle, I think, that you deduce is the cluster decomposition. So, and from that point of view, the configurations that stand out are the ones that differ in the exotic structure. So how do you think that discussion fits in this story, where the gravitational path integral is performed with the inclusion of all sorts of topologies, not just topologies that could, that are required by cluster decomposition?
Is Edward still there?
Anyone else has any comment also, it would be nice to hear.
Edward, I think the question was for you.
Is Edward still there?
Edward is muted.
What was the question? Sorry.
Hello, Edward. Should I repeat the question?
Yes, please. I can't hear you.
Sorry. Yeah, sorry. The question was that in your paper on global gravitational anomalies, you talk about cluster decomposition being one principle that tells us what sort of configurations to include and what sort of configurations not to include in the gravitational path integral. And the conclusion was that the configurations having to do with exotic structures, different exotic structures, are the ones one should include because those are the ones that are dictated by the cluster decomposition. So how do you think it fits in with this story?
Okay. What I said was that the most conservative interpretation was that exotic spheres had to be included because you could prove from cluster decomposition that they had to be included. I said that purely cluster decomposition doesn't tell us what else we should include. But by now it's clear that all kinds of other things should be included. Roughly speaking, everything.
Thank you.
Okay, Deepak, you have a question?
Hi, yeah. Thanks. My question is for Sovrat, actually. The question is that, so your statement is that given observers sitting in the space-like slice at the boundary of the space-like slice in ADS, these observers can conduct measurements which will tell them about the state which is in the interior, in the bulk of the ADS, right? So the question is that if you want to conduct such measurements, right, you have to perform some sort of a computation, right? So, and those observers themselves are also part of the geometry, right? I mean, you cannot think of them as like external to the geometry in some sense. So the question is that, like, is there possibly a situation where there is some back reaction due to that fact, which might create an obstacle in your plane?
Yeah, I think that's a very interesting question. Actually, it's I think the kind of question we don't engage with enough, which is, you know, when we think of measurements in quantum gravity or in a cosmological setting, we don't have the nice separation that we usually have in quantum mechanics, where you have an observer who's, you know, making some measurement, and you have a clear separation between the observer and the system. And so the kind of question you're asking now is, as I said, you could have these observers who live near the boundary and who make unitary manipulations and measurements, and they're able to get some information about the bulk. But you're right, one could ask questions about whether there is some uncertainty because of some necessary back reaction that appears or something like that. And that's the kind of thing you wouldn't worry about usually in quantum mechanics. You have a system, you make a unitary manipulation and a measurement, and you don't worry about whether the fact that the detectors themselves are part of the system. I don't have a good answer to that, and I think it's an excellent question, and I think it would be great to understand how measurements work in a cosmological setting, and how quantum mechanics works in a cosmological setting when the observer is part of the system themselves. I don't know, maybe other people have something about that.
May I make a comment?
No.
Sure.
Oh, I'm sorry, I don't know how to raise hand. So if there's people before me, please go ahead.
Go ahead, say what you want to say.
Okay. Yeah. So about the observer thing, yeah, I think that's really important question, and just want to mention that I have a new work together with Xidong and Zhenbin Yang and Shangnan Zhou, which appears next week, where we discuss this using some tensor network models and also in some gravity theory. And just I think that the key point, for example, one example is, I think if we assume we can have a strong, we can have an observer that's very powerful, that observes arbitrary correlation functions in the island, in the entanglement island, then the entanglement island is not an island anymore. That's excluded from when you say you calculate the same region of Hawking radiation, which has this entanglement island. But if at the same time you can observe arbitrary things in the island, then that's gone.
So your paper will be out next week?
Yeah, hopefully Monday.
Awesome. Thanks. Thanks for your answers, Subra.
Daniel Hollow, you've still got your hand up.
Yeah, I still have a comment. Is it okay if I make it? So I wanted to emphasize something that Juan mentioned also in his talk. So, you know, there's all these debates about, do you include the wormholes, do you not include the wormholes, and so on. But there's, to me, the same mystery has already been there all along with the Gibbons-Hawking calculation, where I think that, you know, we were discussing, is there input from UV physics or not? Well, if you really just tried to compute a partition function in the bulk using the Euclidean path integral in the standard way, then you would do a Euclidean path integral where the spacetime is a circle times something, and the circle wouldn't contract. That's how we compute partition functions in every other kind of physics, except for gravitational physics. But in gravitational physics, we somehow have decided that we're allowed to compute partition functions in a different way, where we allow the circle to contract, right? If we did that in a statistical mechanics system, people would tell us we were crazy. And I think that that is where one example of a situation where there really is some kind of input, we need some kind of input from high energy physics to really tell us that we're allowed to do that. We can of course assume it and see what we get, which is what we've been doing for 40 years. But I mean, to me, you know, the evidence that it's really right to do that is that there are calculations like the Strominger-Vafa calculation or an ADS-CFT, where you can see that the entropy you get from that saddle point is really the right entropy. And without any kind of input from the UV, I think it's just something that we're making up. I mean, we don't know whether that's the right, we're allowed to include contributions with that topology or not in the Euclidean gravity path integral, just from the bottom-up point of view.
But sorry, wasn't the fact that that calculation gave exactly the right answer for the entropy and showed that the pair of black holes were quantum correlated strong reason to believe that that was the right way to do the calculation?
I'm not sure. I could just say that since the circle contracted, it's clearly the wrong way to do the calculation, right? I mean, I think we have to somehow put in some assumptions about what we think is reasonable. And I mean, the way Euclidean gravity has always worked is that we do a calculation, and if we like the answer, we say, okay, we're going to include that saddle point. And if we don't like the answer, then we say, oh, it was crazy to include that saddle point. We shouldn't have included it. And the reason why we're in that silly state.
I don't think that, because you could pair create, cluster tells you you have to be able to pair create.
But you're imposing some
monopoles at the end of strings, right?
I think you're imposing a principle there of cluster decomposition, right? I mean, Euclidean gravity path integral. The word Juan used is oracle, right? It's an oracle, and we just we play with it and see what we can get by doing different things, and we try to make up a story that's reasonable. But I think that in the end, like with a real UV complete theory, right, it would tell us which configurations we include.
There's a general rule about computations in physics. If you do an approximation and the approximation looks sensible and the answer turns out to be finite, then this is the right answer. If the calculation is infinite for some reason, it means that you did not take into account some physics that you should have taken. And I actually don't know of a counterexample to this rule. So I'm actually not surprised that if you do a sensible calculation that gives a finite answer, the answer is meaningful.
I agree with this.
And that also addresses some of the question to what extent we should be surprised by an IR computation being sensitive or not sensitive to a question that could depend on the UV. I hope I made myself clear, because from all the chat here, I realized that people did not understand what I said before. So I feel very frustrated. So I'm really hopeful that this was clear.
Yeah,
I can also add that what Hawking always said was, if you want to know why a classical black hole has an entropy and a classical soliton in any other field doesn't, you should just look at the fact that when you do this Euclidean path integral, the Euclidean time circle pinches off in the black hole, and it doesn't. So you don't have the product structure, and that gives you the entropy even for a classical soliton. So yeah.
Emil?
Yeah, so I just wanted to follow up on that. So the Euclidean calculations in gravity seem to know more than they should. They can compute the entropy microscopically. And the cousin of that calculation, for instance, is the Carty calculation of the entropy in a 2D CFT, right? Where you do some modular transformation and you look at some identity channel in the dual channel. It's not that the identity channel knows something about the microstates, it just knows how many there are. And so what I'm wondering about these more recent calculations is that the Euclidean calculations that are being done with replica wormholes and so on give us answers that are very appealing and seem to be tracking some details of the microscopics. And where we seem to kind of stumble is in trying to give those calculations a Lorentzian interpretation, because then that leads to islands and all these puzzles we've been discussing. So I'm wondering if there's some wiggle room to accept the Euclidean calculations as, knowing something about the coarse-grained features of the theory, but that we shouldn't try to put too much into them and analytically continue them to a Lorentzian slice where they seem problematic. So I'd be curious to hear panelists' opinions.
So I think that has always been my view, that the actual states of the black hole, they don't have any horizons and they are then given by the fuzzballs. You can always take all those states. A state can be, you can think of it as Euclidean non-Lorentzian, just a state. And then if you evolve them in Euclidean time and make a one loop path integral, okay, that will be some finite number. It's a normal states in a normal theory. And then this particular path integral may actually have a saddle point, which is then given by the Euclidean cigar geometry. And so that saddle point is fine, doesn't have the interior to the black hole. The saddle point can be used to compute this path integral. But then you shouldn't continue a saddle point back to the Lorentzian section because it's not computing anything there. So I think that's when we make the mistake. In the Lorentzian section, they are all actually fuzzballs with no horizon. In the Euclidean section, you can define a one loop path integral, and the saddle point of that is the Euclidean cigar black hole geometry. But again, we never continue a saddle point to Lorentzian and ask, what does this guy mean? And I think exactly as Emil might be hinting there, I think that's where we make a mistake. If we analytically continue to the Lorentzian, we just get a tool. And I think whatever calculation we have seen sort of working with the Lorentzian geometry, it seems to me that they have always things which can be computed on the Euclidean side, like a two-point function, and then analytically continued to Lorentzian. So sometimes we say we've used the Lorentzian black hole and look, this particular two-point function of one scalar field on the left, one on the right came out to be correct. But then we should go and check if that was the same thing which would have worked on the Euclidean section and then analytically continued. Then it hasn't really come from a Lorentzian calculation. You continued both the geometry and the path and the operators, and so it worked out. So I think indeed it's the Lorentzian continuation to the traditional black hole, which I think is the problem. It creates the horizons, the informational problem, the singularity, but I think none of that should be there.
I think there is an old calculation that was done by Oppenheim and Snyder of a collapse of a shell. And they shown that the black hole forms, there is an interior and so on, and there is no argument that this calculation is wrong. So there's no need to do some Euclidean computation.
There is, at least in collapsing M2 brains, there is, because there's a tunneling. You have e to the s possible states.
Well, this is a vague argument. This is a vague argument. I like to see a concrete calculation.
It's done. It's, I mean, if you take M2 brains and you look at them tunneling into bubbling microstate geometries, you can calculate and you find exactly e to the minus s tunneling probability for e to the s possible states. So the calculation is done for a toy model with collapsing M2 brains instead of collapsing dust. But the calculation is done. It's not, and it gives exactly what you want. And there's a very nice conspiracy, how things work and so on. So this is known. I mean, the Oppenheimer-Schneider calculation ignores quantum effects, which should be there. And again, the quantum effects come because you have a huge amount of microstates, and it's like this enhanced tunneling. So the Oppenheimer calculation is invalidated by this calculation directly.
So I'd just like to respond to what Samir said earlier. I mean, in fact, I think we all agree that none of these calculations are giving you watertight evidence that the interior is smooth. But I think a lot of these were, I mean, these ideas originally, I think, were really brought into relief with the paradox that Samir himself set out, which is that if you look at degrees of freedom near the black hole, they look near the horizon, they look like they're entangled with each other, but it also looks like they're entangled with the radiation far away. And of course, one resolution to that is you could say, maybe the interior doesn't exist, or you could say the interior has another, the interior and the radiation in some sense have to be identified. And I think the fact that they have to be identified, I want to emphasize, I think there's a lot of evidence for that. And I think there's a lot of direct Lorentzian evidence for that. And I think that's also something we can see in the absence of black holes, that if you make suitably complicated measurements far away, you're able to, you could get these kinds of monogamy paradoxes. So I think, to the extent that these arguments suggest that, just this monogamy paradox is not a requirement for structure behind the horizon, I think to that extent they're persuasive. But I think, I agree that, and I think everyone agrees that they're not directly telling us that there's nothing behind the horizon. Maybe there's somebody could come up with some other argument telling us why there's something behind the horizon. But I think the monogamy paradoxes are addressed, and I think they can be addressed directly in a Lorentzian setting as well.
Okay. Well,
Okay.
I think we'll leave it there.
Okay.
9 o'clock in that time zone. So thank you very much for everybody who participated. And I'll hand it back to Jeff.
And thank you, Malcolm.
Thank you, Malcolm. So I'd like to thank Malcolm and thank all the panelists. And I think this was a great discussion. It looked like it certainly go on for another couple of hours. We're 2 hours in and it didn't seem to have slowed down at all. At this point, I would like to see if David Gross is in the room. Hi, David.
Hello.
Hi.
Hi.
Okay, so I would like to welcome David Gross to share with us his vision of where string theory is in 2020. Thank you, David.
So let's see how to do this. Okay. Okay, is that set up?
Yes.
And you can hear me?
Yes.
So Jeff asked me to give a vision talk, but only gave me 15 minutes, which more or less coincides with the amount of useful vision that I have to impart. This has been an amazing conference. We're all astounded by how well it has gone, even though we're living in very difficult times. We're separated across the world, and yet Jeff and his collaborators have managed to bring us all together. Not just the usual 400 to 500, but if I understand correctly, 2,304 participants. I find that amazing. Sessions that I've attended, there have been no more than 500 to 600, but maybe people rotate a lot. But in any case, no matter what the number is, it's an astounding achievement. And it has been a great week. I've enjoyed it immensely. And that really is great because, as we all know, the world is in a mess. I mean, we're faced with crises everywhere we turn every day, which seem to be getting worse from week to week. So This week, however, has reminded us all that we are a very lucky bunch. And first of all, theorists, theoretical physicists, and second of all, high energy theorists, and especially string theorists. We're lucky because as theorists, even though many of us are locked up and have been now for months, we can still continue to work and produce all the wonderful physics that we've heard about during this last week. Unlike our experimental friends who are really in a desperate situation, they can't get to their labs, they can't explore nature using experimental tools and observation, but we can. And we can go on. And in fact, if anything, my impression is that productivity among this group increased. Actual evidence, physical review has worried that during the pandemic, submissions would fall off and journals would suffer. But in fact, in theoretical physics, submissions have gone up. So we're really lucky. Not only can we work, we also can do what we do calculations and explore with paper and computers the nature of reality. And that certainly is a great diversion from the mess that the world is in. This conference also reminds us what a great community we have. I mean, with the 500 to 2,300 participants, if I look through the participant list, what community we consist of. And the nature of the visual conference enables all of us to participate in ways that are, go somewhat beyond the usual conference in person, I think. And I think we're going to have to, in the future, adapt some of the tools that we're learning from the virtual world that we're forced into nowadays into future conferences, which I hope will be physical. We will be able to meet in person, but at the same time, we should use these tools to enable more of our colleagues around the world to participate fully in the conference, as was the so let's go on to the physics, but we should all remember that the world is in a mess, and we're all going to have to work hard outside of physics to clean up the mess that exists. There are enormous threats to even our enterprise from increased nationalism, and they threaten the kind of mobility and collaboration across national borders that we take so for granted in our enterprise. So the conference has been amazing. And just a brief survey of the various topics that we have learned. Of course, the first talk and it had to do, like so many of the talks in this conference, with the primary tool that is available in string theory and related fields at the moment, which is the ADS-CFT correspondence. But here, we really seem to have for the first time a derivation, or close to a derivation, of a particularly simple case of the ADS-CFT correspondence. ADS 3-CFT2 in a very special case, which sort of corresponds to the tensionless string, which Rajesh and collaborators are close to deriving, in the sense that they can they hope to be able to show that the observables in both sides of the correspondence obey the same equations and are therefore this would be a major step forward and perhaps lead to, in many directions, to understanding better the correspondence and expanding it. Very exciting. There are a lot of other works on more traditional aspects of ADS-CFT and new directions, CFTs with defects and their duals, melon space, technology, and much more. Some of these advances are really amazing, and I find them, this happens every year. You go back, as I did, thinking of this talk yesterday, to conferences a year or two ago in Okinawa and in Brussels. And it's amazing how much in this field we accomplish on every year. There was also a talk on celestial conformal field theory or flat space duality by Strominger and Poon, which I found fascinating, also in its infancy, but beginning to give some hope that one could really have a dual description of flat space theories, in particular string theory, but it still seems to have a long way to go. Then, of course, there were talks on quantum field theory, which Nadi likes to call the language of physics. It certainly includes more than traditional quantum theory, includes string theory, but perhaps Nadi believes that string theory is just quantum field theory. In any case, here we had some impressive works on the general program, which includes the bootstrap, although there weren't many, or if any, bootstrap talks in this conference at all, but rather general, the whole program of trying to derive constraints on the S matrix, on observables in a relativistic quantum mechanical theory, with or without gravity, from general principles. That is, sort of in the old bootstrap. And it seems to me always, well, absolutely fascinating, and in some cases very powerful constraints and some rules. But the goal appeared to be originally, are there other theories that include quantum gravity, or are UV completions of theories we know about, which are not string theory? As far as I can see, the general conclusion tends to be that the constraints that one explores are realized in string theory, and so far in nothing else. There were some very new ideas about symmetries, dynamics in quantum field theory, fractons, and higher group symmetries, which seems somewhat disconnected from what we're discussing now, but not completely. And as usual, Nadi is certainly right that any advance in our understanding of quantum field theory will have implications for everything else we work on. And then there's what might be called more traditional string theory studies, including actual use of non-perturbative effects, exploration of non-perturbative effects, instantons, in string theory. Soluble matrix models, descriptions of string theory, or string field theory by Sen and Yin. These are very impressive calculations and certainly should motivate the community not to be afraid of doing non-perturbative string theory. And then, of course, the study of the space of allowed, of compactifications and of string theory, and the exploration of other effective field theories that do not come from string theory, the so-called swampland of theories that, effective field theories that don't have a string and then presumably UV completion. But of course, most of the excitement in this conference occurred in discussing, once again, but in a very exciting way, the black hole information paradox. There have been amazing developments in the last year in this direction, and we just heard today was almost completely devoted to this problem. I must say, at the end of a day which began for me at 5 a.m. in the morning, it turns out you can actually watch the conference, and I really commend the crew in Cape Town for doing this. I was able to talk from my bed over YouTube. It's amazing. And it was such a great talk that I didn't fall asleep. So, but after all of these talks and the panel discussion, although many beautiful results, it's not clear to me, and I have a feeling to the whole audience, of whether we have solved, or even what it would mean to solve the black hole information paradox. Although the progress that has been made suggests that we're getting very close to feeling assured that it has been solved to the extent that, of course, information is not lost. But as usual, raises more and more questions. And at the end, which we just saw, so this slide was made before today's talks, which is good because now I know a little bit more, and I'm a lot more confused. To a sort of a choice or a conflict between fuzzballs and a more traditional gravitational path integral approach to the problem, the new element being wormholes, wormholes that can occur in a treatment of the calculation of entropies using replica tricks. So, it's not whether there's these two ways of looking at black holes and at the information paradox problem are truly different or incompatible. At times I felt that they're compatible. They're just different ways of describing the same situation with, but that's not at all clear. And clearly the debate that we just went through illustrates that many of the pioneers in this field disagree. Wormholes, of course, raised the issue of baby universes and ensemble averages, which I must say, when Coleman put forward this idea and explained how baby universe necessarily violate, sorry, the wormholes and baby universes do not necessarily violate any sacred principles. It just means that one lives in a super selection sector where the couplings of the theory are couplings of the theory which one is sort of averaging over in the gravitational pattern integral are fixed by measurement. It always bothered me because it sort of seemed to indicate that many of the parameters that we need to calculate observables and are not going to be calculable. They're determined by measurements, by the it's sort of like the many universe and it's almost as bad, well, as internal inflation. And it just means that one's hope that all the parameters, say of the standard model and of everything else, and in string theory of the nature of the compactified background is not something you can calculate, but rather is determined by the measurements that somebody carried out in the evolution of the universe. So that might be true. And presumably in that case, the only recourse to calculation of many things we would hope to be able to calculate would be entropic, but I always hated that. And is that really being implied by understand how the information gets out of black holes, so on? I'm very reluctant to believe that, but it's certainly up for discussion, and it will be probably for many years. Is there a way to distinguish experimentally between these two possibilities? After all, it would be nice, as Andy said, to have an answer for the information paradox that depended on, was independent of the theory, but there's, in the end, there's only one nature and one theory, which we're looking for. And it would, unfortunately, experiments are difficult, particularly difficult. So this is more of a question to the panel, which I didn't get to ask, but how would you actually distinguish by carrying out experiments, say asymptotically away from real black holes in the universe, without either falling in, whatever that means, or preparing a pure state black hole? It would seem to me that that's kind of hopeless for a real experiment, right? Because black holes are always going to be in some kind of mixed state. And a mixed state that decoheres with its environment is unlikely to distinguish between fuzzballs and some kind of coarse-grained average, which might very well be described by replica wormholes. So I'm not sure I can't imagine there being an experimental, in the real world, distinction between these two possibilities. But obviously exploration of this question will, I'm sure, push us in directions where perhaps the incompatibility of these two ways of looking at it becomes more extreme. In particular, as many people remarked, trying to push these ideas to cosmological cosmological situations might challenge us in ways that'll teach us a lot. So I'm sure you can see that I am as confused as I think is that many of our developments, but they're extraordinary, and we can come back. We will come back next year, I'm sure, and the following years to discuss black holes as well as cosmology. And I'm going to. So the real reason Jeff asked me to end this conference was to provide an end. You always need an end, and to thank everyone who was involved in putting this conference together. So let me take a few minutes to thank people, and I am following largely Jeff's reminder of who it is that's responsible for the extraordinary meeting. So the talk great. It was a great choice of talks, and the people who deserve credit for that are the Scientific Program Committee, chaired by Malcolm Perry, Fernando Alde, Agnes Bisi, Alejandra Castro, Robert de Mello Koch, Shira Minwala, Kyrgakos Papadimas, and then, of course, the local organizing committee, which probably worked very, very hard to put on this conference and support string theory in South Africa. And I'm not going to read all their names. But Jeff wanted to single out Nathan Moynihan, who worked behind the scenes to make the web page up to date. The videos were edited and uploaded very fast. I can attest to that because I looked at them. They are, this was an amazing production. And then, of course, all of us, the speakers, the panelists, the session chairs, and every one of the 2,304 by now participants that made this the biggest string theory meeting in history. Quite amazing. But Jeff also wanted to thank all the people who helped support this conference financially. Okay. Amanda Weltman and Robert de Mello Koch through the South African Research Chairs Program, Frederic Scholz in the National Institute for Theoretical Physics, Robert Dijkgraaf at the Institute, Fernando Quevedo and Atish Dabla, Martin Britson in the Clay Mathematics Institute, and Michael Douglas, Peter Sverchek, Josh Leppen, and Vladimir Sadov, all of who gave personal contributions to support young people. And Mamogeti Fagkeng, I hope I'm pronouncing that correctly, who opened the conference with a beautiful speech, the Vice Chancellor of UCT, who was very supportive for hosting the conference in Cape Town. And Chiara and Edward Witten for coming up with the idea and driving it of doing strings in Cape Town. Obviously, they've been pushing this idea for some time and made a big effort to help raise money for young people. Now, since nobody attended in person, I hope that this, whatever is left over, this money, will be used to help young people attend the in-person conference in Sao Paulo. Eric Nathan for his very generous use of the photography of Cape Town, and Yvonne Brown and Melissa Largier for finding the best venues for dinners that we never got to use, and the best merchandise that we've never seen. But they did a lot of work. maybe it too could be brought to Cape Town and distributed there. And finally, thanks to Jeff. I mean, we all should applaud Jeff for all the work that he's done and the leadership and carrying off. At some point, there's major claps. Carrying off a seemingly impossible job, very difficult times, and making this a truly memorable conference. Thank you, Jeff. And next year in Sao Paulo, in person, we hope. Thank you.
Thank you, David. And I think with that, I want to make just two comments. One is that at the end of this month, on the 27th of July, because it wasn't enough to organize strings, we're also organizing string math, which will also take place online, and the details will be, the registration details will go up in the next couple of days. So it would be great if we could have just as enjoyable a string math conference. It was supposed to be held in conjunction with strings and a week before strings, but COVID put an end to that. But we're taking that online as well, and we're going to have it at the end of this month. And then finally, before I close, I really need to thank my wife Amanda. We like to think of ourselves as an equal household, equal parenting, equal householding, equal careers. But her equal was clearly more than my equal this week. And I'd really like to thank her for taking up the slack so that we could have this conference and manage it. So thank you all very much for everything that you've done to participate in the conference. It was a very enjoyable week for myself, and I know for my students and scientists in South Africa. And hopefully sometime soon we will see you in person, and hopefully we will see you, most of you, next year in Sao Paulo, as David said, in person. So thank you very much, and that brings this conference Strings 2020 to a close.
Thank you, Jeff.
Thank you.
Thank you, Jeff.
Thank you.
Thanks, Jeff. Thank you.
Thank you, everybody.
Thank you, Jeff.
Thanks.
Thank you. Thank you.
Thanks, Jeff.
Thank you.
Thank you.
Thank you.
Thank you very much.
Very much.
Thanks, Jeff. Thank you very much.
Thank you.
Thank you, Jeff.
Okay, thank you, Jeff, again.
Thanks, Jeff.
Thanks.